Test. 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 Hello? Test. Test. Hello? Hello?
Hi everyone, our program starts in 10 minutes, so you can spare your 10 minutes. I mean, yeah, the door is closed, but still we are ahead of time. Thanks. Oh, cool. You're amazing. So usually even without those, even with those rehearsals, we couldn't do that. So are you ready, Sean?
Yes.
Yes. So I'm excited to introduce Sean Hong Shen from, he's CTO at Pi Squared, and he's going to talk about K, and we are happy to have him today, and looking forward to his lectures and lessons and things that we can learn from him. And you have 25 minutes, including Q&A. We do not have a clock, but let's go. And please give him big hands.
Thank you. Yeah, thank you, everyone. So it's very happy to be here to talk about programming languages and why they must have formal semantics and what we can get out of the formal semantics and so on. So I'm Xiaohong Chen. I'm currently the CTO of Pi Squared, a new startup focusing in the blockchain space. Before that, I got my PhD from UIUC. So a lot of the work I presented here is the work that I did in the UIUC and the work that existed before I even entered the UIUC. It's a long history of serious work on this topic. All right, so I'd like to give a very prompt start. Just remind you how complex software systems are today, and basically they're everywhere, right? So they're everywhere in our daily lives. So they're in autopilot airplanes, banking systems. You find them in cryptocurrencies and smart contracts, AI agents, and so on. So needless to say, these complex systems create higher needs for program correctness. But the other side of the equation is that the way we manage and organize programming language design implementation makes it actually harder to establish that correctness. So let me explain. So how do we approach PL design and implementation in the state of the art? Well, we pick a language, say Java, and we pick a tool that we want for the language, say interpreter. And then we spend years and years and a lot of effort, right, to develop an interpreter for Java. And then, yes, great, now we have an interpreter for Java. But how about the other tools, right? So as users may want to have a formal verifier for Java. How do they get those? And how about the other languages? Are we going just to repeat basically the same procedure for each and every combination of a language and a tool? So are we just going to do that? Unfortunately, yes, right? So that's what we do today, right? So we pick a language, we pick a tool, we consider each and every possible combination, and we implement a specific tool for a specific language. So naturally, it results in higher cost because we need to design, we need to develop, we need to maintain L times T different systems, right? Because of this, you have this quadratic effect going on here. And there is an enormous amount of duplicated work in this scheme. And programming languages become hard to update if you do the tools this way. Why? Because imagine now you want to add a new feature to Java. And imagine the amount of work you have to go back and change all the related tools, right? So there's a big effort, right? So actually, programming languages become reluctant, right, to embrace new features if you do the tools this way. And it's very hard for the tools of the same language to stay in sync with each other as well, right? So what happens very usually is that when a new version of the language comes in, the core most critical tools like an interpreter and or a compiler is immediately updated, but all the other tools like the verifiers or model checkers, they start to deprecate it. Why? Because no one is there to maintain them, to update them, and so on. So this is kind of the state of the art, and what we like to do here is to take a step back, right? Look at this problem and see, is there a better way to approach PL design implementation? So this is what we believe how PL design should be, right? So let's still take Java as an example. So yes, we have Java, and the first thing we should do is define it formally, which means that we want to have a formal semantics of Java. So I depict it as a very big circle to illustrate that the formal semantics itself can be a very complicated artifact, and it can actually take no less time to develop than, say, an interpreter for Java. So it's a big effort. Why? Because this formal semantics is a complete, rigorous, and unambiguous mathematical definition of Java, right? So it defines all the behaviors of all Java programs out there. So it's a very comprehensive artifact, if you think about it. Now you may ask, what's the point of spending a lot of effort defining it? Well, because once you have a formal semantics of Java, then in principle you have all the information to do these tools. So you don't need to implement the tools by yourself. All the tools can be derived in a fully automatic way from this formal semantics of Java. So as you see here, right? So we can derive from the formal semantics of Java all these tools, interpreter, compiler, a model checker, and so on, fully automatically. So this formal semantics serves as the fundamental basis of correctness. And of course, we can extend this vision to all languages out there. So whatever programming language you want to do, define their formal semantics, which is a complete, rigorous, unambiguous mathematical definition of all the behaviors of all programs of that language, and derive all the tools automatically. So the advantages of this approach are clear, right? So instead of higher costs, now we reduce the cost significantly to L plus T systems, right? So each programming language has its own semantics, which, as I said, is a very complicated artifact. So that's L systems out there to maintain, to develop. And each tools is now parametric, right? Because that interpreter right there is actually a parametric interpreter. It takes the formal semantics of a language as input, right? So basically, we're talking about T parametric tools, language parametric tools. So only L times T system out there, right, to consider, to maintain. And by doing so, we reduce the duplicated work via these parametric tools and also the reusable semantic modules, for each languages. Now languages becomes, instead of hard to update, you can actually plug and play your language, right? All you need to do is to define the formal semantics of a language using a tool called the K-framework that I'm going to explain later. But you can really plug and play your language, and this is extremely convenient if you're doing your own language. For example, if you're designing your own DSL, right, for your domain. So this is very helpful because it helps you to get a prototype of your programming language very quickly, right? You don't need to worry about implementing manually, right, a compiler or interpreter or the verifier, right? If you care about correctness, you don't need to do that manually, right? So all you need to do is to look at your programming language as a language designer, right? You care about its features, you care about its behaviors, and you formalize all of that as its formal semantics, and let some automatic language framework do the rest for you. And finally, because because tools are parametric in the formal semantics, they are automatically in sync, right? For example, interpreter and compiler here, they are based exactly on exactly the same formal semantics of the language, right? So they're correct by construction. And for example, if your language change, if you modify your language, all you need to do is to push one button, regenerate all the tools, and you're up to date. All right, so this is how we think PL design and implementation should be, right? So we call it semantics first approach, right? So whatever thing you want to do, define the semantics first, and then everything else follows later. So to give you an idea how a formal semantics of a language looks like, right? So, okay, right. So this is the K framework. So all that I said have been accomplished, right, by the K framework. So I'll be explaining K later. But so basically, how does a K definition look like? So just to give you an intuition, so this is the complete K definition of kernel C, which is a fragment of the C language. Of course, it's sort of like a graphic representation, so it's kind of like automatically generated from the text version. You type the text version, and K has this tool which generates this LaTeX-ish, with the graphic representation. But this is actually a formal semantics, right? It's understood by machines. You can actually generate, correct by construction tools out of it. The point here is to show you that you can actually fit the formal semantics of language in one slide. Of course, you probably cannot read it. We'll zoom in a bit. But what happens here is that, so in the first column, you define the formal syntax, okay, of the language. And the second and the third column, you define what is called the semantics. So let's zoom in a bit, right? So look at the syntax. So syntax, not very exciting. It's defined using BNF with annotations. So for example, here we're defining the syntax of expressions. And this particular grammar rule is for assignment, right? And you have this blue annotation. And there are many annotations in K. So this particular one is about evaluation order, right? Saying that the evaluation order of an assignment is strict on its second argument, which means that I want to evaluate the second argument, the right-hand side, first to a value, and then go on. So basically, from the syntax, right, you have a parser. And just to make things easier, we allow people to write annotations like this one to specify some useful semantics of the syntax. Like this one is about the evaluation order and so on. So once you have the syntax of the language, the next thing you want to do is to think about the configuration. So a configuration is essentially a state, a runtime state of the program, when it's being executed. So it's consisting of all these little pieces called cells, semantic cells. Each cell holds a specific type of semantic information. So for example, all the cells are aggregated in this top-level T cell, and within you'll find individual cells, like the K cell, one of the most important cell. It holds computation. K stands for computation. Basically, the code you want to run. And the code starts to change, starts to evolve as we execute it. And in order to execute the code, we need to also have other cells like the function definitions, the environment memory, the function stack, input and output, and so on. Right? So you figure out what semantic cell should be part of the configuration of your language. And then the rest of the work is just to specify how a configuration should go to the next one. Right? So basically, that's the formal semantics of a language. It's a transition system over configurations, over the state of a program. So the way we do that is like this. Again, so on the top is the graphic representation. In text, you will write something like this. So this transition system is given by semantic rules. And this rule is for assignment. Okay, so let's read the graphic representation. They're identical, right? So basically says, if I have a configuration where in the K cell, the first computation is an assignment. So X is assigned to V. V is a value here. And in the environment, X is pointing to some value which I don't care. Right? So that's what the first line says here. So if this pattern is matched by my configuration, then I rewrite them in the following way. I will write the assignment expression into the right value, V, because that's the semantics of C. Right? The value of assignment expression is its right value. And I will write the value that X points to in the environment cell also to V. So this is this step. This is a rewrite rule, and each step defines the semantics of assignment, basically. And look what's interesting here, and I think this is one of the critical innovation of K, is that you don't mention anything that you don't need here, right? So literally, you just mention the K cell, because you need to know it's an assignment, and the environment cell, where you need to do a rewrite there. So you don't need to mention any of the other cells. So semantic rules are given contextually here. And the benefit of that is it makes semantics modular. So imagine I have C, and I start to add new features. Like I want to add threads. Let's make this kernel C multi-threading. Cool. Well, in order to do that, I need to add semantic cells holding the actual threads and so on. So I'm expanding my configuration of the language. But this rule stays the same. It doesn't need to change. Why? Because it only mentions the minimal right, fragment of the configuration that it needs, that it cares for this particular assignment expression. Right? So imagine you have more cells going on. The exact same rule stays. Right? You don't need to go back and change existing rules. So this is, I think, one of the most important engineering techniques that really make K scalable, because it allows you to define the semantics of a language in a modular way. Okay, we need to move faster here. Yes, yes.
Question about that. So, because you mentioned.
Yes, go ahead.
Sorry, yeah. Because you mentioned concurrency as an example. So once I have concurrency, I will have more than one K cell because there's multiple threads. I will have more than one env cell. I have one for each thread. I might even have one for each stack frame. So something somewhere has to define, like, it's not unambiguous anymore in itself, right? There has to be something somewhere which deals with the fact that, like, I have to match up the threads with the environments and things like that. So this can't be as easy as just leaving it unchanged. So how do I deal with this in a
That's a very good point. So basically, what happens here is that K has this. In order to figure out how to put together the pieces of the cells here. So K has a configuration completion algorithm. And it will take into account of what you just said, right? So for example, if I have a semantics of multi-threading language, which means that my configuration will have multiple K cell and environments and so on, each for each thread. If I just write the rule like this, K will know that I need to find a K cell and environment cell that's as close to each other. So they must be within the one thread and so on. So that's taking into account of the configuration completion of K. If you want to, you can control it. So if you want the flexibility to, I want to match a cell in K and another environment cell in another thread, what you need to do here is to specify that, right? So you'll be wrapping around this K cell with a thread cell, and you will wrapping the environment cell with another thread cell. So K knows that, I'm looking for two different thread cells. One should have this code, and one should have that environment, if you want that feature. Right? But by default, if you just provide a minimal example, K gives you the expected behavior. Right? But that's a very good question. Yes. Yeah. Thank you. All right. So, okay.
Sorry. How are the side effects handled?
Sorry,
side effects.
Oh, side effects? So side effects, you mean, for example, so basically this is, so for example, if V here somehow is an expression, so the reason why there's no side effect here is that V is a value, right? Because, for example, you may have a side effect where V is, for example, x++, in which case you must evaluate x++ first, because that is the, if you remember, right? So this is what this annotation means. When you evaluate an assignment, you want to evaluate the right value first, which means that before you get to this rule, you will get to the rule that tells you how to evaluate x++. And in that rule, the side effect takes place. Because to evaluate x++, you will need to find where the x value is and update it, and so on. And then you get a value and do this assignment. So basically, side effects are also defined as we write rules. Right? Because at any time, so the point is each and every semantic rule here is a transition step from one configuration to the next configuration. So in principle, right, so you have the entire configuration of the program in hand. So you can specify whatever side effects you want to do on that configuration. The fact that you don't see the other cells is a feature of K, because they don't change. Right? But if indeed some side effect happens and something should change, for example, you may have a counter. You may have a counter saying how many assignment statements have been processed. Right? So in that case, there should be a side effect where you have a separate cell holding the counter, and you have to increment that counter. So in which case, you will add one more line here saying the side effect. Yeah. OK, wonderful. Thank you for the question. So right, so moving on, so so just to give you an idea, so this is the complexity of a real world C language. So it has 120 cells, plus more than 5,000 rules, semantic rules, we just saw. So I think this is the kind of, finding that makes us believe that any formal semantic framework must be executable, right? Because we are talking about the definition of a language, right? The semantics of a language is the definition of a language. And we have a definition of this complexity. And how do you know that definition is correct, right? So you cannot prove it. It's not like a theorem. It's a definition. So the only way to do that is to do massive testing, right? So you run the definition against a lot of test programs, and you see whether the results are expected. So if your formal semantics is not executable, then most likely it has bugs that you don't know, right? So so basically that's our firm belief, right? So formal semantic approach must be executable, with the only exception that you may work on a correctness proof against an executable model of the semantics. But you have to, essentially, this is the only practical way to the correctness of a definition. Okay, let's moving on. So I think I will skip this very quickly because we're running out of time. So let me show you. So this is basically K in practice, right? So you see that a lot of pretty complex languages have been defined in K, especially the blockchain languages these days and so on. All right. So I want to spend maybe 2 more minutes to talk about some recent progress on K. So basically, people have asked this question a lot. So what if K itself has bugs, right? How are you going to do that? So a very recent work here is to focus on making K trustless. So we don't need to trust K, right? So we hear that trust is a good word, because the thing about that means you don't need to trust it. You kind of eliminate K from the trust base. So the challenge here is K itself is very complicated. So it's more than 500,000 lines of code, many languages, complex data structures. Of course, it has bugs. And of course, you don't want to trust it. You don't want to take the correctness of K for granted. So, but it's very hard to verify because of this complexity. So the idea is to try translation validation, which means that let's find a logic and use that logic to formalize K, so that everything you define in K, every semantics in K becomes a logic theory. And everything that K does has a logic proof. So I don't care whether K is correct if I can check the proof. And I can check the proof using a very small program called the proof checker. So this is like a way to eliminate K, right? So making K trustless. You don't need to trust K anymore. Instead, you require K to give you a logic proof of everything that it does, and you check the proof independently, right? So, and if the proof checks, then you know that K is correct. So, for example, right? So this is how it works on C. So if from the C semantics we can do a C interpreter which can execute programs and give you some output, right? So for example, this is a very simple program that calculates the total sum from 1 to n, and the K interpreter will say that the value S is yes 50-50. But you don't want to trust that. In this case, you might. It's simple. But imagine this is a smart contract, right? It holds like millions and billions of dollars. You don't want to simply trust K on that. So what you can do is to get a logic theory out of the C semantics and encode this particular execution trace of your program as a logic formula. Now we have a logic theory and a logic formula. What connects the two is the logic proof. So we find a logic proof and check that automatically. And if the logic proof checks, then K is out of the picture, right? So now the trust base is reduced to this very simple proof checker. So I think I will stop here because we're clearly running out of time. But I'm happy to take any questions from you. Thank you.
Thank you for your talk. Going back to your first picture with the semantics in the middle and everything you derived from that.
Yeah. That's a K picture we use like all the time.
So I definitely agree that the interpreter can be derived, but things like symbol executor, compiler, program verifier,
yes,
these things you want, for example, optimizations so that your compiler will produce code that runs fast or your symbol executor runs fast. And these things you can't really derive from formal semantics, or then you have to modify your formal semantics and then the artifact becomes unreadable. what's your experience with that?
So yeah, thank you for the question. That's a very good question. So I think that another theoretical breakthrough of K is it shows that you can actually do formal verification using an operational semantics. And the foundation there is called reachability logic. Okay, so I know that when talking about formal verification, people think about Hoare logic or Hoare, logics like Hoare logic. But if you think about it, Hoare logic is not a logic. It's a design pattern. It basically tells you if you want a formal verifier of your language, design a logic, right? So you have a Hoare logic for each and every language. Reachability logic, on the other hand, is a language parametric logic. It takes a formal semantic. It takes the operational semantics of a language as input, and it gives you sound and relatively complete reasoning of formal verification.
I mean, I understand it's possible to do it,
yes.
But will you do it as well and as fast as a native verifier?
Oh, the performance.
Yes.
So I think performance cares. Performance is definitely so on interpreter, right? So performance, we are currently one order of magnitude slower than a handwritten interpreter. Verifiers, I don't think performance of a verifier matters that much because it's slow anyway, and it's and you do it once and for all for a language anyway, right? So for example, if I can spend half of my day prove my very important program, I'd be satisfied. The point is the usability. How fast can I get a trustworthy verifier for my language? Do I need to like design a whole logic from scratch, or I have something off the shelf to use?
So we'll have two questions from Rob and Conrad.
Yeah, not quite a question, more a response to what you said earlier about Hoare logics being a design pattern. I mean, there are Hoare logics where you just plug in an operational semantics and you get a Hoare logic, right? That's totally possible. Iris is an example of that.
Mm-hmm.
So this is, I mean, you can, given an operational semantics, derive all sorts of logics. But then also what we do in Iris is typically, that's not the logic you want to use. You want to have some nice reasoning principles on top of that. I don't know, do you have support for then adding these things and checking them, or like I wonder how you're dealing with like getting proper domain-specific reasoning principles?
Well, could you be like more specific, like adding what type of things on top of?
I mean, the standard thing is you want to have some sort of nice separation logic to reason about programs with the heap, because you need framing to do any kind of compositional reasoning. If you have more interesting structure in the heap, like if you model all of C, you have fun things like sequence points, and you probably want to have like custom reasoning principles which hide the sequence points from you, so that you can pretend they don't exist, and it's all just separation, and like you just move up the stack from there.
So I think along the separation logic line of work, so there's some very interesting theoretical work, but I think on the engineering side, so no, frame reasoning is not natively supported by K, and the reason for that is we think the frame rule as a property is a blessing of the language. It's not something universal, right? So it's actually a property of the semantics of the language. So because my language is designed in this way, I can prove the frame rule as a lemma. But there's no way for a framework to kind of take that for granted, right? Because there are clearly languages out there. I can design a language which don't have the framing property. So that's what makes it a bit challenging. I acknowledge that to do framing in K, because K faces all the languages. So somehow framing is something you have to do. It's a property you prove about your language, and then you can somehow take advantage of that. So we've not done much on that on the engineering side, but we've started to establish the connection between separation logic and K. On the theoretical side, I can point you to some interesting papers if that helps. Yes.
Okay, thanks.
Yeah.
So with respect to your comment that reachability logic gives us a generic way to derive these things from a semantics, if I'm understanding correctly, this does require your semantics to be stated in terms of a term rewriting system.
Yes.
So what I was wondering was, do you ever feel there are any expressivity problems when you're trying to maybe specify parts of the semantics that aren't so neatly described by a term rewriting system? The main thing I'd be thinking of would be some kind of inductive type system, like maybe for a structurally typed language. I would expect normally things like the weakening rules that are involved in those wouldn't go into a term rewriting system very naturally.
I think yes. So basically, the reachability logic can be plug and play. And actually, if you look at the proof, right, it's a sound and relative complete proof. And the way you prove that is it's complete, modular, all the static reasoning you want to do. So you can really put the, the inductive reasoning of data structures under the big bracket of like in static reasoning. So I just prove like the equality of some properties about the static data, inductive data. And reachability logic only talks about the dynamic part of a program. So if you do that management, then yes, they can be embedded.
So you wouldn't, when you talk about these languages being specified, that doesn't include their type systems, or does it include their type systems?
It can include the type systems if your type system is part of the semantics. What I'm saying is that so basically you can integrate the reachability logic verifier with other means. Actually, as a matter of fact, we do have, like we use, for example, Z3 for built-ins. And you can extend that to like some static reasoning about inductive data types, because maybe that they are more efficient, performant, and so on. So yes.
Okay, let's take the other questions offline. Thanks a lot. We have
Happy
a
to.
coffee break.
Yes.
So please give him big hands. Thanks a lot.
Thank you.
And Matthew. Questions? For your information, coffee break is at 10 to 10. But you can take your time. Yeah, actually, we have 5 minutes spare time, so you can, you can give the talk as you expected. Okay, the second speaker is Matthew Flatt. He's going to talk about lightweight semantics engineering with Redex. Please give him big hands.
So a lot of what I'm talking about today is Robbie's work most directly, collaborating also with Matthias, building directly on a lot of his ideas. Redex is an executable semantics, I would say, at the research paper level of abstraction. Thanks to Xiaohong for giving us a great setup. He's put your head in the right space. We're doing very much the same sorts of things here. We are writing some program in Racket using the Redex domain-specific language. You write down a grammar, reduction rules, judgment forms. Maybe what you get out is, you can run those reduction rules as an interpreter. You can generate some tests to make sure it means what you think it means, typeset your rules for a paper, and so on. Just to get us started a little bit on the comparisons, things I can compare most easily that I know. K, which you've had a great introduction to, and very similar sort of ideas and foundation here. We're going to write a grammar, we're going to write reduction rules. K, if you're building something big, like real-world programming systems, you want K, not Redex. Right? So Redex is going to be this lightweight prototyping, writing a paper, exploring some part of a language. And what I hope to do today is give you a sense of how that feels. So we'll try to work through some code on that. Another thing you may think of in comparison is OT, because we're going to emphasize using other backends like to typeset or maybe prove things. But OT is not so embedded, and Redex gives you more of an escape. You can get out to Racket and do whatever you need to do and get back in the world. That means you have more of an obligation to set up some bridges, right? The thing about OT is you're in this declarative language, and then it can do a lot for you. It can prove things directly in typeset. And you may have to do more plugins in exchange for the flexibility in Redex. And you'll get a sense of what I mean as we go through the example. I'm not going to focus on these things, but there are some extensions to Redex to get you into the proof world. But most of what I'm going to show you today is just about running the interpreter and testing it and exploring it in that way. All right, so know that there are further things that you can do with Redex as an input, but I'm going to focus really just on the interpreter part and running it and seeing what it looks like. Redex is used for some papers, and I just did a sort of naive search and found a few recent papers that use it. So you may have seen it in use before, but I want you to be on the producer side today to see what it looks like to actually run the language and use it. So let's jump right into that. Here is a grammar starting at a similar point that Xiaohong started us starting in K. So I'm going to take this code, not my mail, but go over to Dr. Racket. And you see I've got require Redex there after #lang Racket. I'm going to paste this in. When I run this, okay, nothing happens, right? We've just defined the grammar. So this is the grammar has this identifier LC because we're going to write down terms, but the terms are not inherently attached to this grammar. Anything we want to do, like reduction rules, will say with respect to LC, with respect to this grammar. So we're defining some non-terminals here, obviously, E for expression, X for variables, and I'm just going to throw in some integers because it makes examples easier to write down. You will recognize this as the lambda calculus, and so I didn't need to tell you what LC was. I'm going to have multiple variables just so I can use some dots. So lambdas take any number of arguments, and so function calls have any number of argument expressions there. Variable not otherwise mentioned. This giant name is a built-in name. It says that if I have not used a letter anywhere else, I mean that to be a valid variable name. Not a letter, but any identifier, right? So I shouldn't use E as an identifier, but I can use double E or emphasis or something like that, right? So now that I've got this grammar, we could do more things, but the first thing I can do is just do a Redex match to say, like, with respect to LC and the pattern E. So I'm asking, is this, in fact, a term? 0. Right? So the term form is really quotes, except it's sensitive meta functions, which we'll get to. So I'm just writing the term 0 and say, is that an expression according to my grammar? And what should the answer be? That should be true, right? What if I say lambda 0? Is that a term? That looks badly formed, right? So we should expect a false. And what if I say lambda x0 instead? Right? We're back in a good term world. Lambda xy is fine. But I can't put 2 expressions there with no parentheses, right? That's no good. But I could apply 0 to 8. Now, of course, applying 0 to 8 is not going to make any sense if you call this function. But that's not the grammar's problem, right? The grammar is just saying grammatically that's well formed. Right? I might want to talk about errors in this language. So Redex match is another built-in thing that you write some pattern here. I could also ask, is this 2 expressions next to each other? I've written this wrong, but suppose I try this. It's not, right? It's one big expression. So it should say false. What if I say 1, 2? That looks like 2 expressions sitting next to each other in parentheses. It's still going to say false, though. What if I make it 1, 1? Oh, now it says true. What's happening is E with no subscript is the E for this pattern. And so it's making sure it's the same E. That's sort of unclear. I might have been better off writing _1 in both of these places. So underscores are special. That says an instance of E, a particular instance of E. Right? Or if I put E1, E2 now I can write 13 or some other name here, and now it's true. All right? So that's an introduction to the idea of patterns. And we can use dots, like, do I have any number of expressions here? And now I can write 3 of them, and so on. Everyone with me? Stop anytime you have a question, of course. So, let me throw in some of the other examples here. Yes?
So do you have to use the letter E?
I do have to use the letter E if I'm talking about expressions. Yes. Yeah, so the question. Yeah.
So do you have to use the letter E, like whenever you want to match Redux, like
yeah,
the terms?
Exactly. It's important that I use the letter E. You can see the binding arrow now that I've moused over it to say that's talking about an expression, a particular expression. Yeah. They don't have to be single letters. I've just chosen single letters for compactness here. I'll throw out some other examples. I think we've tried all of these kinds of things though, right? So here I've got an application of a function of 2 arguments to 2 arguments. So all those should be true. Yeah. And of course, if I wanted to write some tests to make sure that things are working, I might require rack unit, say, and just use check true. right? And if I get this wrong somehow, if I said those need to be the same term and it fails, then I get an error. So this is another example of the embedded nature. You just use the usual racket stuff like the rack unit to write test suites. All right, let me correct this so it doesn't complain as we go forward. Okay, so that was just my grammar, but I want to start writing some reduction rules. I'm going to do this in the usual way, which means I really need to distinguish between expressions that are not yet values and values. And the way we do that in a paper often is we say expressions can be things like variables and function calls, but they can also be values, which is where lambdas sit, as well as numbers. So I'm going to refine my grammar this way. Put this in place. And, well, I haven't really changed anything. I've just given myself an extra name here. So all the things work as before. And now that I have that, then I can write the reduction rule that says call by value lambda calculus. When you have a function call, you need to have values for the arguments, and then you can substitute them in. Okay, this gets a bit more complicated, so let me copy this over and explain the pieces. Okay, so we've got just a regular racket define of arrow v, but arrow v is going to stand for a reduction relation. So reduction relation is a built-in thing that's with respect to that grammar. It says the domain is E, so this is a reduction relation that works on expressions. Redex has no idea I meant expression by E, but this is what tells it with respect to this reduction relation. Codomain is the same by default. And then here's the rule. We're saying rewrite lambda x with body E applied to arguments V into, well, substitute x with V in E. Where does subst come from? We'll come back to that. You see this somewhat unusual ... _arg. That means make sure there's the same number of arguments, actual arguments as formal arguments, formal parameters, right? So underscore, you can use underscore with dots. By default, dots mean separate things, unlike variable names, or unlike non-terminal names. But you can make them explicitly the same by using an underscore. And so if we apply this reduction relation, this looks like this lambda applied to 2 and 3. We should get a 2 out, right? Let's try it. We did not get a 2 out. Now we got an extra set of parens because apply reduction relation tells you all the possible results here. What we got is subst x, etc., right? Why didn't it substitute? Well, what is substitution? Nobody said, right? So this is sort of the lightweight, flexible nature of Redex. If you didn't define something, it assumes it's a literal. And then there was no more reductions to do, and so that's what you got, right? Right? What if we wanted to define substitution? Surely we do. Here's one way to do it. Here I'm just doing it the hard way, just writing it out all myself. You could read this. I'll just highlight a few things maybe. This says when we substitute x with the same x going to v, then we should get v out. If x and it's any other thing, then we just leave it alone, right? Now, meta functions, as a convenience, go top to bottom. So this second one won't match. If it's the same x, I could be more explicit and write some side condition that says they have to be different. Then the order doesn't matter. And so on, right? So this is saying I've got some x0s followed by an x and some more x2s, and it's the same x. Well, then it's shadowing. I shouldn't change anything. But in this case, I've got some different x, and so I should substitute recur into the body. Yep?
Is the second rule redundant? Like if you don't write it, the subst xx prime, or if you don't write it?
If I leave this one out, then Redex will complain. I don't know what subst to do. It won't just leave it as subst. It will complain at that point, because I have said subst is a meta function. Yeah. Yeah, define meta function is the thing here that's defining subst with respect to the language LC. Yep?
One thing that is sometimes annoying when doing something like this in a system like Rock is that you have like the same thing as an expression and as a value, and you need to convert between them. I don't see anything here dealing with that. Do you get this for free somehow?
You get this for free. So if I say, does Redex match? I can type LC is 1 an expression? Yes. Is it a value? Yes. They're just non-terminals. I'm just matching them, right? V is included in E. So yeah, I don't have to, in this case,
Okay, so
worry
like-
about the coercion.
So it's like one big grammar, basically,
Yeah.
and the non-terminals just carve out different pieces of it.
Exactly. So in other words, a term is not attached to a non-terminal. It's not even attached to a language. I could have LC prime that has other interpretations, and I could use the same term with both of them.
Okay,
Yeah.
thanks.
Again, that's part of the lightweight sort of dynamic programming sort of flavor here. Great question. Okay, so now I have defined subst. I guess I meant to hit run here. And now we do reduce to 2. Right? Make sense? Okay. That's one step. What if we had more things in here? Like what if I had lambda z, x, and let's pass the y in. What's going to happen here? Are we going to get 2 or is it going to stop? And the answer is going to stop. Apply reduction relation applies the reduction relation just once. If you want to keep going, well, use apply reduction relation star, which is keep going. And now it'll find me all the ways it could keep going. And I seem to have not kept going the way I expected. Why is that? I actually don't know. All right, well, we'll figure this out. Just to make sure we can look at traces, like.
Does it have to be Unicode lambda?
Oh yes, thank you. Yeah, it wasn't actually a lambda. For some reason, I thought it would be a good idea to make myself convert it to Unicode every time. Great catch, right? So I was going to see in the traces that it got stuck. So this is demoing another tool, but here you can see the traces go through. Thank you. All right, and there was nothing like. Yeah, because lambda was not otherwise mentioned, it counted as a variable name and so on. It was still a well-formed term. All right, we all know the trade-offs of a flexible dynamic language. It may have felt a little dumb that I wrote out substitution myself. Of course, it's so common, there is built-in support for that. Let's switch over to it. So binding forms goes in the grammar here. And then I can use substitute instead of sub. So substitute is the built-in thing that takes advantage of these binding forms. So this just says, when you have this kind of thing, which happens to fit in the grammar of term, then these x's are available in E, and so on. There's a little sub-language for binding. And so now I can use substitute. I don't need subst anymore. And we'll still get the same things that we got before, I hope. I had a double T, so substitute misspells. You guys are great at this. All right, and so you see we did get the same result. Let me try to show you just a couple of more things. Typesetting, because this is for papers, we want to typeset things. So language depict takes says typeset the grammar with non-terminal Z and V for me. And the other one's going to typeset a reduction rule. You can see it's kind of small there, right? The default fonts are set up. But we are in just Racket, and these are generating pictures. So let's just use the pict library. And now we have the scale function, so we can make it twice as big. And now you can see. Okay. Or, well, we usually generate PDF and then drop the PDFs into LaTeX. And it has the right bounding box, so it even works in line in the text. Right, as you may expect, there are various parameters to control the style of this thing, so that illustrates one of them. One thing you see is it's a bit dissatisfying that substitute is spelled out here as a meta function. That's the default typesetting of a meta function. So sometimes you want to take more control, and so here is a big pile of code. Typesetting is often like most of the code when you get ready to make the paper, because you want to tweak this. You don't want to say substitute. You want to use the standard shapes there, so I need to scale it again, but the exact details of this are not all that important, but I fixed up the dots and I fixed up substitution, so it looks on this last line the way you would expect it to look. Right. All right, so we have this whole picture library, so you have lots of flexibility in how you put things together. I think I'm running out of time, so apply reduction relation star, I showed you already. If I do more examples, then we'll discover that it doesn't know how to evaluate sub-expressions. And why would it? Because I've just said, my reduction rule here says, take exactly this shape and match it, and it doesn't say this can appear somewhere down inside. Right. So the way we do that in reduction semantics, Matthias style is with context. And so here I'm defining another thing that I would add to my grammar. I think I have time to do just this one more thing. So I'm going to add C here, and this is whole is a built-in thing to cooperate with in whole, as we'll use in the revised reduction rule. So it says a context is either a whole, or you've got some number of values in a context and then some number of expressions. And so now we have this revised rule that I will drop in place of the old one. All right, so now my old examples still work. Let's turn off the typesetting. All right, I'm still so apply reduction relation star will still give us 2, and now I can nest these, right? So I could have, let's move the application out. You know how this works. I probably don't need to go all the way through it, but here we go. We should get 10 out this time, right? No, 2, because it's throwing away the 10 and giving us a 2. All right, so you do that. Now, if you've done any of this context stuff, you know it's easy to mess this up and like put an E here instead, right? If I do this, I still get 2 out, but that's because it's confluent. So if I use traces, oh no, it's not, I don't have any ambiguity. If I get another example, there could be multiple ways of doing things. So in this one here, the second term, it turns out there are multiple ways to do it. And if I use traces, then it will show you the different paths through. Let's do that second one. So now we get, instead of just a linear list of boxes, we get a graph, and it can show you. And then you may look at this, you may run traces and say, that's not what I meant. I meant for it to always be a deterministic step. We have an example in this case, but maybe you wanted to make sure of that, so you can write a unique step property like this. And then you can use Redex check, which is like quick check for Redex, and it'll go find you terms. It'll go find a term. In this case, it'll find it right away. Find a term that is not a unique step. Yeah, so it finds this counterexample here. That is an ugly counterexample. It's not minimized. Also, it's got all of these free variables, and I meant for all the terms to be closed here, right? So what if I wanted to write, find me only closed terms? Well, now I need a judgment form to tell it what closed means. Well, this is at least one way to do it. So define judgment form, you write things that look like judgment forms. And this is saying, numbers are closed and lambda's closed as long as if I substitute away all these arguments in the body with 0, just picked arbitrarily, I get a closed term and so on. And with that closed judgment, now I can write this revised property that says, find me a closed term. Make sure that any E you pick is either not closed or it has a unique step. So this way I will get a somewhat nicer example. Actually, I won't. It will not find anything in 10,000 steps or 100,000 steps, because its random generator is too unlikely to generate a closed term. And then if it does happen to generate one, it turns out to be a unique step. So another thing I could do at the end, I want to use, the important part of this slide is Redex check satisfying closed unique step. So this is helping the random search by saying, first make sure you satisfy this judgment form. And then instead of just generating random terms, it works with the judgment forms and finds them. And then this will succeed. But to do this, I had to, it turns out that this satisfying thing doesn't know how to deal with dot, dot, dots in their full generality. So I just made a sublanguage that has subst1 only deals with one argument variables in lambdas, and closed one similarly, and then it can work and it will find I have to extend the grammar with this other part. But again, as we've seen, I can just throw in these extra non-terminals. Since this is the last thing I want to run, let's just try running. Okay. Throwing in some extra non-terminals here. My intent is that E1 and V1 are subsets of E1, E and V, and big enough subsets that I find interesting counterexamples from them. And you can see it found a nicer counterexample for me this way. It's still kind of big. We'd still like to have some minimization tools, but at least I'm not skeptical because there's free variables everywhere. Right. So that's the idea. I should mention that there's a lot of work has gone on to this random test generation to get these different tools and techniques. And these are some, at that time, students who worked with Robbie to build those tools. Xiaohong did such a great example setting us up. He even set up my other example, which is sort of multiple threads. So what would that look like in this world? You would add a pair form and so on. We don't have sort of the nice structuring that K has for making things modular and inferring generalizations for you. There are ways to write extensions. But that's all the idea. If you're interested in more, whenever you get Racket, you're forced to have Redex, you know, if you get the main distribution, so it's already there for you. You can find out more information at the Redex specific site, or there's a whole book if you want to look more at reduction semantics and how they're used inside of Redex. So, happy to take more questions. Thank you.
Okay, at the risk of sounding like a broken record, what's your story for type systems? I saw that the judgment there had quite a general inductive syntax, so can you use that for type systems?
That's what we use to write down type systems.
Okay, in that case, what works and what doesn't? Can you generate like random well-typed terms using your testing infrastructure?
Yeah, absolutely. That's the main use case, really, because you're otherwise generating random terms are unlikely to be typed, right?
Well, that was actually my next question. If you are just generating random terms, how do you make sure they're typed, or do you have some more clever kind of symbolic exploration?
So the satisfying with a type rule written with defined judgment form, that is the more clever thing, right? And that's Burke's work, his dissertation on how to do that search. And I glossed over it, but the reason these different random generations work better in some cases and worse in some cases, so you really need a mixture of these things. But if you have a type system, you definitely want that one. Yep.
Cool, thank you.
Yep.
Hi, thanks for the talk. I think the first manual version of substitution you defined was not capture avoiding, was it?
That is correct.
And the second one is that is derived.
That's right. Yeah, the automatic one was, and that is technically, if you happen to notice the weird variable names it picked, that was part of it. I'm not going to find it. But it made up, oh, it's in the other tab. It made up like X17 in weird angle brackets because it needed to do the making up names to make it capture avoiding. So in this case, I wrote down a manual one that I didn't intend to be capture avoiding. I wanted to only consider closed terms, and that's why it was important to me in the end to have the closed judgment form. Great question.
Thank you for a great talk. I have two questions. First is that does Redex support big step semantics or denotation semantics, not other than reduction-based semantics? And second is that does Redex generate verifier-friendly output such as rock or lean?
Let me answer the second question first. This is work on generating proof things. I can't comment on it much. I've only just looked at it a little bit. But for people who know what they're doing, I encourage you to look at Redex Plus or Redex to Conc here that will have more answers to that question. The first question about big step semantics, you can write them as meta functions. So we often do that. And then we get a certain amount of type setting. The tools in Redex are less good at it. The meta function either gives you an answer back or it doesn't. Maybe that puts your head in the right space for trying to write the proof. I don't know. But we'd like to have better tools for that, in fact. Yeah. And the judgment forms may be somewhere in between. You could also use that to write big step rules. And the tooling is a little bit better.
Now it's coffee break, so let's keep asking questions during the coffee break. We'll be back at 10:30. Thanks.
Thank you.
break, so we'll be starting our second section. It happens to be that two organizers are giving the talk in the same session, so I'll be chairing this session. So we have 3 talks in this session, and we first have Spectec, a single source of truth by Seokyeong. Please give her a big hands.
Hi everyone. To repeat what I said in the beginning of the first session, I'm so happy to see you all here. And some of the students from KAIST in my school told me, like, when I saw this workshop program, it was like your interest. And yes, this is a present to myself, because I was happy to see all those language mechanization work with K and Redex and verifications in Wasm and JavaScript, Ecmarkup, all those things. There are people who develop programming languages. There are people who write language specifications. There are people who use them and maintain them, the language communities and all that. And this is the workshop to get everyone in the same room and listen to their experiences and listen to their troubles and how to solve them together. So that's why we are here today. I am so excited. And this talk is about our recent work on Spectec. And actually, this was supposed to be given by Andreas. Where is his name? Yeah, Andreas here. Andreas was supposed to give this talk, but he couldn't make it. So he shared his slides on Working Group 2.16 this April. So his title was A Mechanized Language Spec in the Real World. And as you can see, it's a big project. The KAIST team, who are all here, and Philippa and Conrad, they are going to give a talk this afternoon. So we are happy to share our experience. March 27th this year, Andreas wrote this article. Spectec has been adopted. 2 weeks ago, the Wasm community group voted to adopt Spectec. For authoring future editions of the Wasm spec, in this post, he described what Spectec is, what it helps with, and why it takes Wasm to a new level of rigor and assurance that is unprecedented when it comes to language standards, right? And actually, if you go to read the meeting note, you can see that on March 11th, the community group had a poll, adopt Spectec as the toolchain for authoring the Wasm spec, and 15 strong in favor, 17 in favor, and 1 neutral. Yay, it's adopted. So what is Spectec anyway? Thank you. What is Spectec anyway? Before talking about Spectec, let me start with WebAssembly. WebAssembly, in short, Wasm. It is a binary instruction format for a stack-based virtual machine designed as a portable compilation target for programming languages. It is very well known to be well designed with formal language specification. For a language construct like binary operator, the spec describes the syntax and semantics in 2 ways. One in this natural language, step-by-step algorithmic explanation. Another in gray with our beloved Greek letters, like formal rules. Some people prefer this. JavaScript developers and Wasm developers, people in industry, they don't even look at this. They love this. And the single editor of the Wasm specification, Andreas Rosberg, he only wants to read this. And he even translated this to English phrases. So we have different kinds of people, and we'd like to help everyone. And yeah, so Wasm 1.0 was introduced in this PLDI'25 paper. It was tiny, as Matthew and the Xiaoheng showed. This operation semantics, dynamic semantics is 1 page, and static semantics is even less than 1 page. It's very tiny. And the real specification, you can see this. On the left, we have dynamic semantics. On the right, we have static semantics validation. As I said, for each instruction, it describes the semantics in 2 ways. Prose algorithmic explanation and formal LaTeX declarative style. 2 ways, both for the dynamic semantics and the static semantics. Am I moving too much? Sorry. Yeah. And in order for a new language proposal is standardized to the specification, the community group is really picky. They are asking for 4 artifacts. In order for a language proposal, a feature proposal to be standardized, they need to describe the semantics formally in LaTeX and also specify the semantics in prose using the restructured markdown and implement the semantics in a reference interpreter in OCaml. And finally, provide a test suite that can test the implementation of the feature. So all 4 things should be provided to sell your feature to the community. They do not require that yet, but they'd like to have even mechanized definitions and mechanized proof in this standardization process. So when I first heard that, I was like, is it possible? Can you do that? And actually it happened. And the language is that's really rigorous. But the thing is, because of these many steps and too much work to do, it's not that easy to make the language grow faster. So for example, let's look at this instruction select. This is one instruction in WASM. The spec has this prose description and formal semantics. And what the spec editor writes is this. Prose description is restructured markdown and formal rules in LaTeX. So after writing all that, you are going to get this beautiful spec. So WASM is large, and it has over 500 instructions in the latest, not yet released, but soon to be released WASM 3.0. And its type system is not trivial. It's growing fast, and actually it wants to grow faster if all those mechanisms help. So it has already over 20 extensions since 1.0, but still missing important features. It currently has 15 completed and more than 20 active proposals, and the community wants to standardize it as soon as possible. So fully formalizing this big and fast evolving language incurs various challenges, right? You can imagine that. The prose is a handcrafted translation of formal rules. As I said, Andreas writes the semantics in formal rules, inference rules first, and then translate that into English phrases. It's labor intensive, right? Tedious, error prone, and for some reasons, it's written in that weird looking restructured text. So that requires some tooling hacks. You can imagine that. And code reviews are painful and unreliable. Can you check the differences between LaTeX? I don't want to take a look at them, right? So spec differences for a single proposal, it's huge and not really human readable. Another thing is they really love mechanization, and Conrad has beautiful mechanization with Isabel for 1.0. And we'd like to have that for 2.0 and 3.0, but that requires a lot of work. It's really difficult to keep up with this fast evolving language. So here's our present, right? Instead of all this long specification description, what we want the editor to do is to write only these 6 lines in Spectec. Then from this 6-line description, our Spectec toolchain can generate this. Yay, it's kind of magic, right? So what is Spectec? Finally, it's a domain-specific language for defining the WASM semantics and authoring the specification. It is the single source of truth in the sense that if we write that 6 lines, then the other artifacts are going to be automatically generated. It translates, like math rendering and that natural language, and rock definitions and the others. It's easy to write, read, and much easier to see the differences. And it's easy to review with, it also has some meta-level error checking. It is not a theorem prover, just a preprocessor. So again, whenever we have this kind of talk, people ask about, how about K? How about Redex? So I loved Matthew's second slide. He sets the context of Redex, where it is good for, right? Here, our Spectec is an in-house tool for WASM, period. Okay? This Spectec is especially specialized for the WASM specification, to be clear. So we are intentionally specialized to our use case. All the specs meta notation, that's built in, but hopefully no more than that. And the backends can make domain-specific assumptions. Our tooling has, WASM-specific assumptions, and later I will show you the overall picture, but every single point has its specific assumptions. Especially the interpreter backends, it has lots of assumptions. And why? Because that really simplifies our work. We don't need to be general enough, because this is for us. We built it for us. So we control the implementation. We didn't take the risk of depending on someone else's tool. That's good for other purposes. We love K, we love Redex, and we use AUT. But for this purpose, we are making this decision. But it's still a research. A long-term maintenance is still an open problem, and we are looking into that. We are trying to make that better. So this is the overall picture. Spectec, it's the DSL. That's 6 lines, right? When you describe the semantics, as Xiaohong said, when you define a language, you'd better have a semantics, right? Like old programming languages, they started with implementations, not the semantics. Then what does it evaluate to? What's the value of this expression? Then often we heard like, let's run it. It's not the semantics, that's the implementation. So here, what we are saying is we'd better define the semantics first in this Spectec DSL. And it has many layers, like it has this, several layers. The first layer is still declarative, which is easily emit LaTeX formalization. And after several transformations, we translate this declarative description to algorithmic description. Why? Because declarative specifications are good for proving, mechanizing formalizations and things like that, but they may not be good for running or understanding the semantics in a machine-like way, how to run it in step-by-step execution. So that's why we translate this declarative style to algorithmic style. Then we can generate a meta-level interpreter. I'm not going to go into the details, and we can finally emit prose descriptions. If you remember, that was algorithmic. Number 1, do this. Number 2, do that. And this is new. This is under submission, so I'm so sad that I cannot tell you the detail, but we do have a fancy fuzzer, and we can generate cool WASM tests, and that also revealed various bugs in the implementations of WASM. So this is the prior version of the spec editing, and now one can write this. This is getting shorter, right? And another thing is that we can mix manually written part and automatically generated part. There are, you may not be able to read it, but there are some places saying splice in the automatically generated text here, encountered by, encompassed by other manually written text, meaning that we do not need to get rid of the WASM 2.0 spec and replace that with a new one. We can incrementally replace the parts with the automatically generated ones. And on the left, we have manually written WASM 2.0 spec. On the right, we have automatically generated WASM 3.0. And if you just look at that as a picture, they look similar, right? Yeah. So if you take a closer look, they're up different. But yeah, that's good because you don't need to write all that. So that's the deal that we are making with the community group and the developers. Okay, WASM features. WASM 1.0, again, announced in 2017. It has the core-based language that Comrade proved. And 2.0 in 2020. It has the vector type SIMD instructions and reference types, multiple return values. WASM 3.0 will be released this year. And it has exception handling, garbage collection, tail calls, 64-bit address space, multiple memories, and things like that. All these features are now handled by Spectec. And we are describing the semantics in Spectec for continuations and effect handlers. So it's going really well. The reason that I'm enumerating all this exception handling proposal, garbage collection proposal, they are all individual proposals. They have their own 4 kinds of artifacts, right? Prose description, formal rules, test suite, and implementation. Only testing garbage collection. Only testing exception handling. I'm going to get back to this point in a minute. Okay, by using mechanized language specifications, we could find so many bugs in JavaScript and in WASM implementations. And bugs found in spec and proposals of the WASM, like type errors like missing record fields in formal rules, semantic errors like missing index errors and missing stack operands, things like that. Prose errors like unbound variables, you're going to be amused by learning that editors often use names without defining them. Right? We do that too. And lots of editorial errors. So previously, spec editors had to check them, but now the tool can do that. And in order to see whether our tool is really useful, we collected bugs fixed in WASM 2.0 for the last 2 years and re-injected them and see whether Spectec can help finding them. And yes, it was really helpful. And the details are in our PLDI paper last year. And with WASM, this is the bit that I cannot tell you the details. We can talk about that offline. Yeah, we are available. So we have a test generator for WASM by using this Spectec. And we had the experiments with 5 major WASM engines, V8, SpiderMonkey, JavaScript Core, WASM Time, and WASMer. We found bugs in everywhere, right? And another cool thing, we knew that, but we just experienced that those implementations implement different specifications. Right? V8 and SpiderMonkey implement WASM 3.0, even though it's not yet released. JavaScript Core, it implements WASM 3.0 except multi-memory and memory 64. WASM Time implements WASM 3.0 except for exception handling. And WASMer implements only WASM 2.0. So in order to test these 5 engines, you need different specifications. You need a way to create test suite for each implementation. It's onerous if you do that manually, but we have this tool. So we only need to change the spec a bit, then the tests are going to be generated, targeted for each different implementation. So, so it's cool, but still it has many open questions, right? I was an editor of the cool language called Fortress specification. Right? It died because it was so adventurous, but the spec was so beautiful because I was the editor, right? And back then, we were not sure how much mathematical notation is good for scientists and engineers. Scientists prefer to have mathematical notation. Developers, no, I don't care. Give me the prose description. Right? Like best trade-off between what you see is what you get versus some ambiguity and complexity in the front end. In order to support mathematical notation, parser is a disaster, right? Just 2 things get together. That could be multiplication, string concatenation, function call, you name it. Right? So there are this big question. Also, Spectec does not support evaluation context yet. it, as I said, it has lots of assumptions. Whenever Andreas does something cool, new, then the interpreter breaks. And he's like, why? And we were like, oh, here's the assumption. Let's make it more general and things like that. We are going that way. And we are interested, that's kind of a learning journey, I think. We are trying to get some balance trade-off between general enough language framework and language-specific framework and what not in between. What's the best option for other language like Rust or something else? So we are now interested in meta theory for Spectec. We are also applying this technique to P4, yet another programming language, and we are realizing that Spectec is really specialized to WASM. And we have now P4 Spectec. Really? Do we want to have Rust Spectec? Maybe not. Then what do we get from these experiences? That's gonna be my keynote talk tomorrow morning. Okay, with that, I think I'm done. Yeah, and thanks for listening. Yes.
Thank you for your talk. The argument for Spectec for WASM and for not using things like K and Redex is that you want to specialize to WASM. So if you want to generalize to other languages, that's kind of circling back?
So, again, it's a spoiler, but I can tell you that every language is different, and it's too big. Every language has different purpose and different client. Different users have different taste. For JavaScript, I think ECMAScript is the best. And Jihag and Michael are going to talk about ECMAScript in a minute, and they have very different purpose. WASM has different audience. And Rust, I'd like to learn more about Rust from Ralph this afternoon. And we have different preference, like because Ralph likes pseudocode as a specification, right? So yeah, in that sense, languages are different. I mean, programming languages are different. There's C and Rust for performance. There's Haskell and OCaml for higher level description. For this mechanized language specification, I believe that we have different applications and different platforms. It's not like making up new technique for each language. There are something common beneath, and there are things different. So that's what we are trying to get. Thank you.
I guess actually just to add on to that as well, in some sense, the P4 project for Spectec is doing exactly the right thing by forking Spectec and making its own specialized Spectec variant, right? We're not trying to change Spectec so that it supports both P4 and WebAssembly at once, which I agree would put us in a difficult position with respect to this narrative.
Yeah. Philippa, get that microphone.
But at some point, we have to understand the commonalities, right? So the yeah. So that's where this discussion's going.
Yep.
Yeah.
You can say, yeah.
Very cool work. So last I knew, Spectec was still kind of encoding assumptions for handling of numerics, especially like floating point numerics. So that's kind of from WASM 1.0, but like the actual details of the numerics. Is that still the case, or is there a plan for handling numerics inside Spectec itself moving forward?
So yeah, correct.
My postdoc's done it.
Okay, cool. We should talk. Thanks.
The answer is.
Some floats still to do, but a lot is done.
Yeah. The answer is Conrad's postdoc is working on that. Okay, the last question.
Lovely talk. Lovely talk. Your enthusiasm is very infectious. Thank you. So, for a follow up on all the previous questions, how specific is Spectec to WASM? As I understand it, as someone who's not really in WASM, WASM is a stack-based language.
Mm-hmm.
So, is there anything in Spectec that binds it only to languages that are stack-based?
Yeah, thanks for the great question. So this is the overall architecture, and it starts from this single source, and WASM again wants to have both declarative description and algorithmic description. K is more like rewriting system. So they have different tastes. And here, I think that we have WASM-specific assumptions in every edge. The picture may remain similar for different programming languages. P4 may have different interest because it's more like low-level data network kind of thingy, right? And higher-level languages like JavaScript, so you know what? It's really high-level functional language. And its language specification is written in high-level functional language with continuations as first-class values. They are different. So the main thing is not JavaScript programs or WASM programs. The main thing is JavaScript language specification and WASM specification, how that is written. And with JavaScript, we didn't even dare to change the spec, but WASM, because we are all one team, we are even changing the WASM specification to be more equipped to this model. So I think that's the difference. Okay? Thank you. Thanks a lot.
So we have a little bit of spare time until lunch, so you can spare your time for your presentation. Seems like we're lagging behind like 5 minutes, but I think it's gonna be okay. And the screen seems... So for the next talk, we have Trusted JavaScript Language Environments with ESMeta by Jihyuk, and please give him a big hand.
Okay, so hello everyone, I'm Jihyuk Park from Korea University. So in this talk, I will introduce how to support the trusted JavaScript language environment with ESMeta, our tool. So JavaScript supports its own language specification called Ecmarkup 262, and it is maintained by the technical commit 39 called shortly TC39. And it describes the JavaScript syntax looks like this, BNF-like form. And it describes the semantics for each syntax feature or built-in libraries using the pseudocode style algorithms. So it consists of step-by-step execution, how to execute the language features. So it means that all the JavaScript implementations, including engines in the web browser or transpilers, including Babel or SWC, and also other the research tools, strictly conform to the semantics described in this specification. It means that if we have a new language feature, it means that the specification will be updated, and then all the implementation should follow up that new language features. And we need to check their conformance. So I'm sorry, so I think it is better to, yeah, I'm sorry. So here, we need to check their conformance, but the problem is that we need to check their conformance and we need to manually update all these specification and then implementations by hand. So actually, until before 2015, it was not a big problem because this JavaScript language has rarely updated, but since 2015, it becomes really more critical problems because TC39 decided to annually update the specification. So for every year, we have a new language feature. So all the implementation should follow up this new update to support the new language features. So many research tools suffer from this problem. So many research tools only support this ES 5.1 version because of this. They cannot follow up this new cadence of annually cadence of the update. So we believe that if we can extract some mechanized specification from the language specification, then we can automate all this process. We believe that. So this, I use this mechanized specification to explain to denote the executable and easily analyzable, but strictly just having the similar style written, the writing style of the specification. So this is our goal. So actually, this talk I will explain our journey with our framework called ESMeta. So in each step, we develop different tools, including JSet, JStar, and all these tools. But all these tools are included in our general framework called ESMeta. So I will first explain how to extract our mechanized specification from the language specification and how to utilize it in very different way. So let's start from the first part, the how to extract the mechanized specification. So I said that this specification describes the semantics in a pseudocode-like algorithm. So this algorithm describes the specific case of the array literal. So it has multiple steps, and it describes how to execute the array literal. But it has a very similar pattern because it's pseudocode. So for example, we can define local variable using the let be blah blah, or we can call another algorithm looks like this one. And also we can invoke another syntax-directed operation for some specific abstract syntax tree. So for example, actually these element list and allegion also are parameters. We can take JavaScript syntactic component or abstract syntax tree as a value, and we can call some syntax-directed operation for that ASD by passing some additional argument. So we can do it. So this specification has specific pattern. So we want to formalize or support some meta language to capture all the patterns in the specification. So we design our own meta language called IRES. So IRES stands for Intermediate Representation for Ecmarkup Specification, shortly IES. So the specification, JavaScript itself is functional, but the specification itself also functional. It supports the first-class functions or values, and also even it supports the first-class continuation. There are some specific parts support the continuation. So our meta language support their first-class functions and first-class continuation in a specific restrict form. And I explained that this is meta language for the specification. It means that we also treat the JavaScript ASDs as values, looks like this. So this is special point. So this meta language only for the JavaScript specification. And using this meta language, we developed our first tool, JSet. So it takes the language specification and automatically generates the JavaScript parse using the syntax, and then automatically compiles all the pseudocode-like algorithms into our meta language functions. So it means that it is actually interpreter. We can execute JavaScript programs using the mechanized specification. If we have meta language interpreter, then we can execute any JavaScript programs. And the core part is this one, and to support the compilation, we manually define more than 100 compilers. So for example, we can compile this single step into our meta language instruction looks like this using some specific compilers. So this is how to extract the mechanized specification from the original language specification. So now we have mechanized specification from the original specification. Now we can execute JavaScript program on our mechanized spec, or actually we can mechanically handle the semantics using our extracted mechanized spec. So our first application of that mechanized specification, we want to detect some errors in the specification by analyzing the specification. So we want to design the type analysis for specification. So this was our first application. So I will show you what happens if we perform the type analysis on the specification. So this is the semantics for built-in library math.round. So it takes any JavaScript value, so the parameter x, the type is any JavaScript value, string type, boolean type, number type, object type, and so on. But after calling the algorithm to number, it returns not only number JavaScript value, but also JavaScript exception. So JavaScript exceptions are also values in the specification, so it returns both either of one of them. But this question mark operator filters out the exception values. It means that if the return value of the two number is exception, it directly returns to the caller. So now we have a number type. So the variable, local variable n, the type is number. But let's look at the step 3 and 4. In this step, this algorithm compares the variable x with mathematical values 0.5 or 0. But it is the specification error, because in the specification, there is no meaning when comparing the non-numeric values. So for example, if we pass the Boolean value to the math.round, then this Boolean value will be passed to that parameter x. And in this algorithm tries to compare the Boolean value with the mathematic value. So there is no meaning. So this is obvious specification error. But actually, this is not an official release version because Ecmarkup 2.6.2 is maintained as an open source repository in a GitHub. So this is internal version. So at this point, in this internal version, it happens. But before releasing the actual official version, it was fixed. Looks like this, using n instead of x. Now we have the correct semantics, even when it takes Boolean values. Looks like this. So if we perform type analysis, we can detect these kinds of bugs and specification errors. So we developed a tool called JSTAR, that's type analyzer. We successfully detect 93 type errors with 59.2% precision. And among them, 15 bugs are newly detected by our tool. And after developing the first tool, we realized that we needed some more advanced type checking to reduce some false alarms, because the precision is 59%. And for example, this is ongoing work. So here, this is an example of our motivation. So let's look at this part. And first, pattern can get any JavaScript value. But here, the get algorithm requires object type. So it does not match. So it throws a type error. But actually, these two alarms are false alarms. So to remove these false alarms, we need more information during the type analysis. So here, actually, each regexp algorithm return type is normal Boolean type. But we want to infer another type constraint. If each regexp returns normal true type, then the argument pattern should be object type. If we can infer that type constraint, we can utilize this information. For example, we can propagate this information to this pattern. Oh, I think there is a problem. Sorry. So we can move to like this. So here, pattern is regext is Boolean type. But if its value is true, then we know that the pattern is always object. If we apply this part into here, then at this point, we know that the pattern is always object type. Then we can remove these false alarms. So we want to do it. So this is ongoing work. to reduce the false alarms in the type analysis for specification. So this was the first application. Now let's move on to the second application. Now we want to utilize mechanical specification to check the complements between the specification and implementation. So these two things should come from each other, but how to check it? So typically we need to use developers utilize the conformance test, and TC39 supports the official test suite called the test262. So a single conformance test is just JavaScript program, but it consists of two different parts, program part and assertion part. For example, this is an example. So it says that 4 + 2n program should draw type error according to the semantics of this specification. So the engine developers can execute this test suite to check their conformance in their implementation. But the problem is that this is manually maintained. So it means that we do not know that this covers all the semantics in the specification, or is it really conform to the semantics in the specification or not? So to resolve this problem, we want to automatically synthesize conformance tests from our mechanized specification. So we utilize the mutation-based fuzzing. So first, we construct the initial program pool using the syntax described in the specification, and then we iteratively mutate the programs that looks like this based on the specification coverage. So it is coverage guided fuzzing. So our goal is to increase the coverage in the specification. So I will show you the concrete example in the next slide. And then finally, after convergence of the spec coverage, then this tool automatically injects assertions that looks like this. But these assertions comes from the final state. So I said that this is interpreter. So if we execute these generated program on our mechanical specification, we can get expected final state for each program. Then from that expected final state, we automatically infer the assertions for each program. We can assign the assertions that looks like this. And specification coverage means that it looks like that we have a program pool. Then if we have this program, we can cover that part. If we have this one, we can cover this one. We can have this one, and we can cover this one. But actually, we think that it is not enough. Why? Because this is a single algorithm and different edge cases, but multiple different language features may sometimes share the same algorithm as a HEPA functions. For example, this algorithm, language feature addition, subtraction, and multiplication, their semantics are defined by with this same algorithm. So it is not enough. We think we need to split. We need to cover all the edge cases for each language feature looks like this. So we split the context based on the innermost language feature, addition, subtraction, multiplication, and we can cover all the edge cases for each language feature. So we call this is feature-sensitive coverage, and we extended this concept, and we can increase the diversity of the program to detect many different edge cases in the real-world implementation. So using this idea, our tool, we developed a tool named Jest, and we detected real-world engine bugs, 42 engine bugs, and 94 different transpiler bugs in the real-world implementations. So this was the second application. But after synthesizing these programs and checking the coverage of the test conference, we realized that these synthesized program or filtered test programs are really helpful to advancing the understanding of the specification. So we developed another tool, JSpec, some specification visualizer. So this visualizer consists of two different parts. For each program point, we showed what is the minimal program, synthesize the minimal program for each program point, and which test we need to run to test that program part. And then for each program, we can actually run online to step-by-step execution. Using the step-by-step execution, we can see the internal state or what happens in the state in the spec, forward or backward way. So I will briefly show you our tool. So our tool is released in the Chrome extension. If you install our Chrome extension, this is actual online version of the official language specification. After installing the Chrome extension, you can see the right side panel. And if you click each program point looks like this, then you can see the different programs, the minimum program, and which tests, statistics tests we need to run to test each program part. Looks like this. And if you click the run on double debugger, looks like this. This is the online version double debugger. And this is the synthesized program. And if you click the resume button, looks like this, then it directly jumps into the we interested part. Then you can see what happens in the specification, what happens in the JavaScript, and you can go forward or backward. For example, back over, or step. Looks like this. You can do it in front, forward, or backward. You can do step-by-step execution. Yeah, so this is another tool to advancing the understanding of the specification. And the last application is about the derivation of the implementation. So we want to not only checking the complements between already existing implementation with the specification, but we also derive implementation directly from the mechanism specification. So our first target was static analyzer. Then how to do it? So we have the spec, and we want to analyze this program. How to do it? So after applying our approach, we can automatically extract the mechanism specification looks like this. And then I said that this is the JavaScript interpreter written in our meta language. Then if we have meta language analyzer, then we can analyze this mechanism specification, and we get the analysis result of the specification. But in other words, we can say that that analysis result just includes all the possible behaviors of the interpreter. But if we restrict the initial state based on this program, then that analysis result includes all the possible behaviors of the interpreter when it takes this program P1. It means that this analysis result represents all the possible behaviors of P1. So this is the concept of meta-level static analysis using the definition of interpreter and the given program. So using this, I will skip the details, but so this is the result. After deriving the JavaScript static analyzer from the latest spec, so our empirical study shows we can derive always sound analyzer for it covers all the modern features of the JavaScript, but manually written, maintained JavaScript analyzer cannot soundly support the modern language features here. But actually, this is not practical because we need to perform meta-level static analysis for all the parts. We build all the JavaScript static analyzer from the scratch, but I think it is not the ultimate goal. So the appropriate way to use this one, it is better to automatically derive some specific part, not yet covered part for existing analyzer. So we want to derive the subspecific part, the specific component of the static analyzer, or we also want to derive this transpilation rule or data flow rules from this mechanism specification by analyzing them. This is our next goal to support to derive other language implementations. So I explained how to extract the mechanism specification and how to use it. If you're interested in our tool, so please visit this GitHub link. So it is the open source. And so that's all for this talk, and thank you for listening.
So the JavaScript specification has like occurrences of implementation defined behavior and it permits like implementation approximations for certain mathematical operations. How does that affect like your analysis and your test generation and stuff?
Yeah, so we realized that the JavaScript specification has implementation of host-defined features, but we assume that at this point we assume we implement it in a single specific implementation. We assume that deterministic version of our implementation for that implementation version, dependent or host-defined semantics, but we want to support the implementation dependent or host-defined semantics in the future, but not yet. So at this point, we only implement in a specific way for that all the features. Yeah, that's all. Thank you.
Hi, thanks for the talk. There was some really cool demos. So I was wondering about this. You showed this where you clicked on the clause in the specification and it showed the test cases.
Yeah.
How does that work? Do you have like annotations in the tests, or does it like automatically find this? Like how is this linking done?
So actually, this is pre-calculated annotation. So before releasing our tool, so we already execute all the tests, and then there is annotation. So this test covers this part. This test covers this part. So we filter based on that annotations. So yeah.
Okay, so it's automatically computed, not manually annotated.
Not offline annotation.
Right, but automatic.
Yeah.
Okay, cool, thanks.
I have a question about JSTAR. Since that you are writing a type checker to find the error in the spec, and I want to ask that if you want to generalize your approach for different language, do you have to implement different type checkers? Actually, it's two questions. There are two questions. First one is that can your approach be generalized to different language? And second question is that do we have to write different type checker for different language?
Yeah, I think the two questions are really similar. I think So this type checker only for JavaScript language specification. I think for different language specification, I believe that it is better to design different type checker for different language specification because they have different style and different problems and different checking requirements to check to detect some bugs in the specification. So yeah, I think this JSTAR only for the JavaScript language specification.
Oh, it is very impressive that how you cover whole ecosystem of spec definition and implementation, not just focusing on specific topic. And my question is, can we see the JSTAR statistics slide?
JSTAR.
About 14 bucks.
Oh, about 14 bucks. Okay, about. You mean this one?
Yeah. I wonder what was happening in 2015, September 22.
So, okay, so actually I said that the ES6 version is released as the started from the annual release. So actually ES6 in this is a really big change. So actually also the specification style was really big changed from the ES6 since 2015. So we cannot cover the old version. We cannot cover legacy versions of the specification. So only covers the at this point. So this is start of the new style of the specification. At the first time it has the that kinds of bugs. Yeah.
So the bug was not by one criminal or
one criminal, not one criminal. So it is just started from the initial version of the new style of the specification. But these are not critical. But yeah.
So thank you for the great questions, and let's give him a big hand.
Okay. Thank you.
질문이다. 2015년에 무슨 일 있었는지 너무 웃긴다. 한 번도 그런 생각 안 했어요. 처음으로 커뮤니티 그룹에서 오신 분이라고 소개해줘. 발표 스피커. 출제해 봅시다. 대문. JavaScript.
I think we're good. Can we switch it over to C? Okay. I did that blindly.
So it's the last session, last talk before lunch. So this software supporting the JavaScript language specification, and he's the first speaker of this workshop coming from a language community, not from academia. So I hope it captures your interest, and let's give him a big hand.
Thank you. Yeah, I'm Michael. I work at F5, and I'm one of the editors of the JavaScript specification. And Jiak did a really good job of priming you for this, so my first few slides might actually not be necessary. So JavaScript, yeah, it was originally designed for use on the web at Netscape, but now it's available on a huge variety of platforms. It's still obviously used in modern web browsers, but it's also used in standalone runtimes, which are hugely popular, and also embedded in HTTP servers. It's used in operating system shells, microcontrollers, all sorts of places. So because of that hugely diverse set of stakeholders that JavaScript has, JavaScript is now developed within ECMA. It's an international standards body. It's composed of experts, practitioners, implementers from all over, from industry, from academia, government, research institutions, and they all send representatives from all over the world to work on JavaScript. As you know now, the spec is called ECMA 262. ECMA just publishes a bunch of numbered specs, and we got the number 262. And it's authored using English prose. So it's partitioned into these abstract operations, which are a function-like specification mechanism. We try to use highly regular phrasing, making it effectively a pseudo-programming language. On the rigor spectrum, it's somewhere in the middle, probably for this audience, not very high, but we think it's the appropriate trade-off for our readers. So we have to consider that we have a lot of different kinds of readers. We have implementers, of course, but we also have the JavaScript programmers themselves, both like really novice ones and veteran programmers. We have educators in the community, people who write documentation, academics, of course, as well, and tooling that consumes the spec, as we saw with ES Meta. So we think this is the appropriate kind of abstraction to use. It's shown over the years to be sufficient. Between the specification and the official conformance test, there's very rarely a new feature that results in an engine divergence. So that's all we need. That's the bar we're trying to meet. So in the old days, we used to do this. We had a single editor that used Microsoft Word and this track changes feature, and would periodically send out updates to review, and all spec work would go through that one person. This is really not sustainable. We did manage to release 6 specification documents using that process, but because of the ever-increasing size of the specification, as you can see there on the page numbers, the scope of the language, and the rate of additions that we wanted to make to the language, this is just this couldn't remain this way. There is a really good paper by Alan Worthbach and Brendan Ike that was presented at HOPL 4. I recommend reading it if you want to know more about the history. But moving forward, since 2015, we have a new process that is more decentralized and allows us to scale. I don't think that's rendering very well. But anyway, so with this new process, we also now have editor groups. So there's more than one person working as editor.
and I've been part of that editor group since 2020. The biggest other change in our process, though, is that proposals are now shepherded through this 6-stage, these 6 stages of proposal. Yes, I see that some of you are noticing there's 2.7 up there. Don't worry about it. So the committee members themselves move it through this process, and the ones doing that are called champions. And during stages 1 and 2, they write their own spec text. This distributes that editorial work significantly. So this is how we're able to sustain our progress. So as we transitioned away from centralized editing, we also transitioned away from emailing around a Microsoft Word document. But there actually weren't too many options for what spec medium to use. There's really only these 5 that we identified. There's plain text, that's like what's used by IETF for their RFCs. There's what we were doing with a rich text document. There's like desktop publishing software that we could use to really carefully lay out something like an ebook. And of course, you can use like LaTeX or FrameMaker for generating PDFs. But we went with web technology. We think that web technology is clearly superior to these. So web technologies are all free and open technologies, meaning like there's already extensive developer tooling available and libraries. The proposal authors already likely have experience with these web technologies. And everybody already has a web browser, so there's nothing to install, there's no software to go pay for. And all the web technologies are based on text formats, so that's really good for collaboration. Again, the main goal of this is like being able to collaborate among members of the committee, and we can use like line-based version control systems to version control it, like just things that we're familiar with, like using Git. And of course, the web is an incredibly powerful platform. It has like all kinds of advanced interactivity that we can add. I'll show you some examples of that in a little bit, which should again further justify it. And it also has like end user extensibility through browser extensions, which Jiak showed with ES Meta using that. It's also very important for us as a web spec to be able to integrate with other web specs. There's lots of interdependencies between web specs, so we need to be able to like deep link into specific terms or specific abstract operations. So it's really good for all those reasons. So since 2015, this is what our specification looks like. It's a web application. I want to show you some of the interactivity. So like really simply, you can do things just like hovering over some defined term and clicking the references, and you get all the references to that term throughout the document. And you can do this not just for terms, you can do it for clauses, abstract operations themselves, non-terminals of the grammar, tables. So we use that kind of stuff all the time. When reading algorithms, it's really nice to be able to just like click on aliases to see all the instances of an alias throughout the algorithm. And when you do that multiple times, you can get multiple different colors, and that helps you follow things and kind of like track liveness of aliases through each algorithm. We also have this very useful feature to toggle on these annotations for where arbitrary user code can run. This is very helpful for implementers. It was requested and implemented by implementers, actually. So when it can show you places where you need to recheck your assumptions. If like arbitrary user code has run, your assumptions may no longer hold across that step. When reading the specification, we noticed that we jump around a lot between different abstract operations. A simple feature we have is pinning, so we can easily jump back and forth between different sections. There's keyboard shortcuts for it and stuff. And as an example of like some of the like really more powerful features of the web, we implement custom control over what goes on the clipboard. So some implementers like to like literally copy and paste the algorithm directly into their source code, and we can copy text that will be more appropriate for a text-based medium. So like these are, again, this is a small thing, but this is an example of what I mean when I say that the web is a really powerful platform. If there's something you want to do, you basically can do it, and we're not reliant on some proprietary technology or anything like that. So I want to cover the tools that we use to actually create all of this. The main high-level spec generation tool is called Ecmarkup. This is a tool that is maintained by the editor group. So if you see on the right, we have the document source. It is an HTML document with some custom EMU dash whatever tags. And on the left, you see that same section as it's rendered in the browser. Ecmarkup uses a library called JSDOM to work with the document as if it was a live web page, which means that it's defined using like a lot of like really high-level transforms. It's kind of easy to read and easy to work with. So like some of its responsibilities are generating a table of contents, finding all those links and references, and like finding all the terms and linking the references like we showed earlier. It enforces a ton of our editorial conventions, consistency in phrasing, our formatting conventions, that kind of stuff, which hopefully is helping tools like we saw with ESMeta, with how it's consuming things programmatically. Checks that aliases are declared and used appropriately. It embeds all the sub-resources like fonts and images and styles into the document. Does all the like clause numbering and step numbering and make sure all those references have appropriate numbers. And does some limited form of type checking, not to the extent that ESMeta does, but it does simple things like checking that exceptions are handled where they're supposed to be handled, so that like abstract operations are invoked with the correct number of parameters, that when you like return constants, that's the kind of thing that was expected to be returned from that abstract operation, that kind of stuff, but not like tracking aliases across steps or doing like the refinement stuff that's being done by ESMeta. It also processes this DSL in the headers for defining the like type signature and stuff like that, and that's where it gets that information to do that type checking. Ecmarkup relies on a library called Ecmarkdown. There's a lot of these. The Ecmarkdown processes algorithm steps themselves. So it uses this like markdown-like notation to annotate the different components of a step. So like aliases are surrounded by underscores. The grammar non-terminals are surrounded by like vertical bars, that kind of stuff. Gram Markdown is a similar tool, but this does like annotation for the grammar description. So you can see that this abstract operation is defined piecewise over two different grammar productions, and each of those grammar productions is listed there, and Gram Markdown is the one that is processing those. So yeah, I was gonna do like a whole thing on ESMeta, but I think it'd be a little bit redundant after the last talk. But I'll quickly go over it. ESMeta is maintained by the Programming Language Research Group at KAIST, and GIOC. No, not at KAIST anymore. Generates this mechanized specification, and then from that generates all kinds of tools. The way that we use ESMeta as editors is that we type check the spec using the type checker in CI. So we do, ESMeta does have some parts that it doesn't cover. I think like the module system and like atomics are some of the things it doesn't cover. But that's okay. It doesn't have to handle everything to be useful. And we also, during the integration, we made sure that it has a way to add exceptions for things, for areas that it would report a false error. So we have that ability there, and that means that even as we kind of change the way that we specify JavaScript, if we do it in a way that is incompatible with ESMeta, we don't have to be blocked on each other. We can continue our work, add the exceptions, and later when ESMeta updates to support whatever weird thing we're doing, we can remove that exception. So it's a really good process for us. We find it extremely helpful, and now they can't report any more bugs found by ESMeta because they're found before the PR even lands. So they won't even know anymore. We also use ASPL in a kind of novel way that I wanted to show off. So we use ASPL to check for like newly introduced spelling errors, but we can't just like use a standard dictionary as like you're probably familiar with using it on your own things, because we use like a lot of terms of art, right? And we also don't want to maintain a dictionary of our own terms of art. So what we do is we derive a dictionary from the like target branch by taking all of the existing terms and even like aliases and like splitting up camel case and Pascal case and then using that as a base dictionary, and then we just find newly introduced spelling errors. So you can see like an example of it, just like enumerating all the things that it found that it thinks that it would have thought are spelling errors, and it makes an exception for those. So we also do have to, like I've been talking up all of the web technologies we use, you know, and we're very proud of our specification being a web application, but we do actually have to generate a PDF. ECMA requires that we release a yearly PDF. The ECMA will actually print and ship you a book if you request it. So I have one from years ago, just for the novelty of it. I've never looked at it, but it's fun to have on the shelf. But PDFs have requirements that web pages don't, right? They have page numbers in the table of contents. If you split a table across pages, you have to like repeat headers and repeat captions and stuff like that. The pages don't exist on the web, so there's a whole bunch of things that you have to consider, and there's actually like so many things. So many things. It's really hard work, but there is good news that there is a web standard for this for paginated media. And it can be used to generate like really high quality PDFs. The bad news is that no browser supports this standard. I don't know how we can call it a standard. This is the thing W3C does. W3C publishes these aspirational standards with no implementations. Fortunately, there is a proprietary product called Prince that has implemented it since, and still no browsers support it. But we only generate PDF once a year. So we don't need everybody to be able to generate a PDF. So for now, we can use this commercial implementation. But it would be nice if we could just do it more than once a year, and anybody could do it without running this very expensive piece of software. So yeah, I wanted to go over some additional that's what we are doing. But I see like there's a long road ahead of us for like things we could do, and I just want to take this opportunity, given the audience, to go over some of those ideas I have. So this is what a proposal document looks like today. It just copies out snippets of the spec, and it adds these like insert and delete tags around certain spans to like say this is the change I want to make. It's not great doing that. It also, you know, there's limited tooling support. Wherever there is tooling support, it's been like manually added, and that is unfortunate to maintain. There's also like no way to just see the final state. I want to see what the document looks like with this all integrated and all the changes having been made. When you like click on links, like the links do work properly. They'll go to the like full spec document, but then you're in the spec document, and it's hard to know like when you navigate back to this abstract operation whether like you're looking at the changed one or not. Like you can forget the proposal changed that thing. So jumping between those documents is also really annoying to have to do, and like you have to like manually keep track of like the numbering, the step numbering. So if we change like the specification, since your proposal was made, you have to like realign those numbers. This is like a really bad process. Don't get me wrong, like it works, and we're able to get a lot done, but I think it could be a lot better. So I've for a long time now wanted, I mean this is 2017, this post, I wanted some sort of like semantic diff calculus where the spec authors can write their proposal in terms of like these semantic change operations, and then all the tooling can just like support those changes. So it wouldn't be just like text replacements, it'd be these like limited set of semantic changes you can make. There is a tool from a Mozilla engineer that goes kind of halfway here. If you have created a pull request against the spec, it can kind of create something that looks like that proposal document that we saw before. But keeping a pull request up to date is more challenging than being able to, because as it changes, you have to keep. It's very much like making these line-based changes rather than these like semantic changes. But it does get many of the same benefits I'm looking for. But I think it'd be great for somebody to explore that. Mikael, who is here in attendance actually, from Bergen, is working on this collaborative language design workbench. It's different than like a typical language workbench in that it also wants to like incorporate all the social aspects and like the process aspects of language design into it. I think this is like really cool. The goal of this is to like better evaluate the effects of the proposals on the language, because the committee has like a really hard time doing that sometimes. As an example, one of the committee members, a proposal author for the record and tuple proposal, made this tool that helps you evaluate the consequences of all these decision points for the record and tuple proposal. So you can go through and select what you think like an appropriate decision for like the semantics of this expression should be, and then it tells you why that's a bad idea. Right? Because like, for this proposal, there's no right option, right? Like every single thing you choose, it's like, this is a bad idea because of this, right? Every single thing. That's the constraints we have to work with sometimes. But like that kind of thing is very helpful for the committee to try to make decisions. Otherwise, we just keep going back and forth, around and around in circles, because everybody always has a rebuttal for every single possible thing we can do, right? And so yes, they're all bad. We need to choose one. Or none, right? As we've done with this proposal is now pretty much not moving forward. I mean, that's you didn't hear it from me. So another thing I want to explore more is, this is a tool that another proposal author or just committee member, Nicolo, made. This when you encode in a like module graph into this tool, it shows you what the internal states of the various like spec internals would look like, and this would be really helpful, I think, for implementers to just be able to use like embedded within the document. I'd love to see all kinds of these like interactive tools within the spec document, so that you don't have to just like run through it in your head or on like a piece of paper, or using your implementation. You can actually have these tools which have been like possibly auto-derived from the specification, and they would be able to guide you in your implementation and guide you in creating test cases and all those kinds of things. We also have we maintain this whole list of editorial conventions. I think there's probably something we could do to express them like more formally somehow. We just this is just like notes to ourselves, but I think that there's probably something we can do. If we express them more formally, we can probably then enforce them automatically better. Because right now, as I said before, Ecmarkup has like some enforcement of some of these, but it's like a bunch of regexes that it runs on stuff, and that's not great. And I would love to see what somebody could do with editorial conventions and that space. If this kind of stuff interests you, there is a group like a subgroup of the committee that meets regularly. I think monthly. You can talk to me or Mikael. It's free for anybody to participate. You can just we can talk about these things more often. And that's it. Thanks for listening. Oh yeah, questions. I'm happy to take questions if we have time.
Thanks for a good talk. So you mentioned about the annotation about the user code UC tag in the specification. So is it manually maintained or do you automatically infer some?
Partially. There are like manually maintained, like manual annotations in the spec, but then there's also like automatic propagation.
Propagation.
Yes.
So at the first, you annotate some points, then it automatically propagates that you see text into another part.
Because there's only a couple of like places where it actually bottoms out where the actual user code happens, but we want like any places where that propagates to be to receive those annotations. Yeah.
Okay. Thank you.
I have one question. So about the language maintenance, it seems like a very hard and labor-intensive work, even with all the tooling support. So but it's at the same time, it's hard to estimate how much work do we need to keep up the language standards. So I'm curious, how many kind of feature proposals are there, and how many do survive until, say, stage 2.7?
So that's a really good question. Yeah. So a lot of that, it is a lot of work to maintain the language and maintain these proposals. That is why we distributed this work to the champions, right? We want everyone to write their own spec text. Mika actually has some research recently on tracking proposals, active proposals, and how far they advance, and like relationships between that and the like category of proposal it is. I off the top of my head, I don't know. There is a if you go to github.com/tc39/proposals, there is a list of all the active proposals. Some of them will not be so active, but it'll give you an idea of roughly how many in each stage. It's broken down by stage, on the order of 100 to 200, I guess. That's about how many. Yeah, Carmen?
How often do you manage to successfully have conversations within companies about putting engineer time towards these tools versus kind of hoping volunteers show up and then enough volunteers show up that it kind of keeps going?
It's almost all volunteer, passion driven. Very rarely are like the tools like I showed supported by like company time. A lot of the participation within committee is supported by company time, and the work on the proposals. So when those tools are directly related to proposals, like an individual proposal, that ends up, so like Ashley's tool for deciding record and tuple, for like evaluating the consequences of record and tuple decision points, that was almost certainly sponsored by his work because it's directly related to his proposal. But for things like Nico's tool that would be like integrated into the spec document, no, we don't really see any. Like I hardly can get time to work on Ecmarkup to improve the spec,
Yeah, this has been my experience engaging with people in the WebAssembly standards body as well. But I was just impressed by so many tools you had, so I wondered if you had a better story than us.
Just more passion.
We'll talk in the break.
And what's going on with F5? Because there's the JavaScript standardization story inside F5, but there's also the WebAssembly story inside F5. So is F5 actually sort of really quite supportive in your endeavor to do this, or there just happens to be a bunch of enthusiasts that randomly have ended up there?
Both, there's a bunch of passionate people for both JavaScript and for WebAssembly within F5. F5 is very supportive of me contributing my time to both the JavaScript standardization and WebAssembly standardization. So I participate in both. I'm only editor for TC39 for JavaScript, but we are very committed to advancing the standards, and not just for our own interests. We also feel that just doing things that generally benefit the community also help us in that it reflects our image there. So we're not very selfish in our contributions. A lot of the proposals I've been working on have not had an immediate need within the company internally. We just know that they're some of the most demanded ones from the community, and that would be a great way for us to contribute.
So I had a related question. Like, you've been one of the spec editors for like 5 years. So how's it, and how long do you think you're gonna work on that? And what do you want? You already mentioned that, but what do you want from the academia or all these people working on the spec and mechanization?
So yeah, thank you for that question. So I originally, as most people do, I guess, I wanted to become editor because I was frustrated with the state of things, and I said I can do this better, right? I think things are really good now, so I don't think I need to be editor for much longer. I would love to do a whole presentation on like some of our editorial accomplishments. That's actually one of the original things I wanted this talk to be about, because I think they're pretty good improvements, and I'd love to explain why. But I feel really happy with the editorial accomplishments we've had as this group in those 5 years, and we've also done that like documentation of our editorial conventions. So I feel good that whoever we pass it off to would understand like why things are the way they are and how to continue making them, continue being consistent to those values. So at any time, I may no longer be editor. It would be great to get that amount of time back. As far as like what I would want from this community, I mean, I don't think I needed to request. The yes meta stuff came to us, and I'm super happy that that's happening. So continue with these like great ideas for like tools, and I am happy to be your advocate within and be this liaison. Just like reach out.
So thank you for the great talk, and let's give him a big hand. And we'll be resuming our session at 2:05 after lunch. Have a nice lunch.
Can you just
Hi, Nate. Can you hear us? Hello, Nate. Can you hear us? Okay, we cannot hear him. Try again.
Testing.
Cool.
Any
All right.
luck?
Can you test again?
Yeah, is my audio good?
Oh, wow. Okay, great.
I have a bit of an echo. I don't know if it's possible to mute on your side, or I can try to ignore the sound.
Okay. Hi, Nate. I'm going to introduce you and then mute myself. And if we have questions, I'm going to moderate. Okay? All set? Thank you. Hi, everyone. Let's start the afternoon session. We have Nate Foster as the first speaker. He's in Switzerland for now, and he's going to come to Korea like tomorrow, I guess. And meanwhile, we are going to welcome him remotely. Could you please give him big hands and he can start.
Great. Yeah, sorry that I can't be there, but I will be at PLDI starting tomorrow. I want to tell you about some work that we've been doing on using real-world programming languages specification to reduce the cost of formally verifying some systems. And this is joint work with collaborators at EPFL and ETH Zurich, led by an exceptional PhD student, Charlie Cast. So we've been interested in building and verifying hypervisors, which are really the foundation of many modern systems. They make it possible to virtualize physical resources and share them amongst multiple applications or even different tenants who don't trust each other. And because of where they sit in the system architecture at the very lowest layer, it's really important that they be correct, because a bug in a hypervisor can really subvert a guarantee that you might have proved higher up the stack in the application, in the compiler, and even in the OS. So Charlie and others have been building a new hypervisor called Morales, which the talk is not about. But just to give you a little taste, it's a hypervisor that, like others, allows you to run multiple VMs or applications on the same machine. But it also virtualizes the firmware. And this is nice because it reduces the trusted computing base, because the firmware is a whole bunch of code that normally runs with raw access to the machine. So like any complex piece of software, hypervisors are hard to build. And it's not that hypervisors are this kind of deeply mysterious thing. They're basically a kind of interpreter. But the main difficulty lies that they have to deal with the full scale and complexity of modern hardware. And if you look at the lengths of the specifications for ISAs, they often run to hundreds or even thousands or tens of thousands of pages. So they're pretty complicated. Distilling it down to its essence, what would it mean to verify a hypervisor? What kind of properties would we want? We'll get into more formal definitions in a little bit, but at a high level, there's basically two key responsibilities that a hypervisor has. It has to somehow emulate the hardware, so it allows the VMs and apps to execute against a virtual interface that then gets emulated against the actual physical hardware. But it also has to configure the hardware. So there's all kinds of state that's involved in things like memory protection, sometimes clearing out state when you switch from one application to another, and so on. And so all of this is done through certain instructions that manipulate that state. And doing that configuration correctly is pretty subtle. So we'd like to verify these hypervisors. It's hard because of the complexity, but it's also hard because, if you think about doing this just from scratch in some kind of tool, you'd have to do a lot of work. You'd have to write a spec, and not just for the hypervisor, but probably for the instruction set. And then you'd have to somehow do a proof. And if you were doing this in the context of an ongoing development, you'd have, of course, to maintain that proof. So the question we asked in this work is, how far could we get being as lazy as possible? So could we really automate most of the work involved with verifying these core correctness properties for a hypervisor? And in particular, can we mostly skip writing the spec and even the proof? And the answer is yes, we can. And it's based on two key observations. First is that while hypervisors are complex largely due to the scale and complexity of these instruction sets, they have a lot of structure. They're basically a kind of interpreter that repeatedly fetches or dispatches on the next instruction and then decides what to do, whether just to emulate that instruction, execute it natively, or possibly do some configuration of the hardware. And so we can harness this structure in our tool. We're not, even though hypervisors might be tens of thousands of lines of code, the verification can be broken down into these smaller chunks, making sure that each instruction is correct. And second, although again, most of the complexity comes from the hardware, we can leverage all the great work that's been going on in this community. And in particular, Peter's group at Cambridge has been developing this system called SAIL, which is a DSL for writing down specifications of instruction sets. And the SAIL community by now maintains specs for several real-world ISAs, in particular RISC-V and ARM. And so we can leverage all this great work to let us basically start from a specification of the hardware that Peter and the community have built, and that greatly reduces the load for our work. Okay, so I don't have a whole lot of time, but I want to just kind of take you through a tour of the system that we built and a little bit of the insights. So I'll start by reviewing some sort of classic ideas in hypervisor correctness. Then we'll go into some of the details of how this plays out in a hypervisor like Morales, so how we emulate instructions and how we execute instructions faithfully. And then I'll close with kind of a case study of some of the experiences we had applying this to Morales and some of the bugs we found. Okay, so I gave you kind of informal definitions, but let's get a little more precise. So what do we mean by hypervisor correctness? Well, let me tell you a little more about the architecture. So the hypervisor, we call it colorfully the hardware burger. I guess it's kind of a vegan burger because it just has these two buns that you see in yellow and some kind of lettuce in the middle. But essentially, you have this piece of software that sits between a virtual interface to hardware, and it's important that this be a hardware interface because your virtual machines want to pretend that they're running against a real machine. And then at the lower layer, of course, you have the physical or host hardware interface, which is the one that's natively supported by the ISA. It's a little more complicated than that because, as I mentioned, there's in many of the instructions, their semantics depends on some state, which is not state that we tend to think about most of the time as programmers, but it's very important at the low levels of the system. And I'm just going to call these configs. So these configs, again, do things like configure the memory protection, certain registers or other state that controls memory protection, and other features. And here, the configuration is going to live both in some cases at the virtual level and, of course, at the physical level, which I'll call the platform config. So what do we mean for hypervisor to be correct? Well, basically, we'd like it to be the case that if we take this hardware burger and then on top of it, we decide to run, say, a virtual machine, that this should be equivalent to running on some kind of reference machine where there's no hypervisor, there's no virtual interface, and we just run the VM natively. So formally, we'd like the VM to be a simulation of some reference machine. And this idea of simulation, which is very familiar in our community, was actually used in a classic paper in the operating systems community by Popek and Goldberg. And they were interested in formalizing conditions under which an instruction set could be virtualizable in the mid-70s. But we can also take their design as giving us basically a roadmap for doing formal verification of hypervisors. At the time, they were working in the 70s when it actually wasn't the case that every hardware architecture was virtualizable. So sometimes there were instructions that essentially, you couldn't expose to the VM because they would do things that you couldn't intercede and correctly emulate. But mostly due to the influence of this paper, most modern architectures are virtualizable. And as a result, you can build hypervisors that use a strategy that's often known as trap and emulate. And the basic idea is that we're going to split the instructions in the ISA into two categories. There's going to be unprivileged instructions, and these are going to be the ones that are going to be safe to execute basically directly on hardware. And in fact, we'll want to do that because this is the difference between the OS and the PL community. While from a sort of functional correctness perspective, it doesn't really matter if we emulate an instruction by doing something behind the scenes or allowing it to execute directly. But if you're in an operating system, you care about speed. And so in the original Popek and Goldberg formulation, they wanted to have certain instructions that actually just do run natively on hardware. And they wanted to identify when it's safe to do that. So those will be the unprivileged instructions. The privileged instructions are the ones where it would not be safe to let them run natively. And so instead, we're going to have them trap, and then the hypervisor will be able to intervene and do whatever it has to do to ensure that the whole system continues to execute correctly. Okay, so sorry, I missed one slide. So in the unprivileged instructions, we get a very simple picture where the host and reference machine are basically doing the same thing. Whereas with the privileged instructions, the host machine, which is what I'll call the whole complex of the virtual interface, the VM running on top, the hypervisor, and the host machine, it may take many steps as the hypervisor configures the underlying host machine to do its work. Okay, and of course we want these things to be in some kind of simulation relation, even when the host machine has done this more complicated sequence of steps. Okay, so we call these two categories of instructions and their correctness properties faithful emulation and faithful execution. So I'll do them in the reverse order as what I just described. So for faithful emulation, we want it to be the case that the hypervisor can accurately emulate the privileged instructions, just capturing the picture I already showed you. So the reference machine takes a single step, and then on the host machine, that privileged instruction is eventually emulated. But in the middle, we may take several steps, including manipulating some of this state that I've referenced several times. Here's another way to see it. For all states of the system, that's the S you see here. And for all privileged instruction, that's the I you see in purple on the top. If we're running the two systems, on the left you see, say, the version with the hypervisor. On the right you see the reference machine, which here is just, say, RISC-V. We'd like the hypervisor to, when both of these executions have terminated for this instruction, we'd like them to end up in an equivalent state. Okay, and then faithful execution is just the other picture, where for the unprivileged instructions, it's just directly executing. And again, we'd like that to be indistinguishable or also equivalent with the simulation of the reference machine. This seems kind of totally straightforward, but I just want to remind you that it's a little bit more subtle because the behavior of many instructions will depend on this privileged state. And I've referenced this several times, so I'm going to drill down and show you a little more detail how that works. So this privileged state exists at both layers. So we have privileged state that's at the virtual level, we have privileged state that's at the host level. Again, we want it to be the case that as the hypervisor is configuring and managing this privileged state for the host system, somehow this whole picture still gives us a simulation. So to trace this through, here we have, again, in the middle, we have our initial state, we have the unprivileged instruction, and the hypervisor up here will have configured the host state. This is for the underlying host hardware, and it also has access to the privileged state for the virtual machine up here. And we want it to be the case that no matter which of these two paths you followed, so here is the reference machine where we just have the virtual program running on just a regular, in a regular RISC-V context with this privileged state, the final state that it produces, again, should be equivalent to what happens where the hypervisor is actually configuring the host state, possibly taking several steps, and then running that through the host machine. Okay, so that's a little bit about hypervisor correctness and how these conditions kind of get translated to a realistic stack. With the few minutes I have remaining, I want to tell you a little bit about our experiences building verification for Morales. So I already showed you a small version of this picture, but Morales is a new hypervisor being built by Charlie and others at EPFL. And it has much of the same structure as classic hypervisors. So it sits at the lowest, or the highest level, rather, of privilege, called M mode for RISC-V. This is machine mode. And then it allows you to run different pieces of software at less privileged modes. So the OS running at S mode and the applications running at U mode. And again, I'm not going to focus on this talk, but one of Charlie's interests and others is to be able to actually virtualize the firmware, which is a bunch of code that runs on any system. And they've actually created a new mode for firmware that they can boot real systems running Linux on RISC-V with the firmware all being virtualized. So Morales is a big system. Charlie and others have been working on it for several years. And they've experienced a number of pain points in development. They have to emulate over 80 privileged registers. They have to deal with complex conditions involving interrupts, and they really want to ensure that there's strong properties like memory isolation. So during execution, during development, as usual with writing low-level software, they were building the system, they were trying to get things to run, fixing tests. This was quite painful. And in this project, we were actually able to verify the core logic of all three of these pieces of Morales using this lightweight technique. So how did we do this? Well, again, the key insight is that we leverage the work on Sail. So Morales is written in Rust. Sail provides these specifications for RISC-V. And Charlie wrote a simple Sail to Rust backend that generates Rust RISC-V model. So now we have our hypervisor written in Rust, and we have essentially the reference semantics for the ISA that we can also just run in Rust or analyze in Rust. And then using the Connie verifier, we're able to now apply this to our conditions, which come from this classic Popek and Goldberg work, and these Rust artifacts to check that they have the properties we want. So let me show you what this looks like. This is a piece of code taken directly from the Morales code base, completely unmodified. And it's an example of how we would verify a single instruction. In this case, it's the mret instruction, which returns to either S or U mode from M mode. M mode is the machine mode, which is the lowest, the highest level of privilege at the lowest level, and we're going back up. And so just stepping you through this, essentially the first line here creates what we call a symbolic context. This encodes an arbitrary CPU state where all of the registers have, well, they have arbitrary values, they have to satisfy some validity conditions, and we also have the instruction that we're interested in analyzing here. And then on the next two lines, we have basically the two executions that we want to relate. So we have the Morales execution. We just call out to here the Morales, and we pass the appropriate state and context for Morales. And then down here, we have the corresponding Sail code, where we just directly execute that code. Sorry, don't directly execute, emulate that code. And after doing this, we now have the two states that you see here on the picture. And then we essentially want to check that these things are equivalent. There's a small subtlety, which is that Morales and Sail use slightly different data structures to represent the CPU state. So there's a little conversion function, Sail to Morales, that maps the Sail state back into the Morales representation, and then we can check that these things are equal. Okay, so this is basically the amount of specification that we have to do. We have to do this for each instruction, but it's pretty boilerplate. And in fact, we have a version where you can do this for a symbolic instruction. And the main trade-off there is that you write a smaller spec, but the verification takes longer because now even the instruction is symbolic, so the verifier takes longer. It takes about 2 hours in our tool. Okay, so using this style of specification instrumentation, we're able to find, to verify all the instructions that Morales handles, including all those 84 privileged registers and everything else. In the course of doing this, Charlie found over 21 bugs. And some of these are, what you might call functional correctness bugs. Here's a listing. I won't bother to pronounce it because I think I don't have enough time. And there's also some bugs that lead to crashes or, basically escape some of the isolation protections that the hypervisor is supposed to verify. So these are particularly bad bugs for a hypervisor. Let me show you just a few of these. So here's a snippet of code that's involved in memory protection. So it's the code that transforms the virtual machine's physical memory protection into the physical memory protection. And here the bug that existed in the code base was that the Morales forgot to basically mask out the lock bit for when mapping the virtual physical memory protection bits into the host one. And so as a result, the guest is able to control a particular bit, which is called the physical lock bit. And when this bit is set, then the entry can no longer be changed, and the memory protection basically is the same as in end mode. So in other words, the guest would be able to change the memory protection of the host arbitrarily. This is pretty bad as a bug because that's not something that a VM should be allowed to do. And you can see in green, here's the fix. The fix was basically a very, a low-level thing where we just mask off the bits differently so that the VMs can't do that. Here's another bug. This involves a certain load instruction. So there's some code that decodes the compressed load instructions. These are certain instructions which sometimes need to be emulated in Morales. And here the decoding, which you can see is kind of fiddly masking and shifting and stuff, had an off by 1 error in the computation of the immediate for the load. You can see that there's a 3 in the buggy code and a 4 in the corrected code. So you have to understand the details of how these compressed loads are encoded to know what this bug is from. But basically, it's the kind of code you could easily have in writing low-level code. And this doesn't, break isolation like the previous one. It doesn't directly crash the guest VM, but it can cause memory corruption or, in some cases, device misconfiguration. This isn't my experience, but Charlie reports that this is the kind of bug that is really hard to locate when you have kind of a first prototype and you're trying to run VMs on it, and you have to drop down into the debugger. You have to find a state and execution that gets you all the way to this line of code, and then maybe you can discover that this 3 should have been a 4. But with our verifier, this just fell out pretty much immediately. So when verifying the Popek and Goldberg conditions for this kind of compressed load and store, we immediately see the difference. We get an error trace, and then can go fix it. Okay, and just one more bug. This one is maybe not so interesting from, it's kind of more of the same, but it shows how lightweight verification can be useful in the course of doing a development. So the way that Charlie built Morales is he started with a really minimal set of RISC-V, and in particular, RISC-V has all these extensions. And so he started with a minimal set just to get things working, and then he progressively added more. But it turns out that some of the extensions can actually change the behavior of certain instructions and state-like registers. So in other words, every time he added a new RISC-V extension, he needed to go back and basically redo all the verification or all the reasoning he had done to see if the new extension somehow changed the behavior of things he'd already implemented and validated. So here, in this particular example, there's some registers called the MEPC. They stand for Memory Exception Program Counter. And usually the address that's stored in this particular register has data that's aligned to 4 bytes, but with there's a certain compressed extension, then the alignment is reduced to 2 bytes. So if this C extension is enabled, then you have to use a different mask, or you just get the wrong behavior. So again, this was kind of the kind of thing that was painful when just working without any kind of validation. But with our lightweight verification, add an extension, you discover that some instructions need to change, you get errors, and you go fix them. So it's really been a help Charlie to accelerate his development of Morales. Okay, so I think I'm right at time, so I'll stop there. Again, this is not a talk about how to build formal specifications of real-world languages, but I hope it gave you a taste that these things can have amazing impact for downstream users. And in particular here, we basically did a case study of taking SAIL specifications of RISC-V, taking an off-the-shelf verifier in Connie, and using it to verify at pretty low cost a large complex system, namely the Morales hypervisor. So I think this shows that the work this community is doing, which is often focused on the mechanics of how we specify languages and how do we get them adopted and what are the tricky mathematical things we need from specification frameworks. Like, that's all great stuff, but we do have users, and I think that we can have an amazing impact on not just programming languages but other systems if we continue on the path that we're following. Okay, so I'll stop there, and I don't exactly know how questions work, but maybe the room can unmute and take questions, or I do it on Discord. Just let me know.
Awesome. Do we have any question? Yeah, please. So, Nate, I will take only one question from Ralph, and then we're going to move on. And if you have more questions, then you can grab him tomorrow. Okay.
Okay.
Now I have to decide which of my many questions I'm going to ask now. Yeah, thanks, Nate, for the great talk. I was wondering if you could say a bit more about the TCB of the result. Maybe on kind of two axes I'm thinking about here. One is Kani isn't a full verifier, right? It's a bounded verifier, in my understanding. So there is some potential, I don't know, maybe there are just no unbounded loops in a hardware emulator for other reasons, so that maybe doesn't hurt you or something. And then the other thing is you mentioned something about when you create a symbolic state, there are some constraints on it, which sounds like some sort of invariant, which ideally someone would prove that it's globally maintained everywhere or something like that. Is this assumed, or is it also part of the proof? And what other things could there be in the TCP that like iffy would be maybe a possible gap here to like a full-fledged formal rock proof or something?
Yeah, great question. I'll just say, a completely formalized or mechanized, end-to-end proof was definitely not a goal of this work. So this is very much, adopting sort of the more pragmatic lens of the systems community and saying, can we use all these things to build a tool that gives us some assurance, but we're not trying to squeeze out the last the last pieces of the TCB. So you're absolutely right that there are pieces that are trusted or places where there may be incompleteness due to, say, limitations of Kani. Having said that, I think that these choices made in this project are very reasonable. So first, with respect to Kani's limitations, we're not verifying start to finish all of Morales. So there's a fair amount of instrumentation and basically guiding Kani to just verify the individual steps of the instructions. We have played a little bit with doing a more end-to-end thing, but as I briefly hinted at, that takes a lot longer. So we've had more experience with basically guiding it to verify these relatively small terminating snippets of code, where the fact that Kani's a bounded model checker, basically doesn't cost us anything. Your second question was about what was the second part of the question? Can you just repeat it really quickly? I'm sorry.
You mentioned there's some invariant constraints on the symbolic state you emit,
oh, yes.
And who ensures that those are actually true?
Yes. So there's other parts of the modeling of the system that I think you could connect these more closely to things like the SAIL spec, but for now, they're basically trusted. So the setting up of the context, I mean, that code needs to be right, or the whole model is basically wrong. And I've not thought deeply about how to remove that piece of trusted code. It's not very complicated, but you're right that it could be a place where a simple error could about these invariants could undermine some of the guarantees.
Okay, with that, Nate, safe travel and see you tomorrow.
Hey, yep, see you all tomorrow. Bye.
Bye. Yeah. 아까 보였는데. Okay. Awesome. Oh. 그럼 보여주세요 여기 헷갈리니까.
Is it me?
Now it works. Are you ready, Jonathan?
I'm so ready.
Okay, so the next speaker, Jonathan from Google, he's working on P4-based automated reasoning, and maybe he's our next user of P4 Spectec. With that, please welcome him.
Thank you. That's right. Clearly invited as a bribe, so don't expect too much from this presentation. I'll be telling you about some work that we've been doing at Google with P4-based automated reasoning. P4 here, you may not know, so just in case, super briefly, it's a programming language for network devices. That's most what you need to know. But when you start seeing me talk about switches, I don't want you to be immediately confused why I'm going into that. Okay, so I, of course, want to thank my team of collaborators. Stefan Smolka here is my direct manager at the moment, and Wakar was my manager before this. And actually, I would say was the person who made us able to do this at Google in the first place. Doing these kinds of exploratory projects can sometimes be a bit tricky in industry, as some of you may have experiences with. So I want to go back in time for about 8 years to tell you about some of the problems that motivated us to build this system. So Google needed to get a new generation of switches into their data centers. And in doing so, they had certain goals. The most important goal was for these switches to be very, very fast. Right? This is why we're updating to a new set of switches in the first place. And in particular, this means that there's a new ASIC, new hardware, that is, like a new chip, just in case, and new optics. One thing I meant to say in the beginning, please do feel free to stop me and ask questions. I no longer know if I'm like saying industry jargon, so it's possible it slips in, and then you should be like, that doesn't make any sense. That's not a real world. Cool. The other big goal that we had, and I won't say too much about this, but we really wanted to be open source and industry aligned. And there's some very practical reasons for this beyond whatever moralistic reasons you might think of. One being, it makes it much easier to work with external collaborators. And another being, it means that if the world moves a sort of technology forward, we're not immediately left behind. Right? And that turns out to be a pretty big deal. We think we are very good engineers, for sure, and we have many of them, but we are not the entire world, arguably. Anyway, so the other big thing is silicon independence. And this is the one that I'm perhaps most passionate about. We'll also call this optionality throughout the rest of the talk. And the key here is that I told you that we're going to get this new ASIC with this new hardware. And actually, we would like to be able to just sort of swap these out. Not necessarily while they're running, but like if we buy a new one, then we want to be able to just put that in. And if we start getting programmable ASICs eventually, this is a thing that's coming up in the switch community, you may or may not have heard of this, then we'd like to be able to just go in and use these in our data centers. So that was a very important concern. And finally, we need to move to a new SDN API. I'm not at all going to tell you about why we're doing that, but it turns out to be very important. And the SDN here is software-defined networking, another concept that you may or may not have heard of, but extremely briefly, if you learned had a networking class in your undergrad, you probably learned that networks were these big distributed systems of switches that all do their own little thing, and somehow they figure out how to make the internet work. We don't do that. Think of switches in our data centers as being extremely dumb, like maximally dumb, and there's instead a centralized controller that figures everything out and programs those switches to do the things that they want to do. That's really what's going on. Okay, and in the end, of course, we need to actually deliver a data center fabric. Otherwise, all of this work was useless. So in an ideal world, it would be great if we could just do all this work sort of serially, right? Because then you know what dependencies do before you have to write the things that depend on them. In the real world, that turns out to be unacceptable because by the time 10 years rolls around, you kind of have new ASICs and new optics. And the old ones are no longer fast, right? So instead, you have to do all of this at the same time. And for any given layer now, you kind of have new capabilities that they're kind of figuring out come from below, and new requirements that they're kind of figuring out they need from above, which makes it pretty tricky to design all of these. And in the end, 3 years in the future, you need to deliver this production-grade data center that I told you about that's at least as reliable as the current generation that we've been using for 10 years. So how do you possibly do this? Well, I think there's a key trade-off space here, and that's what I'm really sort of here to talk to you about today, which is there's a trade-off between reliability and feature velocity. And what do I mean here when I say feature velocity? I told you that sort of requirements and capabilities change over time. That means that you have to change all of these things throughout this period, right? You're sort of exposing new features. You learn of a new thing you need, and you expose new features. If you want to do that fast, this is feature velocity. OK, it turns out in isolation, we know how to solve both of these problems really well. For reliability, you just write lots and lots of tests. That's great against the spec. I recognize that this community doesn't believe that that's reliable, and I think that's perfectly reasonable. But in industry, that's a gold standard. All right? So you want to write lots of tests against the spec. But if you want maximal feature velocity, actually, you just don't want to test anything at all. Because now you can just change a feature. You can add a new one. Great. I mean, your data center crashes, but you definitely added that feature. So the reason why these are sort of in contention is that every time you add or change a new feature, all of these beautiful tests that you just wrote have to come and change. And so that just means every additional feature that you add, every additional test that you add, costs you a lot. So there's kind of this nice, it's not really a curve, line of manual testing. And of course, you can move this line. You can just throw more money at the problem. You hire more engineers. Probably there are diminishing returns. I'm not going to touch on that in this talk. But you could imagine that you could move it. But wouldn't it be great if instead there was some sort of magical way to be in that top right corner, where you just have kind of a comprehensive set of tests that appear magically for any new or modified feature that you use, where your tests just change when you change the feature, right? That sounds amazing. So amazing that that's, of course, exactly what we do. And how does this work? The specification part here is the key. And really, it's by making the API, which is how we expose these new features, and the tests come from the same language. That's really the key insight. So if you know anything about P4, and you don't need to, but if you did, you would think that the way we use P4 at Google was very strange. Because what it's really designed for is as a way to program a programmable network ASIC, kind of what I told you in the beginning. Instead, none of our network ASICs are programmable, more or less. Instead, they're what we would call a fixed function network ASIC. And we just use P4 to model their behavior. And then we say, well, the ASIC should abide by this model. What does that buy us? Well, actually, if you think of these P4 programs now as these machine-readable specifications, they just have to capture the requirements for a particular switch in a particular deployment role. If you know data center networking, and again, you super don't, then these are sort of three very common types of switches that you have in a data center. Top of rack switches, middle blocks, and fabric border routers. This is the only P4 that I'm going to show you throughout this entire talk. So I'm going to really make sure I explain it moderately well. The interesting thing about all of these switch deployments is that they're embarrassingly simple. There's very little stuff you need to do here, and particularly with the middle block, which is why I'm choosing that as an example. The middle block really just routes traffic forward, basically. And so the thing that you need is some sort of table, like an IPv4 route table, that matches on a packet, its IPv4 destination, for example, and takes some action. And this is a very common abstraction in the networking space, something called a match action table, right, where you match on some packet feature and maybe some metadata, and then you take some action that probably modifies that packet or some metadata. And so this is kind of our main requirement for the P4, for the middle block, and that's a very simple requirement, but it gives us two very powerful things. Number one is it gives us a schema of the switch API. It tells me exactly, as an SDN controller, what kinds of table entries I'm allowed to install on this switch. How am I able to change its behavior in how it forwards packets? And so for example here, I'm forwarding any packet that starts with a 10 in the IPv4 destination to port 42. But it also tells me what that actually means, right? It gives me the data plane behavior that's expected given some set of table entries. So if I'm actually given such a packet, then whatever port it ingresses on, it should go out port 42, right? So it tells me what this behavior is. And this lets us do some cool stuff. Because the SDN controller now has this extremely simple view of what it means to be a middle block switch, right? It's this very simple API where it just does L3 forwarding, IP forwarding, and load balancing, let's say. And the switch ASIC is actually this crazy, complicated beast of a machine. It can do almost anything that you want it to. It has infinite configuration knobs, and no one knows what a large set of those configuration knobs do when you use them together, but you sure can if you want to try. Which makes it very powerful. Anything you can think to do, it can usually do, but very, very unpredictable, right? Very hard to test that this is doing the things that you really want it to do. But I just told you we can capture these requirements with this nice P4 program, and that gives us this schema. Then we can just restrict the switch access to only use this schema. And now we only really need to test this schema because we know that no one's allowed to go in and fiddle with our switches behind our backs, in some sense. And so this gives us this embarrassingly simple API that's extremely predictable because I just told you that it makes this, gives you this data plane behavior that's completely specified in a machine-readable fashion. And I'll tell you how this P4-based automated reasoning comes into it being predictable in a real sense as well. So now the SDN controller has this sort of beautiful view of what the switch really is, right? There are two additional benefits. One of them I kind of told you about before. Well, actually, both I did, I suppose. One is velocity, right? As soon as I change this P4 program, which is the only way I'm able to expose any new feature, because literally otherwise you cannot use it, then I automatically am going to get this extremely predictable behavior. And also it gives me optionality, right? Any switch ASIC that can implement this API is one that we can now buy. And if you're a vendor and Google says we can buy your switches, well, now you're a vendor. Like that's all you would need to be a vendor in some sense. So how do we get this reliability that I was talking about? Well, the key thing is very, very simple. We do diff testing. So in what sense is P4 an executable specification? Well, in the sense that there is a simulator that executes it. So this is called BME2. We did not build this. This is an open source thing. There's the P4 runtime is the name of the type of API that we use. And this simulator speaks P4 runtime and does data plane behavior. The actual switch also speaks P4 runtime because we built that part of it, and also has some data plane behavior. So what we start by doing is we program the same table entries on the simulator and on the switch. We take some input packets, send them to the switch, and now we get actual output packets. This is the real behavior of the switch. We also send them to the simulator. We get the expected output packets, and we check, are these the same? And that's pretty much it. Now there's a key question you should have here. How do you get input packets that are interesting? let's say I only send 0, 0, 0, 0. Now, like, yes, I mean, that would be correct in the switch probably, but it wouldn't really tell me much about the traffic that I actually care about. What we do is use this symbolic execution. So we have this tool we built called P4 Symbolic. There are now actually other open source tools that also sort of do this. Ours is ostensibly open source, but it's sort of open source. You can see the code. You can see the code. Anyway, but P4 Test Gen is a very great open source tool that will also do this if this is something you were interested in doing. But this lets us generate these input packets given these table entries according to some goal. So if you think of P4 Symbolic as being able to say, I want to hit every single table entry with at least one packet, and for each of those, I want it to drop once, and I want it to be forwarded once. And that's pretty much exactly what we actually tell it to do, but that's the sort of thing you can say. So that's kind of the brain of the operation, if you will. OK. It's possible that everyone here knows how symbolic execution works, but I feel like I would be remiss in case I didn't say it, at least at a very basic level. So imagine you have this extremely simple program where you have some input x, you have a couple of branches, and then you can do 3 different things. You can ask your symbolic executor, give me the input that's going to trigger do b. It's going to go through and turn your input into a symbolic input, and it's going to collect constraints about what it means, like what has to be true about that input in order for you to get to each of these different branches. And then it's going to try to solve how do I get do b is reached. How does it do that? Well, it computes this path, grabs the constraints, solves this equation. We don't need to build these sorts of things. There are plenty of SAT solvers in the world. Use Z3, use anything else. X equals 1 is the solution. Great. How does this look in our world? Pretty much exactly the same, except the input x is a little bit more complicated in that it's some big packet. Tables now are these big sets of branches, basically. Each table entry is kind of one if statement where it takes some action. There's these other if statements in the program, and there's more tables. But I want to say, I want to hit entry 2, and you do the exact same thing morally that I just told you in the previous slide. So that's it. That's the secret sauce. Trivial. Things that you have known how to do for ages. Made a huge difference. We found more than 340 unique forwarding bugs. This is by an extremely conservative measure, because I only checked the most recent numbers a couple of days ago, and the liberal measure was about 1,500, and I didn't want to go through all of those. So I figured that if I just look at the ones that they really fixed, but in a proper way, and then the ones that are still open, that's a conservative measure. And less than 5 forwarding bugs that we are aware of have sort of escaped our detection in the sense that they were caught at some later stage by other methods. Of course, I cannot tell you how many were never caught because I don't yet know about them. But hopefully few. I guess that's the hypothesis. This has also been used for every data center deployment role since 2020. And perhaps most importantly, and I think this is kind of what Michael was also getting at, right? We don't get these nice statistics to update as much anymore because, of course, a lot of bugs are now prevented before they ever get into production or into any sort of testable state by us. Because these are now very well trusted, and everyone pretty much has to run them before submitting anything substantial. And that's pretty much all I wanted to tell you. So wrapping up, we derive this kind of restrictive APIs from P4 specifications. The APIs admit automated testing. The testing evolves effortlessly with the API changes. And so that gives us this very nice trade-off triangle, but now you can suddenly pick all 3. And that's the nice part. All right. I'll give you some resources in case you're interested, but otherwise I will take questions.
Questions? It's okay. So Matthew.
I will push the limits of my networking knowledge with this question. So to what degree are you doing flow-sensitive kinds of routing, or is it all simple table-like stuff, or is it packet inspecting stuff? Or?
Like in Google?
Yeah.
So here we come to these points where I never quite know what I'm allowed to say. To some extent, are we doing flow-sensitive routing? And it turns out you can test some of these things too. But this is, what I've told you about now is very much on a per-switch basis. So some of these properties that would hold between multiple switches don't really get, I mean, I guess we're over-approximating possible behaviors in that sense, right? Because we're basically saying, well, this could send you anything, even if we know actually it couldn't send you anything.
Thanks.
Yeah.
Hi. So you talked about the 5 bugs that you didn't found that came later. Do you have a sense of lesson?
There were 4 bugs.
I remember the number, not
Fair,
the semantics
yes,
around the
sorry.
number. Do you have a sense of given the tool you have, you're actually at the boundary of where you should be, and the other bugs are doing it a different way, and you were not meant to find them? Or do you think you've got more work to do on the particular tool you have?
Both, in some sense. There's a tragic trade-off in industry where there are always infinitely many things to do, and you kind of just have to pick the ones that you think are going to find the most issues. Now we've found a lot of them, so we're moving on to like higher level network verification and not doing as much of that interesting stuff. But definitely some of these bugs, if we made some improvements to the tools, we would have been able to find. These were not like unfindable bugs in that sense. Yeah. Sometimes what ends up happening, the ones that are perhaps the trickiest, are when they are masked by the table entries that we have. So it turns out it was impossible to exercise this particular feature given the set of table entries that we actually use in production. Those are the sorts of bugs that we, with this particular method, have trouble finding, partially because we do this kind of table entry coverage thing instead of path coverage where we could say, randomly delete some table entries and let's see what happens.
The last question.
Yeah, and also about those less than 5 bugs. Can you say a bit more about where those bugs were? Like, was the model just not matching the hardware, or so was the problem that the testing you described wasn't sufficiently exhaustive, or like some part of the P4 model was wrong, or like I don't know, how much you can go into detail there, but that would be interesting.
Yeah, good question. So one thing. I would potentially recommend this paper just for, it actually has a breakdown of like the first 130 of these bugs or something, and like what components did we find them in, which is kind of cool. One fun thing is 10% of the bugs roughly were in our P4 model. We were just like, oh, we wrote this specification wrong.
I mean, the 5 ones
Yeah, I know. But so that's but there were not yet any escapes, so it doesn't cover those bugs. For the 5 ones, it wasn't that the model was wrong, because we would still sort of consider that a bug. Well, okay, actually, in one case, it did turn out that the model was wrong, but it was unfindable, given the set. It was usually the limits of the way that we do the testing. So kind of like I was just telling Felipe, right, where you have, we often use this set of entries that we think are very representative of what we actually use in the data center, because we literally install them in our data center. And so it turned out that sometimes there are just behaviors that those can't exercise. And
the data center changes, and then we do exercise them, and then it becomes a bug.
Yes.
It doesn't have a data center, it's a bug.
That's right. But that's exactly right. Yeah. So then it changes, and this is why we try to tell all of our colleagues that just because it's not a production use case now doesn't mean it shouldn't work correctly. And so if you saw this sort of set of open bugs that I had, anyway.
Thank you. Yeah, let's thank him again.
Thanks.
We are gonna get to the last talk of this session with 2 speakers. So Philippa will start, and then Conrad will continue.
그 두 번째 마이크를
저기다.
주셔야 될것 같습니다.
Can you take off your badge? Ah, badge. Yeah. 그래서 화면은 이 마이크로 되겠죠?
Sorry, just a moment. It's gone dark for some reason.
Ready?
Yes.
Yes. Okay, so let's welcome Philippa.
Hello, I'm going to talk about verification for WASM Spectec and for WebAssembly in general. These are some of the guys working on such verification. These are the ones from Imperial. There's Conrad leading in Singapore, Sam in Edinburgh, and Joachim is in Lean FOO. But first I'm just going to go back and do a little bit of history so that one gets what's happening. I always like to have an excuse to put up those guys, Gordon and Robin, who really started this all off in some version of that. So we go from operational semantics, structural operational semantics, definition of standard ML, mature proof systems of various forms, partial mechanized language standards, and then a formal specification of WebAssembly. I did some work on mechanizing JavaScript in the ROC theorem prover, and that's how I got into this world. And I know very much many people in the audience because of the JavaScript work, including Suk Young, who took what we were doing and went kapow to this new place that we gave up between ES5 and ES6 because it doubled in standard. And then Suk Young came on board. So, and bizarrely, we've ended up in this project together, and how on earth did that happen? But it did. So on the formal specification of WebAssembly, and Anders Rosberg is very much the leader of that group. And basically, this is where I come in, starting with work that Conrad Watt did on doing a mechanization in Isabel of the WebAssembly standard before it got into publication. So the publication of the draft happened in 2017, correcting mistakes in the formal specification by Conrad. And we came together because I was in this Rockland, and Conrad knows about the Rockland, but went into Isabel land. And then with my student, Rao, we did some work linking the mechanizations together and moving to the first industry WASM 1.0 standard. We're now at 2.0, very much wanting to keep together with the projects, so waiting for each other, as it were. And we've got type safety, correct module instantiation, correct interpreter for WASM 2.0. It's been done this year by Rao and by Antanas in Conrad's group, and we will publish it at some point in a large paper, but it's basically done. And what I really love is this module instantiation. Here's the standard definition. Here's the theorem. And this goes right back to one of my mentors, Robin Milner's agenda, all the way to correct module instantiation of modules of a design that he created in ML. So I love that story very much. We then built on top of the WASM Search project many applications. Conrad will talk about what he's done in the ISBEL world. We also have the rock world, where Rao earlier this year at Popple talked about creating an interpreter where the results such as progress and correctness of the interpreter come along with the interpreter definition in such a way that the interpreter can be extracted and is efficient, and the proofs have been done and in tandem at the same time and then get thrown away. For those of you who know Phil Wadler's work on getting interpreter from progress, this is the flip way round. There's work on Certi-Rock, and we have a WASM back-end by Mayo is the first author. Bas Pitters and Jean Pichon are also involved. And we've got many program logics now beginning to come from the Iris work. We were there at the beginning connecting WASM Cert to Iris, and now the Aarhus guys have taken over, and here's the beginning of that stream that's happening. But that's WASM Cert, and we've moved to WASM Spectec. And the reason for why is not only is the formal semantics very difficult to do with the bottlenecks of Andreas and Conrad in the standard, or there were others, but then the main ones having to cope with this formal specification. But also then think about what's happening with the mechanization in an interactive theorem prover. We are keeping on track with it in the sense that WASM 2.0 was published this year, and we've done the mechanizations. So we are just about keeping track, but it's an awful lot of work, and can we do better? So 2 years ago, we had a Dagstuhl where basically a gang of us came together and created Spectec that you've heard about from Sukyung's talk, and it's now been accepted by the standard. Sukyung had a diagram like that. My diagram's slightly different. Just flip it round and squint a bit, and basically it's the same diagram with a little bit missing. So basically we've got the TSL. From it we get the formal specification, prose and interpreter, and Sukyung's done some recent work on the test generation. And the DSL it has this sort of structure. So for example, if we just think of some value types for numbers up there, either integers or floats, we have the notion of type family, where the integers are clumped together and so are the floats. We have operations that can work on the integers or on the floats. Here's how you do variable store. And we have relations where basically it just looks like this. So for example, the command drop takes a value off the stack and drops it. It has the type given the value of the type of the value on the stack to empty sequence, just meaning you've dropped that value, you're not giving it to anyone. And so this is a reduction relation for the operational semantics. We also have various bits of auxiliary function definitions working over the inductive types for numbers. So I've told you about this, and eventually I'll give you some stuff in here. And the middle, I'm not going to talk very much about, but it's there. And in particular, when we get to here, it's beginning to look a little bit like a normal. It's like a declarative semantics. It's actually not, but it's beginning to. So first I want to describe what we've done in 2 MSc projects, which is go from the internal language down to rock directly. And these guys have done it, one last year and one literally submitted last week.
and hasn't done his fiver yet. And basically what's going on, you've got an automatic translation from here to here of the rock definitions and hand proofs of the results. And we've proved preservation and progress. It's very much on the way. And we found real errors with the DSL because of it, some more fundamental than others. And, you know, we'll keep evolving this and get it all better, basically. And just to show where the work got to, we were not working with dependent types at the intermediate language, and in particular, the translation of the type families, what I've just shown you about putting together the integers and the floats, that we haven't done because we can't go direct to rock. And we have lost information about the premises of user-defined types. And I can show that here. If we have two values, different values, we have a way of transferring from one to the other via something looking like this. And if these types are different, then this conversion function will go. And if they're not different, then you don't even think about it. And we didn't work with those. But basically, because of these MSc projects, we're now doing this project for real. And Diego's a PhD student. Rao has always been supervising the MSc projects along with Conrad. And we are basically on the way to doing it for real. And this is what we're doing. So we got the internal language. We're going to create this language, the mechanized internal language. There's going to be a step towards lots of interactive theorem provers and their definitions. And so the idea is, this is a cute application. Can we have it as a environment for lots of interactive theorem provers? And the answer is yes, because my gang's doing the rock, Conrad's doing Isabel, Joachim Breitner, who was part of the start of all this, Spectec, went to Lean, thought he wasn't going to be able to play anymore, but it turns out Lean are really, really interested, and so he's absolutely doing it. And not only do we have to deliver to the standard, we also have to deliver to Lean FRO now. So that's, you know, this is getting a lot. And Sam in Edinburgh is doing AGDA. So the point is, we knew from our work from here to here that there was a natural thing here to make things nicer. One notion is you've got functions that are defined, it's defined this way if the psi condition is this, and it's defined that way otherwise. And instead of that otherwise, you could have the not this. And you know, there was a bit of a fight about this actually, because from here, what does it mean to go to the pros? You know, the otherwise is really nice. But from the point of view of what's going on down here, having a more precise idea of what's going on with the psi conditions is there. So that's just one example, and there's lots of things about what's here is our real normal. That's the way to think of it. This is almost like normal. And in future, where is this going? I've got, you know, there's opinionated imperial people in my group going, this should be the same thing, and we should have just one thing here, losing information to go to the pros and interpreter later. But so these sort of internal structures, you know, over time, I think they could easily change because, you know, actually people are opinionated and have good ideas. But the point is they have to change a way that's compatible with what's going on and not breaking what's going on. So how do we do that? We've got to understand. I think I've done enough of that. So basically, I thought, so we're here. we've got the type families and dependent types, and the type families in particular are quite difficult. So we were exploring monomorphization. We thought monomorphization was going here. So, for example, you have definitions for each of those integers and floats rather than bundling everything up in one. But instead, we've been exploring this at this place because it's also useful to what's going on up here. And what we're finding is we're not quite sure where to put the monomorphization, but it might be better here, it might be better here. So we're exploring all these types of issues of what to put where. And what else to say? How much time do I have? Good, good.
Negative minutes.
I have negative minutes, apparently. So, I'm ignoring that. I was given a little bit of leeway because we're sharing. But what I like about this is that not only are we doing something that we hope is useful for the real-world language standard, but also we have a place where there are all these theorem provers on the same problem, and we can start really comparing them. So, for example, rock is in this place and this place, because for those of you who know what I'm talking about, this is the extrinsic type world. This is meaning do the AGDA thing, which is making everything intrinsic so that you're working with well-typed terms by itself. So rock and lean can also work in this world. So now, actually, which way is better and what about the choices? We can start exploring. So I'm liking this for this sort of reason. Now, in 2 seconds, or rather 2 minutes. Sorry? Oh shit. Sorry. So this is what the DSL looks like. This is a demo that Andreas Rosberg hacked up in Dugstall last week. We have got the new idea, this is why I wanted to do it, new idea of lemmas and theorems in the DSL. It's cute. And here it's done in a template way, with the integers and floats all done once and for all in a template way. Here, those lemmas come in its own bit for the specific integers. And here's the rock stuff, all automatically generated. Thank you and sorry, Conrad.
You can have some coffee break time, so.
I won't be too mean. I prepared 2 versions of this talk. One of them is half the length of the other one, so I'm going to give the half.
Oh, you're so smart. So well prepared. Or you knew Philippa.
What did I know?
Oh,
what
yeah.
could I have possibly anticipated here?
Pre-break.
A little unfortunate that my taskbar is still showing up. Is there a way to hide the whole thing? Normally there is, right? Okay, it's actually kind of, it's cutting off the bottom a little. Actually, I do have some text where that's relevant. Let me try one thing very quickly. Yeah, I'm gonna just restart Chrome because sometimes it forgets to grab the. Okay, moment of truth. You know what? Let's just go with it, I think, at this point. Okay, so hello everyone. This is about Spectec in Singapore. The first thing I'm going to be talking about is the stuff we did in Isabelle. This is against the handwritten mechanization of WebAssembly, which we called WASMcert Isabelle. There was also WASMcert Coq coming out of Philippa's group. The big thing that I was most excited about with WASMcert Isabelle is we use it to verify this efficient interpreter, which is now being used by WASMtime, which is a very widely used industry WebAssembly implementation, which is itself maintained by the Bytecode Alliance, and they're using my interpreter as a fuzzing oracle to check their interpreter is correct. So when I say efficient interpreter, fast enough for a fuzzing oracle, probably not fast enough to replace WASMtime. And this was the paper. So obviously, we should bring this thing to Spectec, not only because we then don't need to worry about maintaining WASMcert Isabelle as it exists today, but as WebAssembly gets more features, we want to kind of inherit them as cheaply as possible and not have to update our model manually and push through all those proofs. So we should put this on top of Spectec. Philippa's group is helping with this by building this nice intermediate representation that's going to go to lots of different theorem provers. So I say, thank you, Philippa's research group. I will use your thing, and I'll take responsibility for the Isabelle bit. So thank you for that. Okay, second thing my group is doing. Why should we trust Spectec? Because it's really good and very carefully engineered by Suk-Young's group especially. We should verify the most important parts of it though. And a core part of Spectec is the animation procedure. This is something that's done in the kind of internals of Spectec to turn a bunch of inductive semantic definitions we have into executable functions. And this powers in particular the reference meta interpreter and the prose specification backend. So it kind of looks like this. A lot of WebAssembly definitions end up being these big inductive definitions. We want to turn them into executable functions. That's something Spectec does internally automatically in a lot of cases. But how can you trust this transformation is correct? Well, with the magic of theorem proving, we're going to try and mechanize this and do some reasoning about it. Currently, we're doing some work on prototyping the animation algorithm used by Spectec in MetaRock, with the idea that you could kind of, at the end of the day, if we get this right, you could take some arbitrary rock inductive, push it through our MetaRock animation, and then get an interpreter out the end that has a proof connecting it. This is something that actually mirrors very closely some work that was already done in Isabelle. The Isabelle community is where the animation terminology comes from, so we're kind of following in their footsteps, but I believe no one has done this for Rock so far. If I'm wrong about that, come and correct me in the break. So, I also thought I'd like to talk briefly, given we're talking about kind of the trustworthiness of Spectec and the meta-theory of Spectec, what are the bits of Spectec I dislike the most from a meta-theoretical perspective? These aren't necessarily things we're going to be able to change, because these are things that are kind of discussed as a group, and, you know, I've won some, I've lost some in terms of the design of Spectec. But this is my time, so I get to complain about certain things. I think Spectec's concept of index types is too complicated. Spectec has this concept of type-level arithmetic, which allows it to write pretty complicated constraints. So, for example, we can define what's basically an ADT, but we can parameterize that ADT by, in this case, it kind of straddles the line between being a number and a type-level number. You'll see what I mean in a second. And then I can write arbitrary predicates over this number. So, for example, if I wanted to define a type that represents an I32, I could say, well, actually, no, this is even more complicated. This is if I want to define like a family of types indexed by number, and then I have some predicate on the number over here. It gets very, very complicated, and it's actually not used that much in Spectec, but it's still part of the front end. And then later on, I can define a function which takes not only a number, but also an instance of my type parameterized by the same number. So this is like classic dependent type stuff, right? It's really scary. And the fact that you can write arbitrary predicates over this. The thing is, 99% of the WebAssembly specification, it's my contention, doesn't need this, and the 1% that does need it, I believe we should be writing by hand rather than making Spectec's type system so complicated. But that's kind of where we are today. Maybe I'll get Andreas to change his mind on this at some point in the future. Second complaint, we don't have a good model for evaluation contexts. The original pen and paper specification had these really sophisticated evaluation contexts. In fact, it gets even more complicated than this, because you have a concept of continuations, which allows you to capture evaluation contexts. But you could write nice reduction rules using the pen and paper meta theory like this. You could just say, here's my big crazy evaluation context with all of the kind of things, and then I can say, oh, the semantics of return inside this big evaluation context is you just jump out of all the evaluation contexts. So that's pretty nice. In Spectec right now, we have to use this more naive semantics where you bubble out of one layer of the evaluation context at a time. So you end up with all of these different reduction rules for every kind of component of the evaluation context. And that is very regular, and it does work, and it makes the animation process easier because you can kind of see exactly computationally what you're doing at each step. But evaluation contexts are really nice, and it's nicer to read on the page, and also it would help with certain things I want to do with generating efficient interpreters from Spectec in the future. So my contention is we need a better story for evaluation contexts. Third, we can generate an interpreter for the runtime semantics, but we can't generate a type checker from the type system just now. We do define both the type system and the runtime semantics in Spectec, but we can only animate one of those things. And you may think, wow, this is unfair. Type systems are really kind of non-computational, and it's hard to connect that to an algorithm. For WebAssembly specifically, type checking is a single linear pass, and we very carefully design the type system to ensure that's always true. We insert a bajillion annotations everywhere. Everything is fine. So, given that our type checking algorithm is so simple and our type system is set up from the ground up in order to support the type checking algorithm, everything should work. But it doesn't right now, so we've got to do that in future. Okay, last thing I'm going to talk about as part of my half talk, wearing my other hat. On the industry side, I'm one of the chairs of the WebAssembly standards body. I helped design WebAssembly's relaxed memory model for its concurrency specifications. You can decide for yourself if that's a good thing or not that we have a relaxed memory model. And to kind of double down on my sins, I also lead this proposal called the Shared Everything Threads proposal, which is like the second iteration of more complicated threads within WebAssembly, alongside 2 industry representatives. And currently, Spectec doesn't support even the first iteration of WebAssembly's concurrency model, so we should do that, essentially. For Concurrency 1.0, that's kind of what's deployed in the wild today and the things that people are using. We'll need a way to convincingly specify a relaxed memory model in Spectec. You know, if I was being really ambitious, I'd say, and we should animate it and get an interpreter and blah, blah, blah. But I just settle for defining it convincingly. Second, we need some kind of extension to the top-level concept of a program state. This is just a very surface-level thing. Your program state used to just have one thread. Now it has lots of threads. But this does kind of bubble down through all the middle ends and back ends that make certain assumptions about the shape of a WebAssembly state, especially ones connected to the interpreter. So that's going to take a lot of hacking on Spectec's internals. This is actually a really good test of our kind of proposition that occasionally you'll need to update Spectec to handle new features, and that's okay. This is probably the update that is least okay for Spectec, so if we can pull this off, we can basically do anything. But these are all the things we need to do. One interesting aside is JavaScript's relaxed memory model is very similar to WebAssembly's, but currently we just kind of specify them separately, and we don't really do any work to make them kiss. So we should maybe be thinking about ways at the standards level to do that more nicely. For Concurrency 2.0, this is the Shared Everything Threads proposal. We're still in the politics phase of standardization, where all the companies are arguing with each other. The core issue is with Threads 1.0, we can share these raw buffers of bytes. In the JavaScript side, these are called shared array buffers. In the WebAssembly side, they're called shared memories, but not garbage collected objects or functions. And it turns out this is really important if you want to compile a garbage collected language to WebAssembly or some kind of program that does dynamic code loading. Because in WebAssembly, dynamic loaded code becomes this kind of function closure that's garbage collected. It really doesn't play well with this concurrency model. So the solution is specify some kind of new garbage collected allocation that's safe to share across threads. If you're in the web standards world, you're kind of curling up into a pretzel when you see the sentence. It's very scary, a lot of politics to do to make some form of this work. And there's a related proposal called shared structs in JavaScript. So this was my stopping off slide in case I had to stop early. So in summary, we want to shift existing verified artifacts to depend on Spectec, which will make it easier to track new WASM features. We want to build trust in the behavior of Spectec itself with kind of meta-level reasoning, potentially change some of the weirder parts of Spectec's meta-theory, make Spectec understand how concurrency works, and then make more complicated concurrency extensions that will probably break Spectec again. So that's kind of where I see myself working with Spectec and WebAssembly in the future. Thank you for your time.
You're like singing rap. So any question? I think we can have 1 or 2 questions from the audience. Okay then, because it's coffee break, we can use this time as questions to Conrad during the coffee break. And we are going to be back at 3:40, and enjoy the coffee break. Thank you. Hi everyone, welcome to the last session, and the room is getting more crowded. But yeah, let's get started. The last session is gonna be with one talk by Ralph here, and another remote talk, and then panel session. So, as the first speaker of this session, let's welcome Ralph.
Yes, mic check is also working. Great. Yes, thank you all for coming and exploring this room. Apparently Rust is very popular. That's great. So let's talk about specifying Rust. So you've probably all heard of Rust, and the main thing you're going to have heard about it is, I mean, it's known for its type safety, right? You get this nice high-level type system for language that still supports low-level paradigm, and that's all great, and it's a happy land, and our little Ferris crab can live very safely there. But what you might have not heard is that Rust has a dark secret side. And this dark secret side is unsafe Rust. So as long as we only talk about safe Rust, the runtime semantics are kind of obvious. I mean, they're not really obvious. There's still a lot of things going on, and we heard a bunch of talks earlier about specifying entirely safe language, and it's complicated. But Rust is like, it's the same kind of problems. And generally everybody kind of agrees on what all the programs would do. The hard parts are more like type system, borrow checking, pattern matching, like there's a bunch of gnarly things there. But when we go to unsafe code, then even just the intended runtime semantics of code can get tricky. So it's kind of a different dimension of the problem that, like for example, Spectec has been solving. And so to explain why that is, I brought two demos of like the kind of weird things that can happen when you have fun with unsafe Rust. So here's a first little demo, which creates an integer by illegal means, namely by just taking some memory which is not actually initialized and just saying, yeah, don't worry, there's an integer here. And then it tests a rather innocent property on that integer, namely that it's less than 0 or equal to 0 or greater than 0. And if you compile this with the latest, okay, this is no longer the latest, but same with the latest Rust compiler, same result, we see that somehow the assertion actually fails. So I think we need to call our mathematician friends because we discovered a new integer. So something very strange is going on here. So that's the first demo. And then there's a second demo, which is a bit more spicy because it involves pointers. And so what we have here is I'm going to go over this program well as slowly as I can. So we start with two local variables, 0 and 1, initialized to 0 and 1, and we get a pointer to both of them. And I helpfully named the pointers after the variables. And then we do a few shenanigans here, which boil down to computing y plus x minus y, which of course the two y's cancel out. So this is basically just x, and we use wrapping arithmetic, so there's no weird like hidden overflow nonsense or anything like that going on here. This is really just y plus x minus y. And we can even confirm that, yes, those are actually the same pointer. And then we write through one of these pointers, and we read through the other. And because it's the same pointer, obviously we should get the result, right? Except if we build this program with optimizations with the latest Rust compiler, we don't. We somehow still get a 1 here, even though we've already written 2 to that place. So again, something weird is going on, right? There's a dark, that's why there's a kraken in unsafe Rust. It can really turn your program into some very, like doing some very strange nonsense. And so some of you will have already guessed it. What actually happens here, of course, is that these are examples of undefined behavior. And once you have undefined behavior in your program, afterwards, like any kind of garbage can happen. So the main challenge when specifying unsafe Rust is to carve out exactly when our program does and does not have undefined behavior. There's usually consensus on what happens on the happy path, but whether we are on the happy path is unclear. And so if you want to look for some inspiration for how we could write such a spec, we could go to some prior work. There's like, I mean, WASM and all the other nice languages we discussed don't really have undefined behavior, so unfortunately we can't just copy what they do. But C and C++ do. And it turns out what they're doing doesn't really work. So there's a lot of work not teasing this out, but particularly a lot of this paper where they kind of went ahead and just asked a bunch of programmers about what they think about various parts of the standard. It turns out there's really 3 versions of the C standard. There's the standard version, there's what the compiler implements, and that's what the programmers think. And those are just like 3 completely different languages. And so I think currently, if you're claiming you formalized the C standard, I don't think you can really make that claim because the standard is so ambiguous and it's so unclear which part it has to do with the real world that you formalized something, but you have not formalized C as it is in the real world or C as it is in the compiler, because those are not even the same thing. So there's work to be done even figuring out the standard, the spec, before we can formalize it. And so we have a similar problem in Rust. We need to figure out our spec first. And so I want to list a few desiderata for this spec, which I can go over very quickly because they will be completely uncontroversial in this room. We want it to be precise and executable. Everybody already said that today, so I can skip this part, which is great. I also want it to be accessible, because I want this to be kind of eventually become part of the Rust specification. I want Rust programmers to be able, at least the advanced ones that are writing unsafe code, to be able to deal with this. We cannot litter this with Greek letters, right? Nobody can read the spec there. So we have to do something which is both precise but also accessible to Rust programs. It doesn't have to be accessible to anyone. We can assume they know Rust. Of course, I want it to be complete because it's actually supposed to be the spec of the language. And eventually, I hope this can become an official part of the Rust specification as produced by the Rust project. So how are we going to go about this? So my proposal for how this could work is mini-Rust, which is following this core language approach, which also has been kind of successfully used in a bunch of prior approaches, including, I would argue, some of the great JavaScript work we saw earlier. This like fragment of English that's basically formal is kind of a core language that they use to describe these individual operations, right? So in our case, the core language is a formal one, but I think this is a very successful approach to break down large operations into a series of small operations. And we're actually kind of doing this on 2 layers even here. And the style of mini-Rust is that it is an operational semantics expressed in Rust-like pseudocode. So I think it should be operational and not axiomatic like the C and C++ spec to avoid all the problems with that spec. And it is expressed in code and not declaratively, because I think that helps both with accessibility and, of course, it makes it immediately executable. So how concretely does this look like? Well, let's look at the core ingredients of the mini-Rust spec, right? There's a grammar, and then there's the operational semantics. So here's the grammar as we would write it down in formal notation. And this is actually probably fine. Most programmers can read BNF. The existing Rust spec even has syntax very much like that. But it is not fully machine readable, not immediately at least. You would have to throw some tooling at that. And maybe we can make it even more blindingly obvious in Rust terms of what this actually is. So we can rewrite this grammar as just a bunch of Rust data types. So we can say a basic block is a list of statements followed by a terminator. Here are some of the terminators that exist in the language. Here are some of the statements and expressions. Because Rust has full algebraic data types, we can just write these down in a very natural form like we would in our idealized interpreter in Haskell, or like in a deductive data type definition in Rock. We can just write this down in Rust terms, and every Rust programmer will understand without a second thought what all of this means. So we are both precise and accessible to Rust programmers. But of course, syntax is the easy part. We have to also express the semantics. So if we did this formally, we would maybe for an operational semantics describe some sort of state space. And then we would describe a function, or more likely a relation, but could be a function, that computes from one state, then what is the next state. And so we do the same thing again in terms of, for mini-Rust, how do we make this more accessible? Well, we express it in Rust. So the state is just a data type, which has a bunch of fields for all of the components that are relevant for the abstract machine state. And then the next function is just a function which we write in actual Rust code. So overall what this is basically an interpreter. And most Rust programmers, at least like the more experienced programmers, will have already seen an interpreter, might have written an interpreter. So this is like a framework that programmers are very happy and comfortable thinking in. And so we can lure them in by saying it's just an interpreter, and then secretly it's actually a formal spec. But they don't have to know that, right? Because it's actually kind of the same thing when we look at it at this level. So this is the high-level structure of mini-Rust. Now I want to get a bit to the bottom of those 2 examples that I showed. So to do that, let's start by taking a look at how memory looks like at mini-Rust. Unfortunately, I don't have like a lot of time to go into to demo what the actual mini-Rust source code for all of this looks like, but I want to zoom in on one thing. So memory in mini-Rust is where we think of memory as there's this one big address space, where Rust is a fairly low-level language. You can do pointer arithmetic. So we actually have to expose the fact that there's only finitely many addresses. This is all kind of visible in the program. So there's 2 to the 64 addresses. And then distributed over this address space are allocations, which are like parts of memory you can actually access. Local variables on the stack, heap allocations, global variables, all those sorts of things. And the data in an allocation is a list of the bytes, which are just the current content of that allocation. And so what you can see here, what's one thing that's interesting about these is that the bytes are maybe not quite what you would expect them to be if like you go to an operating systems class. A byte is not just 8 bits. A byte is either initialized with 8 bits or it is a special magic uninit value, which is just a genuine thing that a byte in memory can be in this model. So this is the picture version. And now, of course, this is not executable and it's not sufficiently precise, so we have to express this properly in mini-Rust, and we can again do this with Rust type. Memory is a list of allocations. Every allocation has a base address and a list of bytes, and every byte is either initialized or uninitialized. And this is an enum type, but Rust programmers will understand what exactly this means, and there's no ambiguity. So this is our idea of memory. And now what you might be surprised about looking at this is that there have been no types so far. So in Rust, we made the deliberate choice of making memory entirely untyped, which is different from the C and C++ specifications, because we think this better matches programmer expectations. People go to unsafe Rust when they want to do like weird type layout shenanigans. And so we can't just tell them, oh, you have to follow some sort of typing discipline on the heap, because they would be violating this all the time. And even in C, we see people do -f no strict aliasing in basically every major C program. So in reality is also most C programmers program with untyped heaps. So we make this like officially part of the Rust specification. There's no types here. But still types do come in, of course, in Rust statically for all our great type system things. They also do come in dynamically for the concept of representing high-level values. So in mini-Rust, we have a rough kind of mirror of the AST of Rust's types. It's structural and not nominal, but the details don't really matter. The key point is that for defining some operations, like arithmetic, we really want to have like high-level concept, like a mathematical value sitting there, right? You want to add 15 and 68 or something. You don't want to add just some bits. So we have this concept of a high-level value, which could be a mathematical Boolean, could be a mathematical integers, could be a tuple of other mathematical values, so this is recursive. And this lives like in beautiful math land. But then somehow we have to reconcile this with low-level raw byte land. And so this is where this concept of a representation comes in. This is something you can see hinted at in the C standard. They talk a lot about representation. They never make it very clear what exactly they mean by this. So here's what we interpret this as, what we mean by this, or at least my proposal for mini-Rust, is that the representation is really basically a form of serialization. You take your high-level value and you turn it into a list of bytes, just like when you want to take your structured thing and like send it over the network or something like that, right? So there is an encode function which serializes, and there is a decode function which deserializes, takes a list of bytes and returns the corresponding high-level value. And these two functions basically they bridge the gap between the safe, beautiful, happy land and the Kraken world, right? That's how you go back and forth. And crucially, the lower part here, to go from Kraken back to Ferris, this can fail. Because when you parse something, you might be getting input which is not actually well formed, right? Every deserializer has an error case. And so our decode also has an error case. Okay, so that's the framework. Now let's get back at our example. Remember, there was this I8 weird integer, which somehow defied our logic and mathematics. So we have to understand what happened there, we have to look at what happens when we decode an I8 value. So at this point, we are decoding a single byte, because I8 has size 1, so I've already simplified this a bit, and we have to return this value. So, well, what can we do with the byte? Well, remember what a byte is. It's initialized or uninitialized. So the only thing we can do with the byte is pattern match on it. And now we have to write two cases. Maybe the byte is initialized. In that case, we do the usual 2's complement thing. There's some logic going on for how to turn a bunch of bits into like a signed integer, and like it's not trivial, but it's obvious and solved, and we can just use that. Or the byte is uninitialized, and in this case, we raise a parsing error, because uninitialized memory is not a valid representation of an integer. Because which integer should it be? And we could put 0 here, but like, no. So this is just a parsing error. So if we now go to our program, this is very roughly the mini-Rust version of the example program I showed at the beginning of the talk. I disabled syntax highlighting because this is now object-level code. Everything so far was meta-level code. This is now actually in mini-Rust. It's a basic block language. Don't worry too much about the details. But also what we do here is we create some storage for x without actually putting anything into it. So x gets some memory allocated to it, but we don't initialize it. And then we test we make our check on that memory. And so if we now go over this program line by line, well, when we run the storage live, we create a new allocation. And the contents of a new allocation are, of course, initially uninitialized. So that's the allocation is length 1. That's where there's only a single byte in that table. And then when we do load x, we call our decode function that we just wrote on this 1 byte, which means we feed uninit into I8 and decoding, like parsing fails. And that at that moment the program crashes and burns, where the interpreter will just say, there's an undefined behavior error at this moment, we don't even have to continue. It just happens to be the case that the compiler still continues and does some garbage, which is okay because the compiler is allowed to do anything once you have undefined behavior. But as far as the spec is concerned, the program already went wrong at that moment, and so later the assertion failure is basically just noise. Okay, so that's the answer for the first demo. What about the second demo, where we had this weird pointer that was like equal but not equal or something? Well, we can already get a hint of what's happening if we look at the docs of the function we've used. We use this wrapping offset function. We actually use wrapping add, but it has the same docs, which says that, okay, so you can use this to do pointer arithmetic, and you're actually allowed to do arbitrary pointer arithmetic. This function itself is safe. It will never cause undefined behavior by itself. But the resulting pointer remembers, in scare quotes, the allocated object that the original pointer points to, and you cannot use it to access anything else. And so the problem that we caused in our code is that we did an offset from x to y, which is a different allocated object, but the pointer remembered where it comes from, and so that wasn't valid. But like, what does this mean in mini-Rust terms? How can we make this precise? Well, to make this precise, we have to look at this pointer thing. Right? So what is the concept of a pointer in mini-Rust? If you come from hardware, you might think a pointer is just a 64-bit integer. That's actually not the case. It's not true in C, but it's definitely not true in Rust. A pointer in Rust, or at least in mini-Rust, is such a 64-bit address, and then some extra magic metadata, which doesn't exist at runtime, but exists for the purpose of specification, which is very much like this uninitialized. It doesn't exist at runtime. It's not a distinction that exists at runtime. Right? I can't ask my RAM, is this byte initialized? They're all initialized. But it's a distinction that's important for the specification. It doesn't affect program behavior, except it defines whether a program has undefined behavior or not, which of course impacts program behavior. So the concrete thing that in this simplified model we remember about the pointer is just the allocation that it points to, which is just an index into this list of all the allocations which are memory. In reality, this thing is called provenance. It's a bit more complicated than just that, but I simplified it for the talk. And so now that we say that a pointer is an option alloc ID, now we can explain how there can be two pointers which are equal but different, right? When you compare pointers for equality, it only checks their address, because that's the only thing we can check at runtime. But actually, for the purpose of specification, there's another part of the pointer that matters, that has not been compared for equality. Those were not the same pointer. They were two different pointers with the same address. And so the equal returned true, even though they weren't actually fully the same thing in the spec. So we solved one problem. We created a bunch of new problems. Which is that, well, now that we have a pointer with provenance, remember we still have to serialize and deserialize all the things we deal with, right? Pointer is now the high-level mathematical value of something of pointer type, right? The same way we have mathematical integers, we now have these like mathematical pointers. So we take this pointer and we want to make it into a list of bytes. Well, okay, we take the address, it becomes an 8-byte number. That's standard, like little Indian, big Indian encoding details, like whatever you want to do for your target. But what do we do with the provenance of the pointer? We have no way to put it in these bytes. And yet when we decode it, we want to get it back. Otherwise, everything would fall apart. So to fix this, we need to change what a byte is. What we're going to do is we're going to extend byte so that it can hold this provenance data. We're going to say an initialized byte actually isn't just 8 bits. It's additionally, optionally, some sort of provenance if there's a pointer stored here. And now we can write the encode function in a way that it takes the pointer's provenance and just splats it on all of those bytes. And of course, now we've solved this problem, we've created a bunch of more problems. So now we need to say what all of the decode functions everywhere do with all of this provenance. And it turns out the details get interesting, and if you do the wrong thing, you lose a bunch of optimizations, and like it gets complicated. But there's a proposal for what all of these things could do in the mini-Rust spec, and there's some sort of design space here and what exactly it should always be. But by writing out the spec in these very explicit terms, and by being forced to write it out like an interpreter, these are questions we will immediately stumble upon, right? We can't forget to answer these questions, which is the thing that happens in C and C++, for example. They added pointer provenance, but then most of the rest of the spec doesn't really talk about what happens with provenance everywhere until Peter Sewell came, and like they spent 10 years figuring it out. And it's not in the standard actually itself. It's a separate technical report. It will probably remain separate, right? Which is not really solving the problem, I would argue. So with this approach, we can't really miss these kind of problems, because our interpreter just won't even compile if we are forgetting to, like, if we don't talk about what happens with the provenance somewhere. So this approach forces us to not have these kind of blind spots in our spec. Okay, so to conclude, The kind of main mini-Rust pipeline looks as follows. First of all, you have to take a Rust program and translate it to mini-Rust. We have an implementation of that, but that's not really formal. That's just, like, we just have a tool that does it. So the details of making that formal are somewhere far in the future, but this will definitely be an interesting problem to consider. And then you can run the mini-Rust interpreter on this program that has been translated, and the interpreter itself is written in this thing that we call Specker, which is this Rust-like pseudocode I mentioned earlier. You can also think of it like OCaml with Rust syntax. It's some of those things. It's basically a purely functional subset of Rust. And we embed non-determinism into this monadically. And so that way we can express what will usually be a relation as just a single function. And we are slowly moving towards getting 100% coverage of the language. So I have a series of bachelor and master students adding all sorts of parts to mini-Rust, because once it becomes a coding exercise, you can give it to a student. And so we now have support for most of the core Rust language features. We have concurrency, but only sequentially consistent concurrency. I'm not planning on touching weak memory anytime soon. But maybe someone has some good ideas for how this could be done. But I'm too scared of weak memory to even contemplate this. There's enough other fish to fry here. There's, of course, also a lot of things to do. Most importantly, I do want to be able to extract these things into ROC. I mean, these monadic interpretations kind of lend themselves to some sort of embedding into iTrees in ROC or something like that. So this is certainly on the agenda. And a lot of other things to cover more of Rust and connect it with the rest of the ecosystem. All right, so this was mini-Rust, which is an interpreter that precisely captures the semantics of Rust and whether a program has undefined behavior. I'm myself also involved in the Rust project, so I kind of can also talk to the people there and advocate for this to become part of the official specifications. I'm head of the operational semantics team, and I'm in contact with the specification team, which is kind of the Rust version of the editor. And generally, so far, the reactions have been very positive. People are excited about actually getting a formal, authoritative spec into Rust. So I think we are on track for this to become, eventually, an actual part of the official Rust specification, fully formal, accessible, and executable, and covering all of the language. And if you want to learn more, there's a GitHub repository here. And also, if you want to do a postdoc in beautiful Switzerland, I have an open position, so please come talk to me. Thank you.
Yeah, John.
Thank you. Really interesting talk. I just saw something flash up on your last slide. You mentioned weak memory models. I'm wondering why you need to formalize that, because I would imagine that anything that would be affected by weak memory would be undefined behavior, but perhaps I'm wrong.
Well, we need to formalize whether a program has undefined behavior. Also, weak memory affects which values you can get when you're doing atomic load, so this can actually affect even non-DB programs. And basically, there are all these formal models of weak memory, and there's mini-Rust, and we would have to find some way to make them talk. Also, weak memory has a bunch of unsolved problems, like out of thin air. Like there are formal models, and then there's the reality, and the models actually don't model reality currently, which is not great for a model. So, I mean, there's unsolved problems on several axes here.
Conrad can ask really loud, and you can repeat.
And then
you repeat, yes.
So I noticed in your model of pointers that contained provenance. If I'm interpreting it correctly, you're not allowing integer pointer casts to preserve provenance. Is that right? Or do you have a concept of like unit pointer t or something?
Right, so the question was that it seems like integer pointer casts would not preserve provenance. I did not talk about integer pointer casts because they are, I think I recently wrote something online saying they are the PL equivalent of a nuclear waste site. So the model that's actually written down in mini-Rust right now says when you cast a pointer to an integer, we put the provenance on a global piece of state called the list of exposed provenances. And then when you cast an integer to a pointer, we pick one of those with angelic non-determinism. I don't think that's actually the end spec we want, because angelic choice unfortunately has a bunch of problems. But I think this is an over-approximation of the end spec we want. I think we want an actual operational spec without angelic choice that is a valid refinement of this thing. But we want programmers to not depend on which refinement we pick so that we can pick better refinements as we go on. That's roughly currently the plan. The Rust documentation just says if you cast an integer to a pointer, it gets some provenance. And it can only get a previously exposed provenance, but we don't tell you which one.
So the claim was that this is more accessible, so now we can tell developers to go read the implementation of a separate interpreter for the Rust language. This doesn't sound accessible to me. How can we improve the accessibility to actual developers rather than telling them to go read a separate implementation?
I mean, you are the expert for that, not me.
Do you have ideas on how we can do that?
No. I mean, in the end, I think it's source code, so we can do like comments and things like that. And then beyond that, I think we'll have to see. I mean, there will obviously be docs and there will be tooling, like you can run Miri or can run this thing, and that should help. I think reading the actual source code probably will only be actually useful for very few. I think reading the definition of what is a byte and like these high-level things, that's very concise and I think very insightful already by itself. So I think for that we can just directly point people at the code. And then for the other things, we'll have to figure out how we can write docs about it. But at least I think this is more accessible than Greek letters. So there is a chance that someone will be able to take this and make it into education material, which might then broaden the scope of accessibility and things like that. So I'm not really an expert on that. But this is, yeah, exactly. Let's talk.
Okay, with that, let's thank Ralph again. Thank you. And our next speaker is now online. Let's thank Ralph again. Thank you. And our next speaker is
Testing.
Let's thank Ralph again.
Testing.
Hi, Peter. Can you hear me?
I can. And vice versa. Testing. Hello. Hello.
Hi, we need to, one of us need to talk, so we can hear you well, and glad to have you here. Okay, let's see whether we are ready. I think the room is ready. Peter, are you ready?
I'm ready.
Okay, the floor is yours. Thanks.
Great, thank you very much. So hello everyone. I'm very sorry not to be here in person, not to be there in person. It's a subject close to my heart. So I thought I would give you a slightly non-standard kind of talk. Right? I'm not really going to talk about clever things that we have done. I'm going to talk instead about things that we have not done, and more particularly about things that people should do. So language specification. You want, if you're going to the trouble of writing down a specification, you want it to be usable in lots of ways. And the last couple of talks have mentioned some of these, so reference documentation and prose and accessible maths and so on. I should say, so I have the Discord chat open at the same time, so if anyone wants to make this slightly more interactive, try typing questions in there and hopefully I'll notice them. So we want prose, we want maths, we want some sanity checking of the definition. These days, it's now, I think, hopefully accepted wisdom that we want specifications that can serve as test oracles that are executable in one way or another. Surprisingly, how many decades it took to get to that point, but now I think many people understand it. Maybe we want a prototype implementation. And then pretty soon you start wanting a bunch of other things which are problems of success. And these are sometimes in tension with each other. And sometimes when you realize that you want one of them, you wish that you had written the original specification in some different way. Maybe you want test generation. Maybe you want to generate some boilerplate. Maybe you want to render little symbolic examples, not just concrete examples. eventually you need a parser, a prototype parser, and then a full-on production parser. You need a pretty printer. You need a code formatter. Can't do anything at scale without a code formatter these days. You need theorem prover definitions, but you probably didn't want to start with theorem prover definitions unless you're a PL theorist, in which case you did. You need proof automation. You might want to use the spec directly in your verification tooling. And you would love if these things were easy to reuse and adapt. So that's an awful lot of things. And surely, to achieve all of that, we should have one meta language and tool suite that should express all of them. Well, no, obviously no. And you can think back to the dawn of time and the history of meta languages for semantics and ponder on the fact that each time we try to do something more fancy, we end up realizing that we needed different mathematics and different tooling underneath. So one should not expect to get to there. But nonetheless, I put it to you that there is a huge space between the current state of the art, which is frankly pretty miserable, and something that handles most or even a large part of these in a reasonably general way. So that, I put it to you, is a very interesting source of problems, which one can address both by building things which will actually be useful right now and perfectly legitimately on solving some of the problems that arise from it. And they vary depending on the context that you're in, and sometimes we don't articulate this variance very well. Right? The problems faced by one researcher working on their next standalone single author POPL paper are quite different from the problems faced by the worldwide C and C++ community and their standardization bodies. Different, but not totally distinct. So they vary in lots of ways, and I'm not going to talk about most of these, but all of these are important. But I thought I would talk about these last few items. Right? So we've heard a couple of talks. So I only joined at sort of your lunchtime, sorry. But we've heard a couple of talks already about very custom tooling in the context of particular languages and particular standardization communities and so on. And that's a totally good way to go. And another way to go is to see what one can do in a general purpose sense. And if so, on how opinionated the tool should be. If you're aiming to generate all of those many kinds of artifacts, then it may have to be very opinionated. But on the other hand, if it's very opinionated, maybe nobody else will want to use it in the same way. It's a big choice. People have spoken of generating definitions in multiple provers, which is a very annoying problem, which is very well motivated because you want multiple prover communities to be able to use the thing. But experience shows quite tricky to do really well because the targets are really different and idiomatic definitions in each are really different. You can't, I think, hope to have mathematically the same thing exactly. Last here is like a big question of how much one aims to generate artifacts versus to check that they abstract onto the thing that you wanted or onto the right thing. So if you have a very opinionated setup and you write one language definition in one particular tool and then you are happy with the generated output in all respects, that's good. But if you find that you end up needing to change the generated output, then that whole scheme is sunk. And instead you might prefer to be checking an abstraction, checking by abstraction the generated thing. There is some existing tooling. There is LaTeX. It's terrible. There are the classic provers. They're terrible in different ways. There are OP and LEM and SAIL I've been involved in over the years, and I can very confidently tell you they're terrible. Great in some ways, but terrible. And by induction, your favorite research tool, and I wouldn't like definitively to speak to it, but probably it's terrible too. So why is this? One is the incentives that we have to build and maintain production quality tooling. They're quite tricky. It is doable. We've seen multiple academic groups doing this, focused often on one particular context, like the mini Rust that we've just heard of. But more fundamentally, we really don't know how. So what I thought I would do was reflect on a little bit of the experience with OT and LEM and SAIL, and pull out from that challenges of things that we don't know how to do. And this is like a 5-hour talk, which I will brutally abbreviate when we run out of time. So some of you will have known some of these things, but they do get confused. So let me discriminate. OT, what was that? It's tooling for user-definable, context-free, concrete and abstract syntax, and arbitrary inductive relations over it. So that's not very opinionated about the things that you write. It's really any old inductively defined relations you can express. And it generates things. It generates LaTeX, it generates Whole for, Isabelle, and ROC definitions. Okay, LEM, in some sense a successor, but it's doing a really different thing, motivated by a different kind of problem. Right? So LEM is good for pure functional definitions, and it's roughly the core of pure Camel Light plus some libraries. And again, it generates LaTeX, now executable OCaml, and the theorem group definitions. And then more recently, SAIL. This is a very specific language, more domain specific for instruction set semantics. So it's a first order functional language with uninterpreted effects, a little bit of lightweight dependent typing, and it generates a whole bunch of stuff. So let's go into these a little bit more and sort of use them to try and sneak up on the more interesting questions for the future. So for OT, we started out, we wanted to have a source syntax for language specifications that we could read, because LaTeX was too irritating and too useless. So if you imagine you have just had the idea come into your head of a great new type system that you want, you could just start writing down the LaTeX, but that would not be a great deal of fun. Or you could just write down an ASCII file with some ASCII syntax for what you meant, just like that. And OP parses that, and it sort checks it, which is really useful sanity checking, and then generates the LaTeX. And you have to do a whole bunch of engineering to make this actually usable, which I won't speak about. And then when you want prover definitions, you just have to add the definitions of the non-free things. You have to say that, I don't know, in this case, we're representing variables with Isabelle strings or Coq natural numbers or whatever. And you get out perfectly fine prover definitions. And it's great, and it has a modest but very enthusiastic user base. So Stephanie Varick had a beautiful quote from a couple of years ago. She's continued to use OT and its locally nameless backend for much of my work. And this was, many years, 15 years after the original tool development. And other people who are not me continue to maintain it, or not me, or Francesco, or Scott continue to maintain it. But it really highlights the problems, some open problems. So you might think that you're defining a language, but you're not really at the end of the day. You're defining a whole complicated family of languages of concrete object language syntax and lexing for things and some syntactic sugar, and the language of the symbolic terms that you end up actually using in rules, which is rather different. And sometimes you need the hybrid of those two. You're defining the abstract syntax that these things denote. You typically end up with some sub-grammars and some context grammars. As soon as you start to use it for any kind of implementation, you need location information. You need to turn off some parts for presentation to carefully lie about particular things. You end up with families of related object languages with or without type annotations or with extra constructors used only in their semantics or parameterized over something, all kinds of stuff. So all of those things OT supports, but the challenge here is that really there's a little subject of operations on first-class grammar definition fragments that we should be expressing our language definitions in terms of. Right? And that's all kind of done with ad hocery there. It should be mathematically more grounded and explicit. It's really going to very hopelessly run out of time here. Let's see. Did we start? Well, when should I stop?
How many minutes do you need?
I could use as many as you want to sit through. So I'll stop whenever you want me to stop. Tell me when.
How about 12 minutes?
Okay, that's great. Variable binding are still a terrible headache. And for large-scale languages, especially the established industry ones, they've mostly accreted some really complicated scoping rules that will need some custom scope resolution anyway. But for more theoretically civil languages, you often have quite complicated binding structure, and how we should imbue this collection of grammar constructions with that, I think is still a kind of open question. There's a bunch of work on the table. Some of it is clearly good enough to get work done. None of it may be definitive. Third challenge, very, very annoying, but like PL semantics people, is that parsing is still a problem. So OT supports arbitrary context-free grammars. And for writing down rules, that's great. And for the symbolic terms that you see in rules, in fact, they're usually very tiny and they're usually not ambiguous, and you can ask the user to fix them if need be. So that's great. But it doesn't generate a standalone production parser or really give you machinery to do disambiguation. So to understand how one can smoothly go from arbitrary context-free grammar to, LR production parsers with decent error messages, that's an interesting question. I experimented a little bit with defining abstract syntaxes as explicit quotients of concrete grammar definition. I like to go back to this point of abstraction versus generation. Abstraction is in principle easier, right? Because all of the information is there. You just need to throw some away. So that may be an interesting direction. Is it executable? No. It's nicely expressive, it's very generic, but you can't run it. Useless. So, as several people have kind of implicitly alluded to here, can we identify a sweet spot of inductive relations, inductive relation definitions, where the spec author can be confident that the execution mechanism will be able to cope? That's a very delicate balancing act. And then there's a huge number of questions of the meta-language expressiveness. Right? So OT supports inductive relation definitions, which is great, often, until you decide that you need a whole pile of auxiliary functions. Right? And then it's no good. Right? And that realization, when we wanted to define some relaxed memory semantics, drove us to invent this lem tool, still wanting to avoid prover lock-in by generating definitions in multiple different targets. but with a decent pure functional language. This too, in the domain in which it works, it's great, we still use it. There are large definitions of ISA semantics. We translate from lem to whole4 and Isabelle via lem to give a nice abstraction above those provers. It looks good. Here's a bit of lem spec for some of the semantics of dwarf debug information. You generate a camel. It looks the same, except it's instantiated the numbers to particular things. You know, all the comments are preserved. It's all good. But these definitions, we use them for execution a lot, but they're not very good for doing proof above, because it's hard to target very idiomatic usable definitions. The different targets, they really are different, and to what extent that can be reconciled is not very clear. Another expressiveness question then. How fancy a specification language type system do you want in terms of the modules or type classes? Lem supports some simple type classes, seemed a good idea at the time, but later the lack of fancier versions made large-scale specs like the Cerberus use semantics of Cave and Mammarian really quite awkward to phrase. And in fact, a chunk of that has now been ported back into a fragment of OCaml, because we just didn't have enough module system. Handling partiality, still a terrible pain in the neck. Right? And again, target dependent, what one would want to do. Distinguishing computational and non-computational things, not an issue at all if you're working in some of the targets, but totally an issue for the other. So it's a case again where generation isn't really enough without extra data in the source. When we moved to looking at instruction set semantics, they're full of bit vectors. And you need, in the end, dependent types, just lightweight dependent types for those. But because Lem was targeting whole4 and Isabelle as some of its main targets, Lem is very determinedly not dependent. But here you need them. So that path led us to SAIL, which is for instruction set semantics in particular. So this is a more specific goal, so it can do a better job by being more constrained. Simple first order imperative language, lightweight dependent types. And from SAIL, we generate multiple things. And here, we're generating via Lem, whole4, and Isabelle. Tobias Grosser's group have recently done a SAIL to Lean backend. Nate told us about a thing I didn't even know existed, which was a SAIL to Rust backend. And there's also a SAIL to Rock backend. And here, because the source language is source spec language is so tight and simple, it's possible to generate quite decent code for these, although of a scale that challenges the theorem provers at some point. Okay, so then if we actually want meta languages for large-scale programming languages or for semantics researchers that are not custom built, if we want tooling that I could give to my undergraduate students to let them just exercise some semantics, what should we use? I don't know. I think there is, one can imagine, roughly the shape of tooling that would be fit for most of those purposes. But one has to really solve some of these problems of the classes of algebras that you want to work over and the classes of inductive relation definitions that you want to permit, and the classes of the level of type theoretic strength that you need in your meta language. And it's not just more is not better, right? Less is better, because less strength in the meta language lets you do more things with it more easily. So there's a bunch of trade-offs, and maybe they need to be switchable trade-offs. Just to end, so there is a great history of related work here, dating back 5 decades, and people sometimes tend to forget it. So I encourage everyone to go off and look at a whole pile of this stuff, because many of these are really not new problems. So there we go. I don't know what formal languages are suitable for specification of semantics. I have a pretty good idea of what we want good tool support to provide, and how we actually engineer the building of them in ways which are usable not just by their developers is a challenging problem. And in order to get there, we have to sort of get over a threshold of usefulness. So we're tackling not necessarily all of these challenges all at once, but a decent, sorry, far too many overlays, a decent subset of them simultaneously. And with that, I thank you for your time and attention. And if we have any time, I'm happy to have any questions or discuss later.
Thank you. So Peter is like, it's like a lecture that I've been dreaming about, and I really want to listen to your 5-hour lecture on this topic. Thanks a lot.
Well, I'm happy to give it, but your audience may rebel.
I know. So you need to come to Korea to give real in-person lecture. Okay, here's a question from the floor.
Hi, Peter. First, thank you for your talk. This is Sasha. Regarding LEM, which I've been, as you know, using a bit recently because I'm tinkering with servers sometimes. Sometimes it feels like it would be much easier if it was just a DSL embedded in OCaml that does the same thing, instead of just being some OCaml very, very like language that compiles to OCaml and then other things. What's your opinion on that?
Yes and no. I think when we started out, it was our intention to have a proper syntactic and type system sub-language of OCaml. And you would get a giant win by just, in implementation terms, by just being able to take the OCaml front end and turn stuff off. But there was like a stupid reason, which is that in hindsight, no, I don't know if it's totally stupid, we were doing a whole pile of very set theoretic definitions of memory models, axiomatic memory models at the time for C++. And we really wanted special syntax for set and list comprehensions, because we wanted readability. We wanted the final thing to be typesettable as decent paper math. That's sort of a stupid reason, but a real one. The more substantive language design reason is that for the library design turns out to be a giant problem, a giant interesting problem, which we did not understand at the start. And being able to set up a decent collection of type classes for different numeric types, that sort of can be mapped onto the different targets, in the end was really useful. As a little aside, you might think that if you have some type of numbers, then you want that to be mathematically the same type in each of the different targets, and that turned out not to be the case. So, I don't know. Kaven's experience in using it at scale for servers over the years, I think, is that the type system, when the language is good, partly because it restricts, all specification languages are good because they restrict what you do, right? And then restricts what you do quite a lot. And for the large-scale structuring, the problem becomes a bit more like a programming language design problem. This is a rambly non-answer to your question, but those are some things. Yes and no.
Okay, so we are a bit late for the next panel session. So Peter, thank you. Please thank him again.
Yeah.
And yeah, I'll talk to you later. Thank you.
Thank you.
Okay, it's a long day. We have the last panel session. So for the panelists, you should bring your own chair to front. 그렇죠. 랄프 체어를 그걸로 주시면 되겠다. 그 체어를 주시고 지혁이가 그 의자를 놔주고 타닥하면 되겠죠? Sorry?
This will block you.
Oh, I'm gonna be over here. Yeah. Sure, sure. 아, 감사합니다. 마이크는 우리가 2개인 거죠. 그다음에 나 전화 좀 주세요. 감사합니다.
핸드가 2개인데
어허,
이거를
그걸 제가 가지고 있고 둘씩 나눠 가지고.
Hello.
Hello.
Yeah, so this one works.
Hello. Talking to the mic.
Wow, everyone's a critic. All right. There we go. Good.
A bit late, like 10 minutes late, but we are gonna end right at 5:30. Okay, thank you everyone for staying with us for a long time, and I really enjoyed this workshop. I hope you did as well, right? And okay, as a moderator, I'm going to start with individual questions for each of you, and then I will ask everyone a few questions, and then we will take questions from the floor. Okay, the order is different. So, okay, I'm from Chao Hong. Okay, as we've heard today, there are many different language frameworks, including K, Redex, Sail, ES-Meta, Spectec, and others. What do you think is unique about the K framework? What makes it particularly good compared to other frameworks? What compromises has the K framework has to make to be successful?
Yeah, thank you for the question. So, I think based on my experience, so K is unique in how it's, if you look at the development of K, which really started 15 or even 20 years ago, it follows a quite different path than maybe other semantic approaches, tools. In a sense, it's engineering first, engineering driven. So when K took the shape, and gets evolved and so on, there is no theory behind it, and we did that on purpose. Not by we, I mean the lab. That's actually before I joined the group. So actually and it's all driven by a very concrete engineering goal, which is let's define the semantics of C. Completely. So each and every corner cases, like undefined behaviors, implementation defined behaviors, all of that is define all of them in something which we call K. So whatever that takes means we need it, right? For in a scalable semantic framework. So basically, in the first 10 years of the development of K, it's the process of defining real-world language semantics and see where's the bottleneck of the existing semantic approaches and how can we accomplish those bottlenecks. And most of the bottlenecks are on the engineering side. So if you look at semantic approaches, like operational semantics, there are many, many variants, denotational semantics, axiomatic semantics, and so on. They all work great on small examples. Like they work very beautifully, very elegant. But you realize things start to break apart when you want to extend your language, right? So suppose you have a very simple side effect-free language, and then somehow you want to add side effect as a feature, and you realize you're in a situation where you're fighting against the hard work you just have done. Why? Because everything that you defined in the past does not take side effect into account, and suddenly you have to go back and change everything. So that makes the development of a formal semantics of a language very non-modular. So it looks like you have to somehow have a very good understanding of everything you need at the point when you start it, and that's just not realistic. So I think what's very unique in K is that it really takes into account of this, realistic considerations. A formal semantic approach that wants to be scalable must have this engineering, good support for notations, modularities, and so on. So I think that's probably one of the most unique feature of K. And then theory comes later, right? So once we get to a point where K becomes, very stabilized, and then we sit down and sit back and look at it. Okay, so what is K? And then, that's where the theory came in. I would say maybe 10 years after K, we started on K. So that's, I would say, what's unique about K. The other part, which is not very unique but is very emphasized in K, is the executability. I think Peter also mentioned that. So, of course, I think specification language can take various forms. But if you're talking about the canonical semantics, then that probably should be executable, because the only way that you want to test the semantics correctness is by massive testing, right? So you have massive test programs. You can test the semantics by running those programs and so on. Right. I think I'm probably taking too much time, so right.
Yeah.
Thank you. Yep.
Thank you. And Jonathan, you shared your experience at Google using symbolic execution for automated reasoning of P4. And what tools do you think are missing for automated reasoning of P4? And how can mechanized specifications help with that?
Great question. I think tools that are missing, one of the things that I would really like to see, and which I actually just told you we built, so you'll be a little confused, is a proper symbolic executor for P4. One that can take in a symbolic packet and output a set of symbolic packets going in the right way that is performant enough and where I trust the correctness enough that I can connect 64 of them together, say, to simulate a data center scale fabric. This would be a game changer for us. Even without the performance, it would already make a lot of our things better. The issue with the thing that I showed you is that we actually don't really rely on its correctness in almost any interesting way. This was maybe a little bit swept under the rug, but the thing that it says it comes out is not really used for diff testing in any particular way, right? We send it through this other simulator. If we really trusted this P4 symbolic thing completely, what's the point of having the second simulator? Well, that's a nice open source simulator used by more people, so we trust it more. How can mechanized specifications help? With that specifically, obviously it would be great if it was derived from some mechanized specification. But more generally for P4, I think there are a number of nice opportunities. There isn't really a particularly good, I guess there isn't really at all reference interpreter. The thing that we use is this BMV2. There's another interpreter as well, and they use sort of different architectures. So even something like that would already be great. And as a PL person, I'm a huge fan of having a single source of truth, right? I would say that our community is quite a bit smaller than the JavaScript community. So we don't really have a particularly good process for how you make changes to the language. Important context here, I am also a co-chair of the P4 language design working group. So this is my fault, you should think. But I haven't been for very long, so it's probably still my fault. So I guess if I were to introduce such processes, I would love if they looked less like the WebAssembly from a few years ago, where you have to go through all of this stuff, which frankly, the networking people would just never do. and more like what I am hoping and assuming WebAssembly looks like now, where there's one small, well-defined thing, and everything else falls out.
As a co-chair of the language design working group, are you interested in having such a process for people?
Absolutely. I was just talking to Michael about this. I'm not sure what I need exactly and how to make it lightweight enough to... we just have so few proposals now that in some sense we don't really even need a process, right? I can kind of just make it up as I go along. But I think there's a significant human cost to not having a process, which is you don't even know where to start, right? If you want to update some feature, like if I'm not part of the group, how do I know where to go? How do I know how to pitch something to say this is a thing I'd like to be part of the language? Even if the process is uselessly simple, like come to this working group and talk to Jonathan, that's already better, right? It kind of gives you a way to approach the situation.
Yeah, I strongly agree with that. Yeah, and Michael. So you are one of the 3 editors of the JavaScript language specification and one of the first advocates of ES Meta. You were so excited when we contacted you. So what made you so excited about ES Meta, and what are your thoughts on it now after using it? You already mentioned it.
Okay, ES Meta is not the first attempt at mechanizing ECMAScript. As Philippa mentioned earlier, like her group had done this years ago for ES5 or 5.1, I believe, and only in strict mode. So some subset of it at that, and then like years before that. Arjun Guha and Sriram Krishnamurthy at Brown had done a mechanization of ES3, Lambda.js, long time ago. I was still in school back then, So those were great, but they were not useful, and I want to say that kindly because it's not that the work was not good; it's that they reflect this snapshot in time. And JavaScript as a language is constantly evolving, and the language at that time is no longer relevant, it's no longer used, it's constantly moving. So the important thing about ES Meta that really makes it stand out is that it's automatically deriving this mechanization from the spec. So as we update the spec, we are updating this mechanization and then all the tooling that derives from it. So that's what makes it like really exciting because now it can like actually be practically useful for us within the committee to do things like we do with it. Like automatically type checking the spec. So that really got me excited, and also the fact that when we worked together to do this implementation, we worked to get to a point where there was no really strong dependence. It's always a bit scary working with like an academic project that you don't really know what the future of it's going to be like, and you don't want to tie yourself to it. Yeah, students graduate, they move on, and this is not a problem. I'm not complaining about that, but like you can't really tie yourself to these kinds of things because you don't want to get stuck depending on it or trying to continue maintaining it yourself. So the fact that we got to a point with integration where we have the ability to like add exceptions to certain parts that would then be excluded, and we can always and we pin versions. We don't ever have it like automatically bringing in new things. We can really be confident that we will always be able to continue moving without it being a hindrance, but always providing at least some help. So it was really great, and now we feel very good about our relationship there. Whether it continues to be updated as it is, which we're very happy about, or whether it doesn't and it still provides value.
Yeah, great to hear that. Thank you, Ralph. So you are the only one who suggested a question from these panelists. So that was tooling that ensures that a language spec has anything to do with real-world use of the language. That was what you wanted to talk about, right? So could you share your thoughts about it?
Sure. Yeah, I mean, basically, so before Mini-Rust, our many years of work on this tool called Miri, and that is really what enabled me to do Mini-Rust. So Miri is a tool that it's a testing tool. You can run your Rust code in it, and it tells you whether there's UB. It's testing, not verification, so it's only is there UB on like the part of your library you're actually testing. It picks one of the many non-deterministic choices, so like it's really kind of sampling there. But that like this started as an experiment for me to have a ground truth that I was trying to figure out some of the gnarly bits of the Rust spec that I haven't even mentioned in the talk. Stack borrows and tree borrows, for those of you that have heard of those things. So I wanted to, I mean, it's very easy to write a formal spec, and then, I mean, very easy. We all learn how to do it in grad school, right? You write a formal spec, you prove some things about it. It's great. But then, like, how do you know that the spec you wrote actually matches reality? And so I wanted to avoid the situation where we would write a spec which ends up declaring, and I'm not just concerned about like, oh, the spec says 5 and the program says 4, like that's just bugs in the spec, right? Like, okay, sure, we fix those. But I'm more concerned about the problem where the spec says, oh yeah, 80% of the code out there has undefined behavior. At which point it's like, okay, so clearly this is not actually a useful spec, right? Like people need a different language. If that's the language they actually have. So I wanted to avoid that. And so that is where Miri came from. So that way I could have some ideas for what the spec should be. I implemented Miri and then I run it on some tiny pieces of code. And if that already explodes, then it's clearly no good. And so slowly over the years, I made Miri into a tool that can actually run on like medium-sized pieces of code. It's still horrendously slow, but computers are really, really fast. So you can run them on like sizable code. And so at this point, we are fairly confident that the semantics in Miri, modulo a few places we know very well about because people send us bug reports, the semantics in Miri are actually practical in the sense of they allow programmers to do enough unsafe code shenanigans that they can do the things that they need to get done while remaining within the scope of those rules. And so now we just need to take what Miri does and make it into a like more condensed, purer artifact, which is what mini Rust is meant to become, and then eventually put in the theorem proof and things like that. So yeah, the main thing here is that like when you are, at least for languages like Rust, where there's kind of a bit like there's 2 steps to a language spec. There's like, is this even a valid program, or does it have UB or not? And then if it has no UB, what should it actually do? And for the first part, there's a very big risk that you specify your language in a way that completely ignores the needs of your programmer. And I think this is a real problem that the C and C++ communities are struggling with, judging from the fact that -f no strict aliasing is enabled in most major C programs. So there's lots of UB in the standard, which those people are turning off because it doesn't match their needs. And I would be very curious about the results of like running something like Miri for C on larger C code bases. But it's very hard to do for C because C has a lot more determinism and a lot more UB as well. So I wanted to avoid that failure mode. And the only way I know how to do that is to just try it on real world code. So you need to have a tool like that and then spend a lot of time on getting this tool into the shape it needs to have to be practical on real world code. So most of the effort we spend in Miri is not figuring out the spec. I mean, that's hard, but that's the easiest part, honestly. The next part is making it so that Miri is just horrendously slow and not even slower than that. Which I mostly inherited, honestly, from the people that designed Miri, but I had to add some parts to it to make Miri cover more of the spec without making it slower than it already is. And then the other thing is that people, when you run this on real-world code, people will inevitably use operations which are not in your core spec, right? They will print to standard out, and they will ask the system for a random number, and they will, like, I don't know, set an environment variable. And so we have in Miri thousands of lines of code of just implementations for all of these operations directly on the abstract machine level, so that we can run all of the code out there. And we have obviously only a tiny fraction of the real-world APIs, because in the limit, this is like a full re-implementation of the full API service of like Linux and macOS and Windows, which we're not going to do. But we have enough to run like some interesting programs, and we have like ePOL now, for example, so we can run the core event loop of Tokyo, which is very unsafe heavy, so they really wanted to be able to test that. And you can run some simple async programs. Someone is implementing like file system access on Windows, because I wasn't motivated enough to do that for this other platform. But like it's slowly growing, and it's completely orthogonal to actually figuring out the details of pointer provenance, all of that stuff. But some of it is still spec work because you want to, of course, model the abstract spec of these operations and not the actual implementation. But yeah, the point is that like there's a lot of these things that go into having a tool that can U/B test practical code. And then once you have that, you can gain some confidence that your spec doesn't accidentally rule out 3/4 of your ecosystem. And I wouldn't know how to do a Rust spec with confidence without having tooling like that. That was basically
Yes, thank you. Wow, what a panelist. What a good set of panelists. Okay, let me move on to a common question in the same order. So the title of the first talk was Programming Languages Must Have Formal Semantics, period, right? So you need the formal semantics. Why the others? What are the formal semantics for, and what good things we can get from the formal semantics?
Right. So, well, that's definitely a very impressive title, I would say. But basically, so ultimately the argument is if you really care the correctness of a program, then a formal semantics is not an option, right? It's a necessity, right? Because without a formal semantics, then by definition you don't know what's the behavior of the program supposed to be, right? So there's no point of talking about correctness. Of course, that's a bit exaggerated, but I think the idea stays there in the sense that ultimately formal semantics is not avoidable. So I think what's really probably more important is the implication of that argument, which is, if formal semantics is not avoidable and it's extremely difficult to develop, then let's make sure that we get the most out of it, which means that I, sit down, I spend, half a year, I understand one language, I have my formal semantics down, and that's it, right? So I want to generate tools, parsers, interpreters, compilers, debuggers, verifiers from that single semantics, because I spend a lot of effort in making sure that semantics is right. So I want a framework. I want an approach that can, cover the tooling part for me. So basically, we want to decouple, programming language design from programming language tool implementation. And I want to say that I think formal semantics one thing, and I think the specification language, or how do you want to present the specification of a programming language? I think that's a related but different thing, right? So within K, we also think about I understand K is based on the rewriting term rewriting systems, and it looks pretty alien, right, to developers. So that's why we have this sort of like a documentation compiler, right? So you can kind of like a pretty printing a K definition into this graphical representation. But even that could look very alien, right, to developers. So I think we definitely need a variety of different specification languages, formal, informal. Just help and they fit different needs, right? Sometimes developers just want to get a good understanding of something, or they want to see something executable maybe. So I think we can have lots of different spec languages out there, but formal semantics, at least what we try to do with the K is that we acknowledge that it is difficult to do. So
one unique thing about K is that graphical visual representation. So I'm not sure whether that's approachable or accessible to usual developers. So my follow-up question is, can you give us some examples of outside users of K?
So we try to, so at some point we have some collaboration with the hospitals. So basically they want to formalize the protocols of some emergency procedures, like the
in computer science.
Right, because you can imagine, right? So because sometimes I think it's actually during the COVID time, but the project itself is not about COVID. But basically, some people comes in, it's an emergency, and the doctor has to do some, follow some procedures, and depending on the readings from the patient, right? So the different procedures should take place. So they want to formalize that protocol, and so we use K, and apparently the the rewrite rules are pretty much so sufficiently good enough, right, to the domain-specific experts, right? So they, of course, they need some training, right, to understand. Actually, we didn't even show them the graphic representation. We just showed them the text version of K, which is like rewrite rules and so on. But yes, it needs some explanation, right? So what is the configuration? What are all these semantic cells? What's rewriting a REST step means and so on. But then, things becomes like I would say okay-ish, right? So that's never been a bottleneck. But I think it's really boils down to the motivation. So in that case, right? So the domain-specific experts are motivated. There are incentives to understand what we do. But in general, if you ask a developer and ask them to read, a write-based spec, they may lack motivation, right, to do that. So what's the point? I'd rather read something written in nicely in English with examples and so on. Yeah.
Thanks. So, yeah.
Can I ask a follow-up
sure.
question real quick?
Yeah.
What makes K the right tool for that job? Like, I'm having trouble seeing what where would I use the interpreter maybe? Or like, I'm trying, I don't quite see how I would use this compared to, say, just writing a pseudocode maybe, which is more or less an algorithm, right? Might be how you specify procedures.
Right. So basically what they're looking for is some spec that is executable. And I think that just falls into the comfort zone of K.
Executable for a person or executable on a computer?
On a computer, right? So they want to monitor the actual actions that the GPs are taking.
You do have some condition and actions, but there is a series of conditional actions. They never try to run it. So.
Okay.
Yeah, there are different people. Okay, so about P4, P4 has a language specification, but it's, yeah, I know. So what do you want to change in the specification? And in various P4 calculi, the papers say that if we have a formal semantics, then it will be much better than now, things like that. So what would you expect to have a formal semantics for P4?
Yeah, so I mean, I guess I think it depends. The usefulness depends on the user and the community, right? For me personally, I would like to just look at it to understand what a program does. Get some of that sweet, sweet Greek back into my life, and I think that would be excellent. From the community perspective, a lot of the people looking at this are not really programming languages experts, much more in the networking space. And probably they have no particular interest in looking at the actual formal specifications, but certainly they have a large interest in the artifacts that you get from those, right? So insofar as a mechanized specification can give you, like we were saying, a reference interpreter, amazing, right? Everyone would love a reference interpreter. That's great. Or make you able to make some minor change, and now the prose of the specification will automatically update to reflect that. Amazing. That also sounds great. I guess what I'm excited about for the future of the community is what it means for you. The ability, the fact that a language has a formal specification, I think makes it a stronger playground for PL researchers, right? The things that you can do with it, just everything has a lower barrier to entry, right? When there's already a formal specification there in some sense. And there's already many papers on P4, mostly in the networking community, some also around here. But I mean, the stuff that PL researchers would come up with, I think is what excites me, personally.
Sounds good.
Not to pander to my audience or anything. But
yeah, thanks. So as I said before, ES Meta and Spectec are a bit different in the sense that ES Meta, Ecmarkup 262 is the God, right? We just take it for granted and we use those terms and phrases in the specification and maybe a little extension later, right? But Wasm Spectec, here DSL is the first, that's the single source. So about ECMAScript specification, do you think it's possible or desirable to have some kind of formal rules in the specification? Or would anyone like it?
Okay, so I think we kind of saw a theme here, at least in a couple of the talks, about we need to have a specification framework that is appropriate for the thing you're specifying in each context. And in my talk, I made this argument that the thing we're trying to accomplish with our specification is that the engines that implement it are not going to diverge. They're going to implement the same thing. So it needs to be formal enough to get to that point while still being accessible for like all the different kinds of readers that we want to have. I don't see too many reasons at the moment to have any additional formality there. We are. If we were not able to get to the point that ES Meta has gotten to, where we can like generate this reference interpreter, I would say maybe that would be a useful case. So we can have like an oracle to test against. But like the language is regular enough that we're actually able to do that. Additional formality, I could certainly be convinced if given examples of why this would be useful, but without actually seeing the like practical purpose at the moment. I don't think that is valuable.
So let me rephrase my question. Let's say we have another language, say P4 or Rust, another language to have well-defined, standardized specification. So which one do you recommend? Natural language or formal rules as the single source of truth?
Oh, that's gonna be so. That's so dependent. I don't think I can make that call, right? That's gonna be like really, really. You have to take into account all the factors around it. So, yeah, I'm gonna step away from that one.
Very dangerous question. Back to Ralph. What do you think?
I mean, I obviously think it should be something formal because that's how I did mini Rust. I mean, the starting point is very different, right? Like JavaScript had this already very detailed, very regular English prose specification. In Rust, we don't have anything like that. We at the same time, we are kind of burned a little as a community, I think, on the system side by having. I mean, okay, the term formal specification, so let me briefly define that. By that, I mean like something mathematically formal. So I would call everything that is entirely just English normally informal. This your kind of English maybe is maybe that's formal, but like something like the C and C++ specifications, they are formal in the sense of like being documents adhering to a certain form, but not mathematically formal. And there is a big problem there about the ambiguity this creates. And it's causing actual issues, and like researchers trying to define the spec of C and C++, and then, well, who knows what the spec is, right? We need to talk to the committee. Like, well, how long does it take to resolve all these questions? It took 10 years to resolve provenance, and it's not in the standard. So it's a technical report. So like there's kind of an example of this going wrong, or at least like not as well as people in the Rust community would like it to go. And so I think in that sense, they were very receptive to the idea of starting with something very rigorous. And also from my side, it was an entirely pragmatic choice. I mean, if I wanted to do this in natural language, I would have developed serious amounts of tooling that can then actually make this executable. Whereas this way, I could just write some code, and then I could put a master student on making executable, which was it was basically translating it from almost Rust into actually Rust, and then we can run it. So it's a very pragmatic choice to get started. And at some point, we'll have to figure out how to incorporate this into the Rust standards process, which there is a natural language specification being developed there. And whether these will be just separate artifacts that are manually kept in sync, or one is derived from the other, or the other derived from the one, I think that's still largely open. But the choice for me was a pragmatic one, maybe also a lack of creativity. Like I didn't think you could actually do this English language thing as well as JavaScript seems to have done it now. Maybe this would also work for Rust. I think it's a bit trickier in Rust because the language has like all these weird like ghost state things which don't actually physically exist, but in principle it's all just operation semantics. You could express it. So yeah, but I mean I'm a PL researcher, so of course I default to doing this in a formal way.
Exactly. So I understand that that's a pragmatic choice for now. But do you envision, or do you want to have mathematically formal specification? Not at all about natural language, but formal semantics for Rust.
Yeah, I mean definitely. Like I mean we want all the, like as you already mentioned, all the nice tooling that comes out of that. something like, I mean, in Rust it's kind of, we're doing it a bit backwards, where we first have Miri and then we extract the formal semantics from it. But of course, going forward, we hope this will be the other direction. Like as language extensions come, they are specified and then they're just implemented in Miri. So you need formal specifications for tooling like that. And Miri has been very successful as finding UB bugs like all over the ecosystem. We can find similar success stories in neighboring parts of the ecosystem. For example, in LLVM, they have this tool called Alive, and now Alive 2, which has found tons and tons of bugs in optimizations, which is now routinely used by LLVM programmers. So LLVM has become, so Alive, the encoding of LLVM semantics in Alive has kind of become a de facto semantics for the fragment of LLVM it can handle. And you can't have Alive without formal semantics, because what's it supposed to tell the SMT solver, right? Like, can't send a bunch of English there. You could try this with an AI, but I wouldn't recommend. So like I think like what you get out of this is this tooling, and at the same time the tooling is how you convince the practitioners that it's worth it, right? Like we've been telling, obviously, like if the LLVM people had ever asked, we would have told them for decades that they need a formal semantics, but they would have been like, why? But now we are getting to the state where there's very concrete benefit from these kinds of tools, and that is what convinces practitioners that it's worth spending the effort of like working on a spec, or at least supporting the effort if some academics show up that are crazy enough to do the work for them.
Great to hear that. Okay, so let's take some questions from the floor. Yes. Oh, that's the mic.
Yeah, so when we have a formal specification, or mechanized specification rather, we can generate a reference interpreter for a language. Maybe my question would sound too naive, but I will still ask it. Is there any hope that actually practical implementations will also be somehow generated? Does it make sense at all? Or, yeah.
Right. So I think maybe the elephant in the room here is the performance, right? So you pay a cost by having these auto-generated tools, and in K we currently stand at 1 order of magnitude slower than a handwritten interpreter, and there are various optimizations you can do, right? So you can do it on the K side, on the interpret side, and there is also something interesting you can do on the semantics level, which is basically, so we call it semantics-based compilation. So what it does is you can have a program, and you can execute the program symbolically as much as you can, and every symbolic execution of a basic block gives you a semantic rule, which is essentially like a partial evaluation of the program, right, using the semantics. And in principle, that's a compiler. If you think about what a compiler, well, a compiler is the partial evaluation of interpreter given the program. So you can do that symbolically. So, and the result of that is a new semantics, but that semantics are specialized for a program. So it's as if you're doing compilation at the semantics level. So that's like a semantics level optimization. So, so all these are like work in progress. So we do hope, but I think the performance is definitely one of the big issue, right? But I think we are getting closer and closer. I think one lesson that we've learned in K, in the K area, is that if a methodology works, then there are always going to be engineering advancements that make things faster. Yeah.
Right, but I mean, I don't know if you were asking about production like compiler interpreter. I think for the compiler part, my answer is no. I mean, you said it's 10x slower than a handwritten interpreter, and that's still like, what, 1,000x slower than the compiler in -0 or something? I mean, so this is not going to replace the actual compiler you use for your production-grade code. I mean, on the interpreter side, there's also very cool things like meta-tracing compilers. I don't know if anybody tried that for K, but I would recommend looking into it. It's very cool tech, basically JITs for interpreters to get runtime binary code. I want to try this with mini-Rust one day. But like for deriving the actual compiler on the backend side, like you're not the amount of engineering effort that goes into making LLVM practical and fast is not going to be replaceable by anything like this. And it's not just the backend, right? Like you can, I mean, we've had parser generators for decades, and yet no practical like production grade compiler uses a generated parser, Because with a generated parser, you get terrible error messages and like often also not great performance. So this is an area where we've had generation for much longer than for the backend part, and yet we don't use it for the production grade compilers because it's just not good enough for what users actually need for the production grade tool. So I think those will remain separate, but they can be very useful as like fuzzing oracles and things like that.
Hi. So I've got a comment and then probably a question-ish, if I can turn it into a question. So Michael said my favorite quote of the day, which is, "Let me know if I say industry jargon that's not real world." I thought that was... Yes, sorry, Jonathan. I'm going to talk about to Michael, so it got in my head. So now for Michael, so you said that we did some JavaScript work, mechanization work that was not useful because it went for, it doesn't matter. It's fine, but I am going to challenge you. Because we did Ecmarkup 5 strict, and then it got to Ecmarkup 6, double in size, good strategy. And we stopped at that moment for obvious reasons. But in particular, for our point of view, it wasn't about immediately going to the standard, although we were talking to the standards a lot. We enjoyed very much those meetings. In fact, we were after the methodology of how to do it, and that methodology turned into WASM-cert. And WASM-certs, for many reasons, turned into WASM Spectec. So in particular, this is all about methodology. So there's the short-term notion of useful, which is that standard can use it now. And then step back, the more long-time notion of useful, which is the methodology. And now we're on the methodology of the WASM Spectec and what we can do. So in particular, whether it will be our version of how to do it, or ES Meta, or Ralph's work on mini Rust, in our different ways, we are creating methodologies for that future. And so I guess the challenge for the room and the question for the room is, for those next languages, what do we need to do in order for those standardization bodies to be receptive for these methodologies? So I think that's where we're at.
Mm-hmm. Yeah, thank you. Thank you for the nice summary. And do you have something to say?
I agree. It was the friends we made along the way that was the value there, and I didn't mean to diminish that. Yeah, I guess repeating myself from earlier, the things that we need to do to make to get that like immediate value for the standard bodies is to have that you know, continued like support of these living standards. All the web specifications are all living standards. They're constantly evolving, and taking these like snapshots in time is while useful for learning and methodology right there, is not useful tomorrow as soon as things change.
And I almost think it's more than this. So one thing I was really surprised about by engaging with the JavaScript standard was actually you guys were formless. You didn't have the math, but at the same time, the precision with which Mark Miller, others talk about what they are doing is impressive. And so, you know, in my world, I would write that precision in mathematics, and then almost I can hand wave after that because I've got the language to be precise. So, so in some sense, it's given that wonderful group of people in the JavaScript world, what happens over the years that one gets them, I say a little bit arrogantly, I don't mean it like this, to the place where actually they might write it down in a way that gives them the freedom to be more hand-wavy in their speech.
Okay. Any question? Yes? Oh, 1 second, Ralph, and then, yeah. Yeah?
good challenge. I think you were also asking about how can we make this more accessible to the communities? How can we make them more likely to adopt this? We're about to see how this goes with P4. You know, the co-chair is only as good as his community, so I'll see what I can do. I'm also from the P4 language community, right? Sorry, from the programming languages community. So I'm of course supportive, but yeah, P4 and PL. Anyway, I think it's almost exclusively, with maybe 2 exceptions, a human problem, right? And I mean, this is kind of part of it, what makes it tricky. You can't just sort of technical away until now you're done. Now, there are technical things, right? Like showing people what they get out of doing this adoption, that's huge. But otherwise, you need to integrate in the community, start early, start getting them used to the idea that this is a concept that you might even possibly get into, right? And then you have to meet them where they're at. And this occurs a lot in industry, but I find is often a very hard and painful thing as a programming languages person. Sometimes when they're wrong, you just have to do their wrong thing and formalize that. And that's really hard, both mentally, like, is this what I want to do? And also, like, sometimes actually, because it makes your specifications real weird sometimes. But then once you have it, the formal specification there, now you can be like, well, you know, look at these 3 segments. These are kind of weird mathematically. Should we try to like simplify this part by removing this? Right now, you can move to the more beautiful world that you maybe were envisioning for the language in the first place.
Right. Before Ralph, yeah. Are you done? Yeah. I mean, our guy working on P4 Spectec, he had this table, and he's just pointing out, this entry is empty. It's undefined. And before having all those semantics spelled out and all those discussion with the community, we didn't know and they didn't know and they still don't know. So it takes time. It takes time to understand their weird word and weird semantics and describe that precisely and talk over and over again until we understand each other. So I think that's the human factor that we are willing to take to make a big difference. Thank you. You're done?
I was just going to mention it's not, I mean, this is not really an answer to the question, but sometimes the way this can happen is also if the communities realize by themselves that the way they have been doing it doesn't work. So like if they've suffered for sufficiently long from their informal specifications, that you can offer them a better way. Like I think this is currently happening in the C++ concurrency memory model world, where they had, like, for the latest revisions of the standard, they meant to basically just copy a certain part of a paper and make it part of the standard, and they made a mistake while translating the paper formalism into English, and now the standard doesn't say what they wanted it to say. And this has been not the first time they have problems there, but like at least some of the people in that community are now, from talking with them, ready to go to a world where the formalism is the authoritative spec and the English is just explanation for it, just because they've been burnt by lack of rigor in the English. Because these people are very good at making the English precise, but there is a limit to how far you can stretch that until you, like, it's just really, really hard to do it without an actually formal language. So that's not a recipe. You can't obviously don't want to make a community suffer for a decade before they then come to you for a solution. But some communities are in a spot where it's just much harder than it seems to be in the JavaScript space, for example, to actually make this sufficiently good and with pure English.
I think that's right on the right track. This question, I think, is getting at, just having a shared vocabulary for being able to be precise. And you may be more comfortable or familiar with this like shared vocabulary you have with your colleagues. That's more mathematical. But Payne has evolved this use of English within the spec within the committee, as you mentioned, for all of these the participants to be using these terms that are all very, very clearly defined to each other. And they may sound actually like generic terms if used outside of that context, but within that context, they have a very, very specific meaning. And you have to be aware of it by knowing the hundreds and hundreds of defined terms that we have in the spec that we use to communicate with each other. But like absent that pain, I think it accomplishes the same thing. We are able to be precise in our communication with each other, and if we weren't, if we were not able to evolve into that space where we are now, we probably would have moved to these other more common formalities.
Sorry. I want to ask a really short question. So I want to ask about everyone's general strategy or approach to really making a programming language specification. Like more specifically, if you are told to write programming language specification right now, what would you do? What is the first thing would you do as your approach? I want to ask about that.
And my two-word answer is to write a reference interpreter.
Similar to that, but of course, if you were to do it with K, right? So the first thing would be to try to understand the runtime model of that, and basically, using case terminology would be started with the configuration. So what is the state basically all the pieces of semantic information that you have to know if you want to execute the code, right? So for example, if you're writing spec for a multi-threading language, then most likely there should be some the structure represent holding all the threads and so on. So start with the configuration and do just the minimal amount of syntax so that you can write some simple programs, and then add semantic rules on the fly, right? So, but I think the configuration and understanding the runtime state of the language, and of course that's not something you do you finish you complete at the very beginning, but start with that and then evolve from there.
Are we talking about like my language specifically or languages in general? Feel free to do a gesture. Got it. For languages in general, okay, production language. Oof. See, now it suddenly got hard. I was going to say for my language, of course, I just talked to Jay and Suki. I'm going to say, pretty please make me a formal specification. I guess for languages in general, I'm much more on the production languages in general. I'd be much more on the Ralph side here. I'd want to do a reference interpreter. For some small domain-specific language that I was designing, I go straight to the math. I just write a denotational semantics or an operational semantics.
I'm going to again give the weaselly answer. If I think it really depends. You have to. Yeah, you.
42, right? Okay, then next, last question.
Thank you. So for the context, Julia from Mozilla and myself, we are at the JavaScript committee. We are trying to bridge industry and academia. So I actually have a question for you, Sukyang. So what would be your advice to the PL researchers who are here, who want to contribute to widely adopted languages and their standards?
Ooh. Can I answer this question? Anyone first? Yes?
Yeah, maybe I can start. So one thing I learned from not my work, but actually at this Daijun Park work on defining the semantics of JavaScript, is that something basically you can generate a lot of test programs out of the semantics. And I remember one thing that Daijun did was he defined the semantics of JavaScript, and he ran the existing JavaScript benchmark programs using the semantics, and to test the coverage of the semantics, right? So he observed that some semantic rules have never been triggered, right? So he wrote some more JavaScript programs, to cover those, corner cases, and then he tested the, at the time like Chrome and Firefox and so on, right? So it's using the new benchmark programs. I found a couple of bugs in those. So I think that could be one way, right, for specification language to help. So basically, once you have a specification, generate some programs, right? So make sure that you have a very solid, comprehensive benchmark programs, because it would be very useful, right? So for production tools and so on. Yeah.
Now I have some answer, maybe not the right answer. I think what Michael said is really important. We need to have shared vocabulary. When we say specification, we think something different. When we say formal semantics, we think something different, right? And everyone has different interpretation and different value. And the important thing is that we do not need to compete. Like there's K, there is others in JavaScript and WebAssembly. They may interact each other. Like I was interested in this question, like K, it's really well used in some languages, but does it also cover interoperations with different languages and all sorts of questions? And so I think this could be some starting point that we get together, learn from each other, and maybe next time we invite Peter to give 5 hours lecture. I think it's gonna be more than 5 hours, right? Like 2 days or something, but I love to hear that, and I hope we can learn from each other from now on. Okay, so with that, thank you for the long day, and let's give them big hands.